Welcome to the 2025 BME Technical Summit. We are thrilled to have you here for a day packed with innovation, collaboration, and cutting-edge insights. Our theme this year is Mining for Today and Tomorrow, Integrity-Driven Innovation. And we've got a stellar lineup ready to unpack just that. My name is Lungile Kulu. I am the HR Projects and Enablement Manager for BME, and yes, I am your co-MC today, even though I usually deal with people, not explosives. Show of hands, who's attending their first BME Technical Summit today? Yep. Well, I'm very excited to be hosting my first ever Technical Summit and to learn from the speakers from around the world today. I'm not alone. I am with my fellow co-host who will hopefully hold my hand through the day. He is a lot more experienced than me. Please welcome Dirk.
Good morning, Lungi. That was for you, by the way. Lungi, thanks for joining me. I'm very thankful for you to be here on stage with me, and I think the audience even more so, otherwise you had to suffer the likes of me the whole day. But from our side, myself and Lungi, a very warm welcome. We're very humbled to host all of you here today and very privileged. We have here our regulators, without whom we won't have a sustainable, stable industry. We have some of our customers from South Africa, from SADC, Greater Africa, and even further in the globe. So welcome to all of you, and as Lungi has said, I think we've got a very good program lined up for you. Now, as you may know, the moment a production person gets up and talks in front of customers or regulators, there's most probably a significant amount of explaining ahead. So today is no different, but we'll start off as we do as part of our culture in Omnia. We believe in safety first. So we'll start off, and Lungi will introduce our host today from the CSIR, just to explain a couple of house rules for us in terms of safety and the organization of the day. So Lungi, over to you.
Okay, great. We're here to guide you through a day of brilliant minds, bold ideas, and maybe a few explosives, just the safe kind, of course. But as you're aware, safety is our #1 priority and value for Omnia. So before we get started, we would like to invite the CSIR SHEC representative, Morgan, who will talk us through the safety protocol on the usage of this magnificent building. Please welcome Morgan.
Good morning. Welcome to the CSIR International Convention Center. My name is Morgan Mahlangu. Sanitizing stations are located in the foyer and all around the building. In the unlikely event of an emergency, an alarm will sound throughout the building. Trained responders will give instructions on evacuation. Stay calm, take only belongings that you can carry. Emergency procedure: walk in an orderly manner, do not run. Responders will lead us to an emergency exit, then to the assembly point. General information: restrooms are available throughout the building. Please look out for signages. As this is a public building, please do not leave your valuables unattended. Wi-Fi information: free wireless internet access is available throughout the building. Select free CSIR ICC on your device and no password is required. Select free CSIR ICC on your device and no password is required. I thank you. Enjoy your time at the CSIR Convention Center.
You can go.
Morgan, thank you very much. Mike's not, there we go, thank you very much. Also at Omnia, we don't always just prioritize safety. We also prioritize our values. And we've made it part of our culture to at events like this and where we get together to take a short while just to share something relating to either safety or our values. And I've recently come across a small article where it says that, and it speaks to parents and partners. So if I look around the room, I think there may be a few of us that fall in that category. And the article went on to say that studies have shown that parents and partners, our cell phone usage is the new secondary smoking. So I don't know if you can recall all the ads in the 90s and the 80s about when you're driving and you're smoking and your baby or small kids are sitting in the car with you. And the article went on to explain that our behavior as partners and parents when we're around these very smart mobile devices can be even more toxic to our relationship and our health to that extent than secondary smoking. So I'm going to appeal to all of us to, we often download an app to try and apply some management discipline over our teenagers. Maybe time that we start downloading an app for ourselves as well, and just take cognizance of our use. And then more specifically for this event, please, a lot of time and effort has gone into the preparation for our presenters to come here and share with you the experience that they've gained over the years. So please mind your cell phone and your electronic devices whilst we've got the presenters going. I am sure you've got the latest and greatest ringtone from Benoni, but let's rather keep that for the break. And for our international guests that don't know what I'm talking about, all the better for you. Thank you very much.
Thank you, Dirk. We have a jam-packed agenda with speakers from around the world, and to help us officially open the summit, please welcome a man that needs no introduction, a driving force behind BME's vision, our MD, Mr. Ralph Henniker.
Good morning, ladies and gentlemen. Maybe to start off, just a little numbers game. In 2025, this is my 23rd Technical Summit, and it's the welcoming of the 26th actual Technical Summit. I would like to welcome you all, especially our customers, our stakeholders, industry stakeholders, regulators, our speakers today that we referred to already, international speakers, local speakers, and then of course also our colleagues from Omnia and from BME. Thank you all for joining us today. It is a privilege to address you today, reigniting a tradition, a cornerstone of BME's engagement with the industry. Maybe a little history, and I had to dig this up a little bit myself. The first conference was held in 1993. Until 2017, there were 25 consecutive conferences. Then in 2018, we had an unfortunate restructuring in the company, and then that led into 2019. And then we all know that in 2020, COVID hit. And then, unfortunately, and I must apologize profusely, our company, they went into a bit of a slumber as far as the technical conference goes. But just the technical conference, nothing else. I'm stoked to see so many of you today. We've got about 350 delegates. As you know, when we had the first conference in 1993, we started with about 15 people. It was more like a technical workshop. This room here was pretty empty, could count the people on 2 hands or 3 hands. And then we ended up with 450 delegates, and today we're ready. As the first reignition, we've got 350 delegates. So we are very, very stoked to see all of you today here, and also the newbies, and there's a couple of you too. I hope you enjoy the day with us. Those who attended in the past will recall this is a day and a space to learn for the day. It is a day to connect with each other, and it's a day to share knowledge. And we would like to make this not a legacy. We're looking forward. We would like to reintroduce this day on an annual basis going forward again. But what we realized just for planning this day is how much material and how much knowledge there actually is that can be shared in the industry. My name is Ralph Henniker. I'm the Managing Director of BME, both for the explosives and chemicals side. I've been part of the Omnia Group since 1995. If you now calculate back, I joined the company a week before the third technical conference, And I'll never forget, there was a story that Mark Thomas was still the managing director. And 1 week into my tenure, as we ended the closure of the conference, he said, "Ralph, you knew, but you're going to close this conference for us, right?" I almost ran out, or jumped out the window. I thought, no way, this is not for me. I can't do this. So anyway, so 20 years have gone by, 30 years have gone by, and here we are today. So yes, my tenure started with Omnia in September 95, and it's been a really, really exciting journey. We also, over the last 5 years, added a lot of talent to our BME leadership team. And it's always nice to get fresh talent in there and teach old hats like myself a trick or two. And I would like to take this opportunity to maybe introduce the leadership to you today, starting off with Mr. Dion Swart here. If you could just stand up that everyone can see you. Our Chief Operating Officer. We've got Megan van der Berg is in the house. Megan is the Managing Director for Africa Explosives, as well as Global Chemicals. We've got Lucy Diole, our Financial Director. We've got Ramesh Durgapasat. Don't know where you are, Ramesh. There you are. GM for SHEC and Operational Excellence. We've got Nishan Haripasat, our General Manager for Marketing and Technology. We've got Dirk Voigt, who's the MC today, who is a man of many talents. He's the Head of Production, Logistics, R&D, and Engineering. We've got Nick Dreyer, Head of SADC Operations. Nelly Tandakwayo, our Head of Legal. Neil Alberts is in the house, our GM from Canada. Welcome, Neil. Kasturi Adari, our GM from Human Resources. And Lefa Musiala, last but not least, our Head of Chemicals. Welcome to all of you. And I am once again stoked to be part of a team like this. You guys make it happen. As Dirk said already, the theme for today is mining for today and tomorrow, integrity-driven innovation. Now that reflects challenges and opportunities in the industry. But what it also does, it speaks to BME's own philosophy. Innovation must be responsible. Innovation must be fit for purpose. And innovation must be grounded with integrity. And that is what we are hoping to see today. Fit for purpose, real practical examples, make it happen. Innovation must help us in the industry today. The program for today includes many perspectives, emerging technologies, sustainability in mining. We're going to talk about smart drilling and blasting practices. We're going to talk about integration of solutions. And we're going to talk about how to improve safety and productivity in our industry. And we are proud to host a global lineup of speakers. We've got speakers that came as far as from the US, from Sweden, and from Australia. And they will share their expertise and practical insights with us today. The conference theme furthermore reflects what Dirk has been mentioning, Omnia's values. Be safe, respect and grow, achieve excellence together, and do the right thing. And the purpose of Omnia and that of BME is one to innovate to enhance life, together creating a greener future. We hope to fulfill many purposes today. As already mentioned, this is a knowledge-sharing platform, but it is also a platform to share case studies throughout the industry, and not only positive case studies, but also negative ones, because those are the ones that we are going to learn from too. This is a learning platform. This is a showcase for innovation, and this is giving back to the industry. This is also, as already mentioned, a networking platform. So please use the lunches, the coffee breaks. I already saw a lot of that happening pre-conference, and I hope a lot happening post-conference from a networking platform perspective. not only with us, but amongst each other. And I know a lot of you are looking forward to that. We've also got 4 breakaway rooms for those who are interested in a little bit more detail in our technology. And we've got 2 plant visits tomorrow and Friday, and there's a real good turnout for those plants visits as well to see how we produce explosives. So that's a real opportunity to share some of that knowledge as well. As we embark on today's journey of learning, my hope is that you find real value in the knowledge being shared, the conversation sparked, as well as the connections made. Once again, I want this to become an annual tradition, and we are already working on 2026 version. Also, Lolita was telling me. Through collaboration, innovation, and integrity, we are shaping the mining industry that is safer, more sustainable, and more competitive, not only for today, but for generations to come. And this is a really exciting time for the mining industry when it comes to innovation. BME's commitment is to add value through our products, our services, our knowledge, and our partnerships. Maybe just 1 or 2 minutes on BME itself. I'm not going to bore you with a lengthy story, but BME has been on a significant growth trajectory over the last 5 to 6 years. We've been expanding in South Africa. We've been expanding in many countries in Africa. We are taking our knowledge, our products, our services, our skills to global jurisdictions. We are currently operating in Canada. We are operating in Indonesia, and we are operating in Australia. Our strategy is based on 2 large pillars. The one is protect the core, and that means our traditional South African and African business. We are here to stay. This is our home ground, and this is the market that we are going to keep on supporting. But at the same time, we're going to grow internationally, and through those jurisdictions that I just mentioned. 18 months ago or so, we also integrated the chemicals sector into our explosives solutions game. Many people ask why we do that, because there are synergies in the market for sure, but mining chemicals are those that liberate the minerals at the end of the mining cycle and at the end of the process. And we offer the blasting solutions up front, but then also monitor what is happening at the plant. Some call it mine to mill, we call it mine to metal. So we're very excited about that space. Penultimately, we are firm believers that any strategy, especially in the volatile macro environment in which we operate today, must be built on a strong foundation and uncompromised basics. With that, I mean, we need an impeccable safety record, as Dirk said. We need quality in services and products. We need sustainability drives. We need supply chain security in this volatile environment. And we need for the industry to trust in our people. And we hope that we bring those attributes to the mining industry today to a large extent. At this point, I would like to thank Omnia for the trust they have in the 1,800 people in the mining space. We want to thank Omnia for the services and support they lend us to achieve our own ambitions on a global basis and a global stage. I would like to thank the local and international partners that we have today. I'm going to start with Canada, Consbeck. We've got Richard Walker in the house with his son. He's our partner in Canada. We've got MNK, who are partners in Indonesia. We are partnering technology-wise with Strayos and Dyna Energetics at this point. We've got partners in Africa like Ultimate Industrials, and we've got a partner in Sweden with Hypex Bio, Thomas Gustafsson, who will address us later with groundbreaking non-nitrous technology as well. I would like to thank our stakeholders again in the industry. I would like to thank the regulators, and I would like you, the valued customers who joined us today and share this day with us. With that in mind, please allow me to introduce our CEO for the Omnia Group, Mr. Seelan Gobalsamy, to address you with a few thoughts. I thank you for coming today, and I hope that you enjoy the day with us. Thank you very much.
Good morning, everybody. Thank you, Ralph. Thank you, Dirk, and thank you, Lungi. It's a great start to today. Welcome to all of you. My job is quite a simple one. Firstly, it's great to see so many customers, staff, partners, service providers, regulators, and others here. We're all amongst friends. Please use this time to engage, and let's create a better world for all of our citizens. Just a little bit about the Omnia Group. Omnia started in 1953. That makes us 72 years old this year. The business listed on the Johannesburg Stock Exchange in 1980. And we roughly have about 4,000 people, and we're in 22 countries across the world. We have two core businesses, an agriculture business, which most folks on the African continent will know us well for. And then we have our explosives or mining business called BME. It's fascinating for me to see how these two businesses interact with each other, how they linked from a supply chain perspective, and how they linked from a production perspective. I guess when I talk to my kids or people that ask me, and the kids are often the ones who tell you, we don't know what you do, Dad. I tell them it's the same chemical that grows something, that blows something up, and that's nitrogen. It's how we all linked together. Our two businesses is premised on doing good and doing things the right way. Ralph has spoken about our value system, the way we think about doing things, and also the way we think about not doing things. So where things don't fit with our values, with our culture, with safety, where things don't fit with the environment or leaving the world a better place, we walk away from those things. However, where our two businesses unite, they unite in terms of innovation, they unite in terms of data, they unite in terms of precision, being accurate, and using a number of new tools. I spend quite a bit of time on an international board where we've got a number of mining and fertilizer CEOs present. And one of the challenges we faced as an industry, and Ralph has said he's been in Omnia or in the industry almost all his career. And if I were to ask for a show of hands here, how many of you have been in mining for under 12 months or in explosives for under 12 months? Can you put your hands up? 2. How many of you have been in this industry for over 15 years? There you have it. It's a simple show of hands of how few youngsters we have, how few youth we have coming into this industry of mining and agriculture. And today, I think we've got an important role to play to make this industry, to make this sector exciting for new people to join, for youngsters from university, from schools, from folk that want to link analytics, data, AI, autonomous ways of doing things into agriculture and mining. And I'm so absolutely pleased with BME's agenda, with all the toys they have outside, showing us how they do that. Not only does Omnia do that through BME in mining, but we also do that in our agriculture business. In agriculture, we focus on being precise, we focus on innovating, we focus on doing what is right for the environment, and we thrive on science-backed research. I want to encourage all of you today to consider giving a little bit back, consider how, from a thought leadership perspective and from a leadership perspective, we take this industry to where it needs to be: cleaner, greener, safer, and underpinned by strong, strong values as Ralph has mentioned. So today is a day of engagement. It's a day where amongst friends we can talk about what's working, we can talk about what's not working and what needs to change. And I think that has to be underpinned by this world we live in. And let's stop for a minute and just think about the world we live in today versus the world we lived in 10 years ago, 20 years ago, 30 years ago, or 50 years ago. Currently, supply chains change overnight. We heard yesterday or the day before what happened in Denmark. It changes shipping routes, it changes supply, it impacts demand, it impacts price. I got and I know you said we shouldn't focus on our phones, Dirk, but yesterday I got a little WhatsApp video of an autonomous truck driving in Shanghai. On the main highway, the truck is going, there's no driver, there's no one in, a whole host of sensors, and the colleague of mine is sitting in a car next door, driving past it. The world around us has changed. From a climate perspective, we see climate change amongst us everywhere. I've got one of our colleagues here. I saw him walk in, our head of strategy for the Omnia Group. MXO, are you here? I saw you. MXO, yesterday or Monday morning, I had a coffee with him early morning, and he said his house was struck by lightning. Windows broken, massive chaos, more lightning strikes, tougher storms, hotter conditions. Climate has changed. Now, let's take that to and we've got a number of colleagues in the US, please forgive me, but if you look at what Mr. Trump is doing, he is changing things overnight, changing things by the minute, and then rechanging it the next minute. I guess as leaders, and all of you sitting here, you have to deal with this volatile, this uncertain, this changing, this ambiguous environment. Let's act and consider all these changes, but let's build a thought leadership platform. And Ralph, I'm encouraged to hear that you want to continue doing this annually. I wish you all the best to achieve that. Let's create a platform where that thought leadership that is underpinned by strong values, that is taking into account the change across the world, the uncertainty, the volatility. It's putting all of that together, and it's creating the innovation and the basis for our sector, for our industry, to make a profound positive difference to our customers and to the world we live in. So I look forward to engaging with all of our BME colleagues. I look forward to listening to our technical experts and our colleagues around the world that have come here. Thank you for making this long trip to South Africa. This is the most beautiful part of the world. We encourage you to leave all your money behind here and invest in South Africa. Buy nice holiday homes at the coast, and please keep returning. And to all of my South African colleagues and friends, the Omnia staff, the BME staff members and friends here, it's great to see you. Please engage. Look at our innovations. Tell us what we can improve. Tell us what we can change. Let's make the world a better place. Let's bring in young people into this sector and industry. And my job is to make sure that we build successful businesses that's able to provide the funds, to provide the capital, to have events like this, and to ensure that our businesses, that our companies, that our solutions are sustainable, not for 1 year, for 2 years, but for decades to come, and that BME and Omnia will be around for the next, I think Ralph said it's 72. He started with a numbers game, 72 years. So thank you, everybody. Enjoy the engagement, and I look forward to meeting you all over the next day. Thank you.
Thank you, Seelan, for that introduction. Always inspiring listening to you talk. Now, before we introduce our first speaker, we would like to remind you to please download the BME Summit app to make the most of your experience today. This will be your go-to guide for the full conference program, real-time event updates and reminders, breakout sessions, details and locations, speaker profiles, as well as the polls and surveys. Now, if you complete our mining technology survey, you stand a chance to win one of 3 field bar coolers.
Lungi, thank you very much, and Rolf and Seelan, thank you very much for those kind words and welcoming everybody. Also on this app, and I'm glad I have Lungi because I've got no idea how it works, so please don't ask me for help. But if you see if you need help, anybody with the BME logo on the shirt will be able to assist you to open the app. We will use the app during the conference or the summit as well. If you click on each presenter's tab, there's a space for you to leave a question. So we please ask you to make use of that. We will allow, with the time that we have, only 2 questions at the end of every speaker. So please use the time during the presentation to note down your questions as part of the app. With that, and thank you for all the welcomes, and thank you. I think we kick off our official proceedings now, and I'm going to start, ask Scott Skvaria to come. Scott, amongst us, and he doesn't like it if we say that, but to us he's Yoda of blasting. Scott, with over 40 years of experience in engineering, management, and technical leadership, he's basically the Yoda of blasting. Over and above his decorated career in mining, exploration, and construction, Scott has also developed and delivered comprehensive blast crew training programs throughout the world. He currently holds the role of General Manager Blast Science and Engineering in BME and is a long-standing member of both the International Society of Explosives Engineers and the Society of Mining Engineers, and has frequently contributed to the global industry conferences. Scott told us that it's always good to know, if you know where you are, to know where you've been. So Scott is going to tell us a little bit more about how we got to where we are today and share a little bit of history with us and bring us down and through to the present. A warm hand for Scott Skvaria.
Appreciate it. Good day, everybody. I'm Scott Skvaria. I've been a blasting professional for 45 years. It's exciting times. And it's exciting to be with BME because they are part of what's going on in the explosives industries today. So we talk about blasting science, okay? A blast is a symphony of harmonized wholes. We do engineered blast designs, and then we take it out to the field where operations delivers that to a level of operational excellence. The initiation system controls the timing, detonation sequence of the blast, and the explosives in the blast hole release that energy at the right time to generate shock and gas to break and move rock. And what we're looking at is a series of very technical blasts around some very critical infrastructure performed by one of our clients. This is a prime example of what great blasting looks like. But blast engineering looked a little different back in my early part of career. We focused on fundamentals and first principles. As an engineer, you had to be a draftsman. You had to have experience and intuition to understand how rock would perform. You also had to be a researcher. There was no web, there was no Google. We had to go by the book. There was no AI. So this is what we produced on engineering sheets, very complex excavation sequences and drill and blast designs. Explosives in the field, pretty limited. It was largely a box and bag business at the time, working with high explosives and bagged ammo. Required a lot of physical labor to get out there and get a blast off. Initiation was dominated by electric blasting, and electric blasting was complicated. You used to have to know what you were doing to get a blast off. Complex electrical calculations and living within the bounds of that initiation system. Started out with conventional blasting, then we moved to sequential electric blasting, and sequential electric blasting gave us a degree of control over vibration. It allowed us to design blasts using fixed time periods to manage vibration to the 8 millisecond rule. So when you look at a blast design, you see things like, you see 17, 42, 65 milliseconds. All that originates back to these original sequential timers. And this was the improvement. We had great control over vibration, improved, and we also had increased fragmentation. And coexisting alongside electric blasting was non-electric blasting. It was in its infancy, okay? We saw cap and fuse used largely in the underground mines. Here in South Africa, I seem to remember the number being something like 8 million units a month at the time. Detonating cord and MS connectors were used on the large surface mines to generate their blasts. And interestingly, you know, we had limited control over the release of the explosive energy. So large blasts looked a lot more like explosions than detonations. Then came the first transitional surge. And this was the advent of the introduction of non-electrics and the initiation system. The signal tube technology led to a rapid and widespread uptake in underground and surface mining. It wasn't susceptible to extraneous electricity. It didn't require complex calculations. It was fast to hook up. It wiped out electric blasting in a period of 5 years. In the final battle between non-electric and electric initiation, we saw improvements in delay precision, and we also introduced programmable sequential blasting. We could do blast designs that on paper looked pretty good and would do different things, but because we're still working with pyrotechnic delays, we never realized the full potential of those designs. Blast recording systems, one of the real advents coming our way in the future. Back in the day, this is what blast recording systems looked like. It was often in a field book, sometimes on the top of a box. So, you know, figuring out and going back to blast to see what you did previously at an operation could be a little bit arduous, if not impossible. Our assessment tools were pretty limited. High-speed filming at that time was considered really advanced blasting technology. And high-speed filming not only required you to be an engineer, it required you to be a photographer. And you had to learn how to take photography. And if you did everything right, you got a blast or film that looked like this. It allowed us to look at intervals of 2 milliseconds. So at 500 frames, we were able to see 2 milliseconds of real time. Sometimes if your high-speed film imploded inside the camera, this is what you were left with. And you could spend a lot of time, money, and effort to get to this point. The boss usually wasn't very happy with you either, nor was the client when you missed the shot. Second great transitional surge, okay, the advent of rapid and widespread use, uptake of emulsion explosives delivered by bulk. It was a conversion from AMPHO to heavy AMPHO in coal and metal mines. And it was the conversion of AMPHO and packaged explosives to straight emulsions and emulsion blends in water-filled holes in small diameters. This technology largely ended the box and bag business. Early emulsions, pretty simple in nature. It was nitrate and water solution, fuel, an emulsifier to help keep it all together, and balloons to make it sensitive to detonation. And emulsions have grown. You know, there's been a lot of innovation over the years to make emulsions better. Okay? First, sensitization methods were changed. We went to gassing rather than physical sensitizers to control density. We learned to manipulate the rheology of the product. There we go. So, I mean, emulsions can be made to be very thin, or they can be made to be very viscous, so they stay in the hole and aren't attacked by dynamic water. There's been a lot of work done on the emulsifier side of things to make really robust emulsions that have long shelf lives, deal with multiple pumpings without crystallizing. And we've had a lot of work done on alternative fuels. And one of the things that I found exciting about BME was the use of used oil. In the US, it was kind of frowned upon. You know, you come down here and they've absolutely mastered the use of used oil in explosives. We tinkered with different bulking agents, polystyrene to make lighter, less shock generating explosives. We tinkered with different energy enhancers, largely aluminum, to help drive fragmentation. And kind of the thing that lies behind this is the process technology. That's really where Dirk comes into the picture. It's like, it's one thing to make an emulsion, but the mechanical engineering that goes behind that is quite fascinating. So talk about youth coming into the industry. This is also a place that could be of interest to people. We had a lot of interactions with the nitrate-based explosives and reactive ground, and you know, it led to several incidents where people were injured and even killed. It took us a while to understand that relationship between nitrate-based explosives and reactive ground. And through chemistry, we were able to introduce inhibition to those nitrate-based explosives to slow down that reaction and allow us to work within a known safe loading window. And Rocky's going to touch base more on that later. All right, so let's talk about theoretical explosive energy based upon composition. It used to be an arduous hand calculation. Thermodynamic equations, it was not for your average bear to figure this stuff out. Now we have these detonation codes. Again, ideal detonation codes based on the same thermodynamic equations. The challenge is that each manufacturer uses a different standard ANFO to generate their relative and absolute bulk strengths that get published on the TDSs. So the takeaway here is that, you know, these detonation codes tend to be company proprietary. You want to use them as a compass within a given manufacturer. So it'll give you an indication of what that energy looks like. But if you step outside of that manufacturer, then you start comparing energies, you're going to find that it has variability. So you need to use that judiciously. Detonation codes. Wonderful thing, ideal detonation codes. The one thing they don't take into account is detonation efficiency. Detonation code doesn't know whether you're shooting a cube of ammonium nitrate or whether you're shooting very refined product. So how do we go about leveling the playing field, understanding energies of explosives? Okay, so we go and we do physical measurements. out in the field at a lab where we do measurements to measure the shock energy and the bubble energy. So we prepare test charges, we take them out to the pond, and then we detonate them. And we record the bubble energy. And now, aided with computers, we calculate the gas, the shock, and the total energy of an explosive. Now, these things are all relative to themselves. So if you measure different explosives by different people in the same pond using the same methodology, then you do have a true understanding of the energy differences between products. Third transformational surge that I went through was the shift to PCs and the digital revolution. It upended our blast design, blast assessment, and blast modeling capabilities. It also created the opportunity and enabled the first blast hole deviation devices and the first face profilers. Adding a digitizer to these workstations was kind of magical, because before, when we did fragmentation assessment, that was our fragmentation assessment tool. Thumb, kind of looks, yeah, that one looks better than the last one. Didn't really have measurements. So with the digitizer, now we were able to take photographs and we were able to digitize particles and then do sieve analysis by hand. Took a lot of time to do it, but it gave us a real measurement. Digital photography made that a lot easier to deal with, and then we actually had imaging processing that helped us along with that fragmentation assessment. Blast modeling, first generation of blast modeling software to predict blast outcomes, muck pile displacement, fragmentation, and the rock damage envelope. I was gifted with the Unix workstation, and then we could start doing discrete element modeling. And this really was an eye-opener, because now we're able to look at particle motion, and we're also able to look at fracture mechanics. Computations like this used to take, well, the better part of 24 to 36 hours to run. Today, it's like lightning. You can do it on the desktop, right in the field. Fourth great transformational surge, GPS. Wow, wasn't it something to suddenly be able to figure out where you were at some place? And it's like, oh, now you can start mapping fragmentation against the location. We did a lot of work, especially in ore control, with the ability to go out on the muck pile and survey that in and understand where we were at relative to the detonation sequence we had employed. It also enabled the first drill positioning systems. So now, the driller kind of had to follow the design that we put forth from the office. It transmitted that design to the drill. He positioned the drill, drilled the hole. And with rock recognition, we started to be able to do some of that mapping too, based on the pull down pressure, rotation, etc. And Bob McClure is going to talk about smart drills and the advances that have come out of that technology. It looks a lot different these days. It's like the dream of stakeless drilling. It wasn't so much stakeless drilling back then. You still had to go put your stakes out. Why? Because the GPS was blind, especially in the corners. That tends to be less of a problem these days. So fifth transformational surge, the use of UAVs. I mean, this really was an eye-opener. It's enabled us to do photogrammetric surveys that have allowed us to do blast designs like we've never been able to do before. You really don't have an excuse for fly rock these days because you can go out there and get these surveys and design blasts that have the appropriate amount of burden on them to prevent fly rock. Now, this was the first drone video that I had seen. This was taken up in Alaska, and I was like, wow, this really changes the perspective of things. You know, we're not looking at things on a flat level. We can get up and behind and really get a good view of what's going on. Now we take images and we do photogrammetric fragmentation surveys, and Tamara's going to present a full paper on that later this afternoon. Sixth great transformational surge, electronic initiation systems. Man, was that exciting. You know, that was around 2000 or so. And, you know, as a blasting engineer, all of a sudden, we had that true ability, 1 millisecond accuracy in our blast. And we had a degree of control like we never had before. We also had the ability that we had a checkable system again. Non-electrics were a faith-based system. You snap all the plastic together, you set it off, and you hope it all functioned correctly. Now you can go back in and check your blasts before you ever set them off. If you need to do any troubleshooting, you can get that accomplished ahead of time. It's not susceptible to extraneous electricity except lightning. It's not difficult to use. It's fast to hook up, and there's a digital record behind it. Computer-aided design allows us to take those designs out into the field. And we moved away from fixed delays. You know, you still see people doing electronic blast designs with 9 and 17 and 42 and 65 based on old rules that no longer apply. You can get away from that. You can do vibration analysis that allows you to understand what your site-specific constraints are and allows you to design blasts to that. That's young Tom working with some of the first electronic initiation. Electronic initiation has really stepped up the game. You know, there continues to be improvements in the robustness of the systems, the expansion of the number of delays that you can fire. I mean, truly, today it's almost unlimited, and we can detonate these large mega blasts out in the field. I think Ralph briefly mentioned our partnership with Dyna Energetics. We're working together to build an HMX-based initiation system that's resistant to very hot and very reactive ground. And there's also the emergence of wireless initiation. So seventh transformational surge, integration of blast design, software, field data collection systems, smart drills, and MMUs. There's been a real surge in this area in the past 5 years, I would say. There's a lot of time and energy by the different software and manufacturing companies to get viable systems, ones that have a high degree of data integrity. You know, these systems allow us to do the design in the office, take that design down into the MMU and into the field, and it allows us to load those holes exactly as we want and program the timing exactly as we want to, you know, degrees of integrity that we haven't had before. Now, there's still some challenges, okay? You got to be able to measure the hole depth consistently at the same point of the collar. You got to deal with fallback out in the field. Point to the measured hole, it's a human thing yet. Blast hole deviations, that's due to geology, and hole loading variations due to start-stop mechanisms on the MMUs themselves. And still, communication outages do happen. So we talk about data integrity. I sit on several drill and blast reconciliation meetings with different clients each week. And it's interesting to see how each client is using these data recording tools to look at the accuracy of what they're taking from the engineer's office out into the field. It's getting much, much better. Everybody's getting a good understanding of what's going on, and you're starting to see progress. I've watched one client move from, what was largely explosions to what we showed earlier, very fine-tuned detonations. One thing that hasn't been replaced yet digitally is the tape, the twine, the stick that we need to measure the holes, especially those filled with water, to get our stemming heights correct and also to get our explosive holes correct. So there's an opportunity. If somebody's really onto this, I've seen all kinds of contraptions over the years. Still, a measuring tape is the tool of choice. We are in the midst of what I consider one of the greatest explosive transformations, and this is the introduction of hydrogen peroxide explosives. We've been looking for an alternative to nitrate-based products for decades, and we're there. We're really at the dawn of a change where you're going to see a lot less nitrates used in order to use hydrogen peroxide. Some of the advantages are hydrogen peroxide, when it detonates, doesn't generate any ammonia. It doesn't generate any nitrate residuals. It leaves our water clean. It doesn't generate toxic NOx gas. Very important in the coal mines in some regions. It has a lower intensity of manufacture than nitrates, so it's helping to contribute to our ESG goals. It's emergent technology. It's brand new. We're going to go through some learning curves with that, but again, as emulsions matured and gained usage, we'll see the same thing with HPEs. We have a great partner in Hypex Bio. It's so exciting to work with Tom. Every time I'm with this man, I feel like with one of the giants again. It's going to change the way we do things. It speaks to our key principle of innovating to enhance life, together creating a greener future. I worked with one company, and I talked about hydrogen peroxide explosives, and I was politely told, please don't talk about that, or you don't work here anymore. So it was kind of fun to come to BME when I brought this idea forward to Ralph. It's like there was a lot of acceptance, not only for the idea of HPE, but also for the idea of partnering with others rather than trying to do it in-house. So, artificial intelligence, that's the new buzzword of the day, right? It seems like you hear the word AI in almost every conversation. Dirk talked about the cell phone. You can't touch your cell phone without AI interfering with your life. I just got a new one. I hate you because it wants to control my life. It seems like it's everywhere. You go to conferences, and you start counting the number of papers that have AI incorporated into them. It really takes some sifting through these papers to understand, is this true AI, or is this some other form of AI that we're reading about here? AI is an umbrella term, right? It covers basically software that mimics the way humans think, perform complex tasks through analysis, reasoning, and learning. Robotics, I have a bit of a fascination with that. We have some robots in our plants. It's gratifying to watch them at work because they do it so well. The digital technology and the sensing has really improved the quality of product that comes out of plants. I used my little AI graphic user interface, and I asked, please, show me a robotic miner in the future. And this is one of the images that it threw up for me. Robot with a pickaxe. So you got to be cautious with AI. AI doesn't know what AI doesn't know. We've got to help educate AI and give it some idea of what mining is. We need to change AI's perception of some of the things that are out there. Now, I have a fun job, right? You know, it's like Ralph looks to me and says, yeah, please, see the future. Where are we going? How are we going to innovate and advance blasting not only today, but in the decades to come? I don't have a digital crystal ball that I sit around. What I do have is I'm a big fan of a card game called Exploding Kittens. And my favorite card in there is See the Future, and I get to look at the top 3 cards before the other players get to play those cards. That's kind of what I do. I look deep into the future to try to see where blasting is going to go. So, these are my three cards, all right? In the not too distant future, seemingly impossible, abundant, low-cost energy. Humankind, aided by AI, is going to crack the fusion code. We're going to be able to harvest hydrogen and turn it into energy. Seemingly impossible metallurgy and manufacturing. We're going to have super alloys that never abrade or break down while drilling or cutting rock. People see lasers. Well, lasers have a limited life. We're going to have long life lasers. And I've seen some prototype laser drills. Absolutely fascinating. It's like, this is coming sooner than we think. Seemingly impossible chemistry and chemical engineering. Electrochemical plasma blasting. Great stuff. It's novel. You're essentially exciting electrolytes with high degrees of energy to break rock. The challenge with that is it takes a huge amount of energy to get to that point. But it's going to happen. Once we get low-cost electrical energy, other things become possible. I'm a bit of a geek, I admit it. I mean, I do sit and dream about nanotechnology. It's going to have some impact on the explosives industry. I'm tinkering with it right now to improve detonation efficiencies. And you know, when you're sitting there in bed, you start, if you're into organic chemistry, you start seeing different chain molecules. And it's like, oh, that one would be interesting. It's like, but how do you make that? It's like, so we have some terrific explosives coming our way. It's just the manufacturing process involved to get there. So to conclude, blasting science, okay, it's discover, develop, and utilize knowledge and technology that realizes valuable, sustainable solutions for our clients in the extractive industries. And with that, I'll conclude.
Thank you. Thank you so much, Scott. That was very, very insightful. We will be taking one or two questions before we move on to our next speaker. I believe we do have a question already on the platform.
Lungi, yes, and Scott, thank you very much. Very insightful, and thanks for taking us back and bringing us back to where we.
I'm hoping to take you forward too, Dirk.
So I was hoping that you wouldn't listen too carefully to what I said, and that you wouldn't touch your phones. So please, we ask you to do use your phones and enter our app and post questions there. If you want to ask a question now, I believe the way to do so is to flip up that little microphone in front of you, and I think there's a green button or a bar that you press, and a little red light will go on, and then you're welcome to state your question.
Don't vote me off the island, please.
Scott, we do have one question, and the question is, single-hole firing, is there a universal firing window to use for acceptable vibration and air blast while achieving optimal fragmentation?
All right, so let me restate that question. It's, I believe the person is asking, is there a universal firing window to control vibration? The answer to that is today, no, okay? Because of programmable timing, if we do our background, our vibration, where we develop the site-specific linear regression equations relative to the rock type at that site, we can go back in and we can simulate firing times that, resonate within that particular rock mass. So with electronic initiation, now we don't have to conform to, say, an 8-millisecond window. That's the old USBM rule that comes out of the United States, and that was based on pyrotechnic technology. And the reason you had 8 milliseconds was because that was the window where you didn't have a high probability of delays overlapping with each other when they fired. So it's still carved in stone, and it's still regulated to that. In Hong Kong, it's 5 milliseconds. Other places have different ones, but it's interesting again with clients. There's a fixation sometimes on hole-by-hole firing. It's not so much the hole-by-hole part of that. It's more about understanding that linear regression equation to manage that vibration.
Excellent. Scott, thank you very much. One last question. I don't see any other questions from the audience live. And it's a comment first to say, since you and I have been quite slow in adopting technology over the years, how long do you think we will see widespread? It will take to see widespread adoption of new blasting tech.
I can tell you, every time new technology comes out, it's sometimes glacial. I mean, non-electrics was pretty rapid. It was widely adapted very quickly. I was a salesman at that time, and I mean, it wiped out my electric detonator sales just like that. And I was like, man, why can't we have that? Well, somebody said, oh, that's patented technology, and we can't do that. So we were in a blind spot for a long time until that patent wore off. Electronic initiation. I know there's some procurement people in the room, and the focus tends to be on cost per unit. They go, good God, an electronic initiator costs 5 times as much as a non-electric. That's true. No denying it. The thing is that you've got to do the solutions part of that to understand that the value electronic initiation brings to your operation versus firing non-electrics. And sometimes that economic analysis doesn't pan out, and it's just better to stay with non-electrics. But a lot of times, especially if you're doing some type of milling, you want to have that added control over your fragmentation distribution.
Perfect. Thank you. Thank you, Scott. Another round of applause for Scott. Right, up next, from chemistry to case studies, she's the emulsion expert. Dr. Raki holds a PhD degree in organic chemistry with over 20 years of extensive experience in the explosives industry. Over the years, she has successfully developed numerous emulsion-based products, guiding them from concept phase to full-scale industrialization. Her exemplary work has presented BME with a distinctive market position and a competitive edge. She currently holds the role of Global Manager Strategic Partnerships for BME. Let's welcome Dr. Raki Pathak, who will show us why BME emulsions are truly worth their salts through her paper, Secular Thinking, Elevating Sustainability from Initiative to Imperative. Welcome, Raki.
All right. Good morning, everyone. Welcome to the world of emulsions, where oil and water finally get along. Today, we will dive into the world of emulsions, the fascinating chemistry of making oil and water mix. It's a magic. I'm pleased to share some of the latest BME emulsion technology solutions. These innovations are helping us work safely, more efficiently, and deliver better results. I'm excited to show you how they can support our industry and help us move forward. Toxic gases, as you know, nitrogen dioxide, present a serious health risk to the surrounding communities. As public and regulatory pressure grows, there is an increasing demand for cleaner, more sustainable blasting solutions that can minimize environmental and health impacts. Reactive ground. Reactive ground condition can be a major challenge in mining. When certain rock types come in contact with explosives, they trigger unwanted chemical reaction. This can lead to safety risks and poor blast outcomes. It's important to use emulsion products that are stable and designed to perform safely in reactive ground conditions. Here, I'm showcasing some of the examples where we encountered a highly reactive ground, where, as you can see, the reaction, there was an extreme reaction when the rock came in contact with an emulsion. There were extreme reaction, fumes. So this is a real challenge in the mining industry. Another challenge that we have to deal with on a day-to-day basis is the improper handling of used oil, as improper handling of the used oil can harm the soil and the water. This creates environmental risks and can lead to non-compliance. Effective management is crucial in preventing pollution and protecting the environment. BME pioneered cold emulsion technology in the South Africa open cast mine almost 40 years ago. It improved the safety, the reliability, and the blasting efficiency. It's boosted the productivity and reduced operational cost. Sustainability is a core part of our product design. We use high levels of waste oil in our bulk emulsions. This reflects our strong commitment to sustainable mining practices. Let's quickly discuss about what is the basis of an emulsion. What is an emulsion? What's a water in oil emulsion? How we can use an emulsion in our blasting practices to get the desired results. An emulsion is a water in oil mixture containing supersaturated solutions of ammonium nitrate and calcium nitrate suspended in oil. So finally, we found a solution where we can bring water and oil together. They are getting along, stabilized by an emulsifier. So we, in BME, we have our own emulsifier technology. We develop customized emulsifiers. We have a production facility where we can customize the emulsifier to deliver results to meet any challenging blasting conditions. So an emulsion is basically a mixture of a nitrate. In our case, we use unique chemistry of dual salts, ammonium nitrate and calcium nitrate, blended with a blend of different fuels. We introduce a high levels of used oil, blended with an emulsifier to form an emulsion explosives. Sensitization is done by means of introducing the gas bubbles, by chemical gassing, or by microballoons. This chemistry creates the hotspots, allow the emulsion to detonate when initiated. Sensitization ensures that control energy is released, improving results, precision, and safety. What are some of the key factors that can affect emulsion stability and shelf life? A raw material. Because it's a very delicate chemistry, where we bringing two different immiscible liquids together by means of a chemical reaction, we have to be very clear about the raw material quality. So raw material quality is the key. The emulsifier structure, the oil composition, the impurities, the properties of the used oil. As you can all appreciate that no two batches of the used oil are the same. Each batch of used oil has to go through a series of stringent tests to meet our internal specification, to make sure we deliver the product that meets the customer requirements. Another factor to consider here is the phase ratio, the oil to water ratio, the HLB values, hydrophilic, lipophilic balance. We have to make sure that we're using the correct emulsifier, we're using the correct quantities, and even the introduction of the emulsifier is critical, how we introduce it to make a final product. There are a number of factors that can affect the stability. Ammonium nitrate crystallization. If our raw material crystallizes, or there is a coalescence, or there is an imbalance in the pH ratios, it can severely impact the emulsion stability. There are a number of stability mechanisms that we use: interfacial tension, strength of the interfacial film, and the droplet size distributions. There are a number of other factors that play into the emulsion chemistry. To name a few is the structural properties, how the nitrates interact with the fuel, how the nitrates interact with the emulsifier, the rheological properties, the nitrate content, and extreme operating conditions, transportation conditions, pumping conditions. So there are a number of factors that we have to consider to deliver an excellent batch of emulsion. Let me just briefly touch on the fundamental differences between a traditional single salt and a double salt, and why we as BME opted for a dual salt technology. A single salt emulsion is basically a supersaturated aqueous ammonium nitrate solution mixed with a fuel. It uses a very high manufacturing temperature, around 85 degrees. It's very susceptible to crystallization and can have a seeding point that can lead to emulsion stability. While on the other hand, our unique dual salt emulsion technology. Our dual salt emulsion is basically an emulsified ammonium nitrate and calcium nitrate mixture mixed with a blend of fuels. It can be manufactured at much lower temperature, at 65 degrees. It has a low congealing point, a low crystallization point, or a fudge point, as we call it, and it can be detonatable at higher density and in smaller diameter. So dual salt emulsions offer unique technology, offer unique solution, those who are energy efficient, and offer better blasting results. So as I mentioned in the beginning of my presentation, the post-blast fumes, as we call it, NOx fumes. So what are NOx fumes, and why do we experience NOx fumes event? Under ideal conditions, ammonium nitrate detonation can produce nitrogen, carbon dioxide, and water. But with incomplete detonation, the same ammonium nitrate can produce NOx fumes. As you can see on the screen, there are different levels of NOx fumes. A kilogram of ammonium nitrate, if not used correctly, can generate over 110 liters of NOx fumes. So it's massive. It's critical that we use our emulsion chemistry properly. So poor oxygen balance basically leads to poor NOx fumes. It generates a high level of NOx. Under ideal condition, the detonation of ammonium nitrates, like I mentioned, gives harmless gases. But if the emulsion system has negative oxygen balance, it can lead to carbon monoxide. On the other hand, if the system has positive oxygen balance, that means it has excess oxidizer, it can create NOx fumes. The differential in the oxygen content between ammonium nitrate and calcium nitrate is minimal. It's so insignificant. It's 1.43%. While on the other hand, CN provides twice the amount of oxygen as compared to a traditional ammonium nitrate, making it more oxygen balanced. If the system is more oxygen balanced, it leads to less fumes. Thus, our dual salt emulsion offers superior oxygen blasting solutions as compared to the traditional single salt emulsions. It offers enhanced stability and reduction in the NOx fumes. I would like to now share with you some of the case studies and the examples where we have successfully used dual salt emulsion to deal with many challenging operational conditions. The first example, where we use bulk emulsion for extreme conditions, are Innovex HE, high energy emulsion. Our product had to go through a number of pumping cycles, through a series of operational conditions to deliver the blast results. So the emulsion had to remain chemically stable during a 1,700-kilometer road journey and a prolonged sea voyage. The site was 2,200 kilometers away from Namibia. So just imagine the emulsion had to endure prolonged transportation conditions, extreme operating conditions, pumping conditions, prolonged sleep times, and still deliver the results. The product needed to withstand repeating pumping cycles. It needed to deal with the variable ambient conditions we developed a robust emulsion formulation to ensure that consistent product was delivered. So basically, in this case, we took on a challenge where we delivered the emulsion over a 2-year period. On an average, 200 tons of emulsion was delivered on a monthly basis. A total of 4,000 tons of emulsion was used. Emulsion endured extended transportation time, longer sleep time. Product performed well and offered the desired results. We're very, very proud of our achievement. It's an excellent example where we took on the challenge, we did a lot of lab work, developed a new system, developed a number of testing protocols to deliver the results. Another example, second one is mechanized solution, our Innovex 300D. It's a patented technology. The emulsion offers enhanced resistance to dynamic water. We all deal with dynamic water challenges in mining. So this is the product that we developed to deal with dynamic water challenges. It reduces nitrate leaching. It prevents the emulsion runoff. It helps in reducing the free ammonia. It reduces nitrate leaching. And the emulsion is manufactured on the mobile manufacturing unit with real-time rheology control. We had a challenge where the product had to be used in the blast holes with sleeving. It created a contamination risk where foreign materials in blasted fragments increase the diamond loss. So with our Innovex 300D, we were able to reduce the top-up emulsion runaway by 66%. Our homogeneous product with a high level of rheological properties, it provided higher VOD results. There was a significant reduction in the plant downtime. There was a reduction, eliminated the plastic sleeving blockages, and it minimized the environmental impact by reducing the plastic waste. So here's another example where BME has innovated another emulsion technology solution to deal with certain mining challenges. Dynamic water is a very common challenge that we deal with, but very little solution available to deal with high dynamic water challenges, friable rock, and other.
This is dynamic water. Yeah. You're taking it like a fish.
Besides dealing with dynamic water challenges, our product offered better fragmentation results as well. As you can see on the screen, there's a huge improvement in fragmentation results. Another example that I would like to share with you is the reactive ground technology, our innovative Innovex RG technology. We had to deal with reactive ground challenges where when the standard product was used with the reactive ground, there was extreme reaction with the reactive ground. And as you can see on the screen, we've seen a number of holes showing the category of 6 where exothermic reaction exceeded more than 200 degrees. There were other exothermic reaction encountered. So we had to develop, again, another product to deal with a very dangerous reactive ground condition. Another example that I would like to share with you is our sustainable blasting solution, leveraging recycled oil. As I mentioned, that BME has been using used oil since 1980. We've been using very high levels of used oil in our bulk emulsion. We look at a reduction of the waste, convert used oil into valuable input, cutting hazardous waste. It supports our ESG alignment. It supports environmental, social, and government's goal. And it also helps in the reduction of costs. Sustainable waste oil management system, our used oil recycling loop. So we collect used oil from various sources. As I mentioned earlier, no two batches are the same. We collect the used oil is then processed at our processing plant to remove the impurities. The refined oil is then blended for use in our bulk emulsion. BME, on an average, consumes 30 million liters of used oil annually, supporting circular economy principles and reducing environmental impact. In summary, BME's sustainable emulsion technology systems offer customized, stable emulsions for tough mining conditions. We support ESG goals through responsible design and waste use. We help reduce NOx fumes, improve air quality and safety. We lower carbon footprint via energy efficiency and recycled content. So in summary, at the heart of every efficient blast lies carefully engineered emulsion designed for consistency, safety, and sustainability. Thank you. Thank you for your time.
Thank you, Raki. That was very insightful. I learned today that there is more uses to salt than just seasoning my food. All right, we've got 3 questions on the app, but before we go there, are there any questions on the floor? No, okay. We'll quickly maybe just take 2. There's quite a few questions. We'll just take 2 because we are running behind schedule. The first one is, what is the future of dual salt emulsion with the introduction of hydrogen peroxide emulsions?
Thank you for that question. Emulsion explosives, they've been around for, like I said, for more than 50 years. But we have evolved. The emulsions have evolved. The technology has evolved. There'll always be a place for emulsion explosives to deliver better results, better outcome, better meet sustainability goals. So I strongly believe there's so much that we can actually do with the used oil technology to deliver the results that we all desire.
Okay. The next one is, what breaks down the explosives pumped in the hole, resulting in a poor blast? I always hear that it is due to ground that reacts, not reactive ground.
Thank you. Interesting question. I think I touched on it because an emulsion, dual salt emulsion technology, it's very unique. It's very different. You're actually bringing the 2 immiscible liquids together by means of a chemical called an emulsifier. So there are a number of factors, like I touched previously, that you have to deal with in terms of making sure the emulsion is highly stable, it has an extended shelf life, it's highly robust, and it can deal with any extreme operating conditions. So how do we ensure that our emulsion is of top quality? We make sure our input raw materials go through, again, a series of tests, so they meet our stringent internal specifications. We make sure the production process is done correctly. There's a consistency in the product. And we also make sure that our emulsion is designed. So it's all in the design, that it's designed to perform to the required conditions. So yes, to answer your question, there are a number of factors that can affect emulsion stability. Pumping, extreme pumping conditions, temperature, handling, soil conditions, equipments. But if we have a highly stable, robust emulsion that is designed to deal with, it can give you the desired results. And we've seen over and over that our emulsion, it can withstand months of sleep time, transportation, pumping multiple cycles, extreme transportation conditions, pumping conditions, and it can still deliver the desired outcome.
Thank you, Raki.
Thank you.
All right.
So we're gonna jump right in, and I'm gonna ask Nishan Haripasad to join me up here on the stage. Unfortunately, our next speaker, Ravi Sahu, could not make it. Some logistical challenges. So we're gonna talk that other thing, AI, now for a short while. As Ravi was the author of the paper, I'm just going to introduce you to him. It's his work. He would have been our next speaker. He is the founder of Straios, bringing us auditable AI and digital twins. Ravi is the founder and CEO of Straios, a computer vision and AI software company that combines remote sensing and 3D drone data analytics to deliver mind-to-mill AI solutions. Ravi has worked for Fortune 500 companies, leading large-scale projects and products, and holds an MBA. His technology is deployed in over 2,000 mines. And we're not going to welcome Ravi, but to just summarize his paper for us, I'm going to welcome our own internal AI specialist, Mr. Nishan Haripasad. Nishan, let's welcome Nishan to the stage. Thank you.
Thank you, Dirk. Appreciate the intro. Not sure about the specialist bit, but I'm going to give it a shot. So, before I start, we opened this morning, and Ralph mentioned that this summit is not just about BME, BME's products, what we have, what our service and what our offers are. Yes, we'll use the opportunity to do a bit of marketing. Why not, right? But as Ravi was intended to be our first international guest speaker today, it's to showcase the developments taking place in the industry and what benefits these developments are providing, and not just to blasting, but to mining in general. And the Straios solution set talks to AI influence across the mining value chain, across from the very first, from the time you drill the hole till the time you blast, to load the hole, till blasting, crushing, all the way down to yield optimization in your throughput. So yeah, so fortunately, obviously I'm not Ravi, right? So I won't do this presentation any justice. Fortunately for us, he's given us his content that we'll talk through today. Unfortunately for you, I'll be the one presenting it. In the world of Straios, the future isn't just about gathering data. Future is about using that data to create a fully connected, autonomous, and auditable system, with emphasis on auditable. A system that uses a closed loop from the second we break ground to the final product delivered to the plant. And that's where integrity first autonomy comes in. It's not just a technical concept, it's a shift in mindset, and it's about building AI that doesn't just work, but works with traceability, safety, and explainability at its core. And the goal is, it's a goal we all seek for, safer walls, steadier feed, lower energy per ton. So the definition of integrity-first AI talks to being auditable, like I mentioned, being explainable, and having the governance structures as well to ensure that it operates within the right boundaries. Shreyas's solution set brings this vision to life by linking every stage of the mining value chain, be it drilling, blasting, hauling, crushing, into one intelligent loop. And this is done not through a couple of presentations or through any hype or shortcuts, but largely through real, tested, and operating solution sets at operating mines. As Dirk mentioned, Shreyas is available in a couple of thousand mines. The number is actually around 5,000, not 2,000. So there's numerous test cases to show the validity, the effectiveness of the AI solution set. So this presentation today, we're going to dive in and explore how computer vision, digital twins, control logic all come together into a smart, connected, and most importantly, auditable system, and is a mechanism of how Shreyas uses it to future-proof mining in their world. In their world and in our world. Sorry, jumped ahead a bit there. So, for the past decade, we focused on digitization. We have elements of digital works in our mines, in our businesses, whether you're a service provider, you're a blasting provider, you're a drilling provider, you're an operating mine. So effectively, the industry is data-rich. But this data, and we know this data lives in silos. We're not connected to every system. The geology model doesn't talk to the blast design in real time. Blast results aren't automatically feeding the plant's control system. And this disconnect means that we are constantly reacting. So more data has not solved our core challenges. It has just given us more to manage. Right? We have the data, we see the data. Sometimes we do not know what to do with that data. Right? And that creates the complexity in our lives. Right? We're at a point where data is everywhere, but the value is not. Many mines already have modern sensors, they have telematics, software embedded in their systems, and yet critical decisions are still made offline. And based on information we get from what we see on the ground, not what we read on the ground, through tangible data. And that's where the closed-loop AI makes the difference. Instead of static dashboards, it creates living ecosystems that observe, that learn, and adjust. This isn't just optimization. This isn't just automation. It's a self-correcting feedback loop that continuously improves safety, productivity, and quality. With today's technology that's available today, not tomorrow, we don't have to wait. We can empower ourselves with edge computing, ruggedized sensors, scalable models, and all of these mean that we can start closing loops right now, linking what happens in the pit with what's needed in the plant. This entire system, and the system that Shreyas has developed, has been built on one foundation, a single source of truth. We call it the live digital twin. It's not a static map that's outdated in a week. It's a live 3D model of your site fed by data from your drones, from sensors every single day that your site's operating. You cannot have autonomy without a perfect real-time understanding of your environment. That's where the data comes in. Traditionally, mining stages, from planning to processing, have been optimized in isolation. The Strayos solution set changes that. It integrates the entire cycle from pit to plant through one intelligent feedback system by stitching together photogrammetry, blast models, muck pile dynamics, real-time plant monitoring, and enables each stage to inform the next. What happens at the shovel impacts the mill, and vice versa. This connected view helps reduce energy waste, prevent rework, reduce waste, and increase throughput. It's not just about data visibility, it's about data that acts across the full loop. In safety, critical domains like mining, black box AI, exist that generally can't be trusted. That's why Strayos, or the Strayos solution set, has prioritized transparency and auditability from the start. Every model or every model output includes traceable reasoning, whether it's in a drill hole, occurring in a shift, explosive loading through tweaking. We all do this sometimes. Users can inspect why the system makes that recommendation on what data it uses and what alternatives can be considered. This means engineers stay in control. It satisfies governance, compliance, and regulatory requirements, which are essential for scaling AI, essential for scaling AI use across fleets and across sites. So we know that every single blast begins with a detailed understanding of the bench. So visual inspections and assumptions are not enough. The days of the thumb have passed. And with Strayos solutions, drones can scan the bench to produce 3D photogrammetry models. AI then analyzes these to detect joint planes, bedding seams, and facet orientations automatically. This enables safety or safer and more efficient drilling. Engineers can adjust hole placement, depth, and angle based on actual rock structures, not just standard spacing rules. It's precision geology at production speed, which is what this technology provides. And drilling isn't just about reaching the right depth. It's about understanding the rock you're cutting through. The Strayos solution set integrates with smart drills to analyze real-time pressure, penetration rate, and feed metrics. This lets our engineers see through rock strength zone by zone, identify weak spots, determine competent zones, all of which you will know what to do and when to do before you load. These insights power better geotechnical decisions, from explosive type to hole depth and stemming zones. Everything becomes more precise. And this is based on the real data that the Strayos solution set extracts and provides, and not on assumptions. Now, we all know, and this happens often, blast performance is often blamed on the crew. But it starts with the design. The Strayos AI platform analyzes rock mass data to predict blast behavior and recommend precise loading plans. This includes, obviously, the actual explosive product to use, the type, the charge length, stemming material, length of stemming, all tailored to that specific geotechnical profile. And by avoiding overloading near soft zones or underloading competent rock, fragmentation becomes more uniform, an imperative we all are targeting. The result is smoother muck piles, safer benches, and less work downstream, doing more with what you have by changing how you do it and apply it. Yeah. With this digital twin, the AI solution set can now sense the ground truth, if it can be framed that way. The Strayos computer vision scans the high wall to identify every joint, every fault, and every change in rock strata. Data from your smart drills tells it precisely how hard the rock is at every point before a single hole can be loaded. We have a complete data-driven this provides a complete data-driven picture of the bench. And understanding what happens after the blast is also just as important as the blast, as the blast itself. Or where does the ore go? What gets mixed? What's recoverable? Strayos Solution Set offers a solution that tackles this with digital twin modeling. The system combines physics simulation and AI to create pre- and post-blast muck pile models colored by predicted ore content, which allows for rapid adjustments to digging strategies, improvements in blast designs, and optimizing of product. These allow for a reduction in dilution, improvements in recovery, and the better use of your ore data before a single shovel moves rock. Now, once that blast is done, the real movement begins. Strayos Solutions offering includes software that can monitor and optimize that movement. So each loader operation is GPS tagged and linked to a specific shot. So you know downstream system, what this does, it allows downstream systems to understand exactly what material came from where. And if ore zones were predicted in the digital twin, they're now actionable in the field. What this also does is it supports detection of oversized rocks and quality variance during loading, which ensures higher grade material reaches the plant as designed to, and problem loads are flagged up front before processing even begins. And this is, in terms of the solution set that Strayos provides, this is the final and most critical link. The placement of 3D vision sensors directly over conveyor belts these sensors allow for every rock moving in the plant to be scanned 24/7. So for the first time, the plant knows the exact size of material it's receiving before it hits the crusher. We know that a single oversized boulder can choke a crusher. Fines can overload screens. Yet most systems only detect problems after the fact. It's a challenge we all face with every day. Within the basket of goods that Strayos offers is a tool called Netra AI. And this solves that challenge by monitoring every rock in real time. 3D cameras capture size, shape, and density as material flows through to the crusher. Edge AI, another solution set, processes it instantly, alerting operators or allowing them to adjust plant settings incrementally or automatically, depending on the setup you have. Now, this not only protects the equipment, it informs upstream changes. And when you know which blast produced what fragmentation, you can adapt your designs to close the loop on performance. Now, we also know that not all rock is equal. But we also know that most plants treat it that way. What we have within the Strayos solution set is the introduction of hyperspectral imaging, which can fix that. These are mounted over conveyors or haul trucks, depending on your likeness. And these HSI systems capture full spectrum light from each passing rock, thereby analyzing it in real time. This enables ore grade classification before the material reaches the mill. Now, I'm sure you're thinking the benefits of that in terms of maintenance, planning, can be quantifiable and can be measurable. We need to do that. And the systems now exist for us to enable that. Through this HSI system, high-grade ore stays in the process, while waste or diluted zones can be rerouted. It's non-contact, it's extremely fast, and it's a game changer for energy savings and recovery rates at any mine. And with that, the loop is closed. The real-time fragmentation data from the belt is fed all the way back to the blast design software. The AI now knows the entire story, from geology to blast, to fragmentation to mill performance. And if the plant sees the poor results, the next blast design is automatically adjusted with the AI code. The system then learns and optimizes itself. Right? So disconnected systems create waste. Integrated systems create insight. That's what the value of data and the value of intelligent data coming from AI systems provide. Now, with the solution offer that we have with Strayos and the collaboration that BME has with them, each shot, load, and crusher run is part of a unified data set. Right? GPS tagging, time stamping, linked haul cycles, or link haul cycles all back to the origin, giving operators visibility into how design decisions affect plant outcomes. Over time, as the AI model learns, this allows pattern optimization based on yield, not just prediction, and that's how mine-to-mill integration comes about, right? And becomes a source of competitive advantage through integrated systems like these. This, therefore, brings us the mine-to-mill loop. It's a simple concept we all know. How we blast rock impacts how we load it. How we load it impacts how we crush it. And for decades, these have been treated as separate departments. An inefficient blast in the pit creates massive energy costs in the plant, and the Strayos solution set with its AI-enabled software and its insights is designed to connect them. Now, across a range of mining environments, these have been deployed, be it in quarries, be it in metal mines or aggregates. Strayos has already seen measurable performance gains. These aren't theoretical anymore. These aren't just textbook theory. These are from sites using actual Strayos dataset today, or technologies today. Whether it's a 7% throughput boost at the crusher, or an 8% cut in ore loss from smarter blasting, the gains are real and now repeatable. That's the impact of closing the loop. Now, there's a big difference between automation and autonomy. Automation follows rules. Autonomy makes decisions. Strayos builds autonomy into each part of the mining process. And AI models simulate and predict outcomes, and then adapt these based on what actually happens in the field. These digital twins create a loop of continuous learning, but doesn't replace people. Instead, it empowers people. Engineers remain in control with full visibility into how and why the system acts. This is what we talk about when we say autonomy with integrity. We still maintain, as we started the session today, safety is not optional. And it's also engineered into every one of Strayos' systems. The autonomy framework includes defined safety zones or safety envelopes, ensuring that no system operates outside approved zones or configurations. And every AI-driven adjustment is tracked with a justification log, forming a reliable and auditable trail. The system provides the answer. Every decision is logged. A manager can pull a complete audit trail, and you can see exact geology data that led to a blast design. You can see the measured fragmentation from the blast X that design. And you can see how Merle's energy use changed as a result. This traceability is what builds trust. And models also forecast structural risks like high wall instability and vibration impact before they occur, which provide our operators with foresight to act. And that there is the autonomy with the governance. Trust in autonomy comes with transparency, and every AI-driven decision in the Strayos system is logged clearly, consistently, contextually, automatically. Whether it's the drill design change or a crusher setting adjustment, engineers can trace what triggered the decision and what the data is based on. Autonomy must also operate with strict or within strict boundaries. And these are what the system calls safety envelopes. You set the rules. The AI can suggest the variations, but it cannot violate your company's maximum grades or intentions. In fact, the AI acts, or the solution set with Strayos, acts as a 24/7 compliance officer, constantly scanning live twin for risks like a missing berm or a scope or a slope that is becoming unstable, and alerts your team or the teams managing the system. It doesn't just satisfy regulatory concerns or needs, it forms a foundation for improvement and using past decisions to inform future training and tune performance. Now, I know that with cloud-based systems and with the increased adoption of AI systems, it raises the question on data privacy. So how does AI get smart? Well, it learns from multiple sites, but your operational data is your own. And the system has built-in intelligence to share the intelligence, not the data, so the learnings from that data. So your data never leaves your site. And the AI learns from it locally, and only the mathematical improvements from the AI model then are sent to the central model. So everyone in this case benefits from a smarter system, and everyone's data stays private. We know that mining companies value privacy, and especially when it comes to ore bodies and operational data and process configurations, the solution set via Streos respects that and has embedded knowledge around that. Right? So whatever IP is shared, there's no compromise of security or data from the intelligence network. Right? So that's what Streos has developed and is an evolution. An evolution in the industry that didn't just happen overnight. Today, the system, as I mentioned, operates in over 5,000 sites globally. Its tools assist engineers, giving them better data, allowing them to make better decisions. And as the system learns, it will begin to augment operations, suggesting optimizations, and optimization that we have not seen, or optimizations that have been benefited or learned at other operations, that feeds into the learning model and manages the loop, which allows you the benefit of freeing up your best people from day-to-day firefighting to focus on the next big challenge. So the path to autonomous mining isn't leap. It's a series of well-planned steps. And with the Streos solution set, mines can start small, one feedback loop at a time. And as confidence grows, so does capability, which is what begins with a smarter blast and can evolve into a fully optimized mine-to-mill ecosystem. At every stage, integrity comes first, ensuring decisions are transparent, accountable, and aligned with human oversight. And that's how Streos has built in the logic that it would build the future that mines can trust. Now, BME has partnered with Streos, and there are a series of solution models, all AI-enabled, that can deliver on that which I've spoken to together. We've branded it for our business Explore Smart. It's being showcased today in one of the breakout rooms, and it would serve you well to spend some time to look at that. Because whether it's called Streos or whether it's called Explore Smart, this is more than just technology talk. It's a call to rethink how mining is done. And integrity-first autonomy means building systems that serve people, not replace them. It means scaling smart, staying transparent, and sharing intelligence responsibly. And these aren't just ideals, they're operational principles that are already working at scale. So the future is integrity-first autonomy. I'm going to park it there. I'm pretty sure I didn't do the summary justice, but yeah, so if there's any questions, I'd love to say, ask now, but we're going to have a bit of a problem with answering that. But yeah, please feel free to put your questions on the app, and we will surely get around to do that.
Excellent.
Okay.
Thank you very much. And yeah, quite a comprehensive summary. Thank you very much. I was going to ask you if the folks at Streos can help me do some predictive work around my two teenage boys, but and I won't go deeper into the marriage. But we had a question around the usage of the system underground.
Yeah.
Do you have any background on that, or knowledge of any future plans?
Yeah, the system is not independently designed for surface systems, surface mines. It's already embedded in a host of underground mines. I would say over, if my memory serves me, I think it's over 1,000, 1,032 or so. Could be wrong. But yes, the solution set can be used independently, or you could use integrated loops per system, as opposed to the complete suite of offers. So if you want a solution set for underground prediction, underground benefits, underground advanced benefits, closed loop integrated solutions, there are solution sets within the Explo Smart and Strayos umbrella of goods that can talk to that. So 100%, yeah. So the answer is yes.
Short answer is yes, fantastic.
Yeah.
And then maybe one more. I see there's a few questions, so thank you very much for warming up to the app and putting your questions down there. And I think it's got to do with the onboarding of this type of technology, and it refers to, training data specifically. So could you perhaps elaborate a bit on how, that would work? Does the system come with its own set of data for training purposes, or how would the system onboard and enable customers?
So one of the benefits of partnering with Strayos for BME is that Strayos is operating globally, be it in Europe, be in the US, Australia, Middle East, Africa, Asia. There is a support network that's available that effectively serves as a 24/7 support loop. So you might have a challenge today with your fragmentation or your software outcome, and today it would be someone in Chinese that picks up the phone, in China that picks up the phone, or it could be someone in Australia that picks up the phone, depending on what time you log your call. All right, so yes, the system is designed with a training model built in, as well as the partnership with BME allows us to deliver hands-on field-based training as well. So we will empower you with the intelligence and the education on how it works, why it works, and why it does what it does. So yes, fully built-in, and that's the model that BME adopts. We hold our hands with our partners. It's not about putting a product on the ground and say, Bob's your uncle, run with it. That's not what we do. We want to see you succeed, and with any system that's embedded or developed or deployed, a full-on training model exists, and the benefit you have is if you can't get a hold of a BME person, you might get a hold of a Strayos person that's speaking in Mandarin, but you'll get your answer.
Fantastic. Thank you. Thank you, Nishan.
Cool.
With that, I hand over back to Lungi. Lungi is going to introduce our next international speaker.
We hear from a pioneer in sustainable explosives. He's making mining greener, literally. Thomas Gustafsson is the CEO and co-founder of Hypex Bioexplosives Technology, a Swedish company pioneering sustainable solutions in the commercial explosives industry. Thomas has been instrumental in developing biodegradable hydrogen peroxide-based explosives as a safer, greener alternative to traditional ammonium nitrate explosives. His work has positioned Hypex Bio as a key player in the global transition towards environmentally responsible blasting practices, with successful pilot projects and CE-approved technologies now being rolled out across Scandinavia and Europe. Please welcome Thomas Gustafsson, who will be talking to us about moving mountains with innovation.
Thank you so much for that. I like this picture. It's a picture from the largest open pit in Europe. It's operated by Boliden Minerals. It's a copper mine, and I took this picture last year. It was sub-zero, 33 degrees, and we had issues with our car. Our diesel didn't really flow as it's supposed. But this is the environment I come from. 7 years ago, we started an innovation project. An innovation project that was spawned based on the insights and feedback working for global mining industries with explosives. And the feedback was normally concerns about the results of using nitrate-based explosives. It was everything from toxic gases, re-entry times, nitrate leaching, ammonia in the working environment, to crystallization issues, supply chain vulnerability, and so on and so forth. And we had this idea that we could do something about this. So we have about 20 years of experience in developing and dealing with explosives on everything from initiation systems to bulk systems. And we thought maybe we can do something holistic. It took us about a year in the laboratory to figure out that we could replace ammonium nitrate with hydrogen peroxide. And for those who doesn't know what hydrogen peroxide is, it's like water, but with an extra oxygen molecule. We can use that oxygen molecule to propel a detonation process, and thereby, in principle, developing a completely nitrate-free explosive. And during that year in the laboratory, we managed to develop a stable hydrogen peroxide-based emulsion. An emulsion that exhibit very similar characteristics, like an ammonium nitrate emulsion. We could gas it chemically and so on and so forth, but it was a lab product. It took us an additional 3 years trialing and testing further the technology in a real mining environment, also with Boliden Minerals, to ensure that we could adhere to their strict requirements on safety, performance, non-disruptiveness in the applicational layer, supply chain reliability, manufacturing, all of these things. So in 3 years, we built a pilot plant, we trialed it, we worked with their production teams, we would start pulling our blasts. Myself, I lived in that mine. We pulled 14 blasts a week for 3 months, and we outperformed their existing blast teams, and we did it without the NOx gas, and we did it without the nitrate leaching. It took us an additional 3 years to take the business and the company to where we are now, in a mature state. We would roll this out through Scandinavia into Northern Europe. We have built a technology platform around this. We still have far to go, but we have mature technology, and we've proven our statements. I'm going to show you some of that data today. And the reason I'm in South Africa today is that I'm also here as a partner to BME, and through this partnership, we're going to take this technology to the Southern African market, and together with yourselves, prove that we can not only achieve sustainability, we can also improve your operations, we can improve your cycle times, and perhaps also mitigate nitrate leaching and ammonia risks. So, let's start with some context. Top down. Global society depends on mining for a simple reason. Mining produces the metals and minerals we need for modern society. Very simple. Mining is not going away. The way we mine is by using the most energy-effective way to extract rock. And to my knowledge, the best way to do that is to use explosives. Explosives are here to stay. Technologies that we have today were developed in 50s, 60s, and 70s. I think you got a very good run through here of Scott previously, but it's principally the same technologies. We have done migration from amphos to emulsions and so on and so forth, but we're still using the same technology paradigm. We're using the nitrate salts as oxygen carriers to propel a detonation process. And we have learned throughout these years to mitigate the issues, to deal with them, to work around them, but we have never truly address the problem, the root cause. And the root cause is the nitrate salts. So I say here, maybe a little provocatively, I say that it's a dire need of innovation. We have done incremental innovation over the years, but I think we have reached maximum maturity of the nitrate paradigm technology. We need a new step, a new paradigm. It's always best to start to try to define the problem before you solve it. And from my perspective, I think most relevant is the left column here. But we also have other things that are relevant in Europe and in this region. But predominantly from an operational perspective, issues such as toxic post-blast detonation gases, nitrate emissions, and ammonia environments underground, NOx clouds affecting local communities, crystallization, and so on and so forth are maybe the most important things from an explosive perspective affecting your operations and your bottom line. To my knowledge, the majority of mining houses today have an emission and sustainability agenda. And when I say sustainability, I mean emission sustainability. We're going to come back to that. It's a little bit of a, let's say, challenged word at the moment, but we're going to come back to that. But we can do a lot in that space. And I think also worthwhile to mention is the dependence of one single technology platform to run our operations. We are dependent on the ammonium nitrate and the calcium nitrate supply chain. If there's disruptions in those supply chains, we have no alternative. And I think from a safety and security of supply chain perspective, I think we need redundant technology. So this is the problem statements that we're trying to address. So back to our innovation project, by looking at these issues, we figured that hydrogen peroxide will address all of these issues. By removing the nitrates from the base compositions, we will not be able to generate NOx gases, we will not be able to generate ammonia. And hydrogen peroxide decomposes naturally to water and oxygen, so even if you have waste product, if you have spillage on your ground, it will naturally decompose to water and oxygen. That was the theory, now I have the proof. I'll show you later. In Europe, at least, we can produce hydrogen peroxide in a completely clean process. It's more energy effective to produce compared to ammonium nitrate, and by using hydroelectric power in Norway, in our case, we can produce a product that is completely carbon-free. In Europe, we can achieve up to 90% Scope 3 emission savings by shifting to Hypex Bio from A&E. And in Europe, we have multiple production facilities producing hydrogen peroxide, whereas when it comes to ammonium nitrate, we have one. So substantial challenges here, which we're trying to address. So over these years we have done this, it's become very evident that we're the first one to do this. There's no support in the world to do this. No support on the chemistry side, there's no support on the processing side. So we worked very hard to package this technology into a platform. It encompasses the chemistry, the emulsions, the sensitization systems, and other chemistry that goes around with that. It implies building and designing high-capacity manufacturing plants and delivery systems, your MEMUs, your underground charging units. And the reason we're doing this is we're striving very, very hard to minimize the transition, the cost of transition to our technology. Today, you can charge Hypex Bio the same way you charge A&E. Chemical gassing looks very similar. You don't have to change your drill patterns. You don't have to change your timings or your detonators or your boosters. You shift the product, that's it, and you achieve these benefits. I should say that this is in a Scandinavian context, and being on the other side of the planet, things might be different here, but together with BME, I'm sure we can overcome those differences. And of course, being new technologies and being first, it also means that we need to support our customers in this transition. So we have developed a very comprehensive training, support scheme, and servicing scheme to ensure smooth transitions into new customers. When we detonate hydrogen peroxide emulsions, the predominant gas we get is water. Our emulsions today comprises of up to 46% water. And if you were to acquire an ammonium nitrate emulsion with 46% water, you would be skeptic of the performance. But with this product, we can achieve fairly good results. In this case, this is a project we're running with a limestone group in, see if I can get this to go, in Europe in order to minimize fines and minimize movement. This is a density of 0.7. It's a bench height of 18 meters, and we do these blasts about 2 times a week. It's 12 tons of emulsion, and this is water steam breaking this rock, 0 nitrates. I'm going to show you some more videos down the line. We are partnering with the biggest mining company in Europe called Boliden Mines. We are on a roadmap to roll this out at scale for 2 reasons. The first reason is operational efficiencies due to re-entry and nitrate mitigation. It just makes sense for them. They make money by shifting. The second reason is to achieve sustainability goals. They have figured out that one of the most cost-effective ways to achieve the sustainability goals is to shift explosives, in contrast to other things. This is a picture of one of our operational plants, which we have in the Boliden area, up in Sweden, to supply 3 of Boliden's mines. Okay. So this is a technical conference. It's not supposed to be marketing, I was told. So I'm going to show you some data. I'm going to try to do this as effectively as I can. This data was collected as a part of a commercial project in Stockholm. We were driving 2 tunnel phases for train tunnels in Stockholm. One phase was developed with ammonium nitrate emulsion, and one was developed with our technology. And it was the first time we did this in an infrastructure project. Fairly big phases, 86 square meter phases. We drilled 6 meters, and we measured everything. But this data is most interesting because when we started the project, 100% of the brothing was done with ammonium nitrate emulsions. And we measured the nitrate content in the pit water closest to the phase. And in the beginning, we can see that we had fairly high nitrates. And this is aggregated nitrates. It's both ammonia and general nitrates. And then pretty quickly, we started migrating into hydrogen peroxide emulsions, and you can see direct results on nitrates. And we're talking very quick results. It took days and weeks to see the mitigation results. And after training and everything, you know, all the operational aspects were ironed out, we moved out to 100% hydrogen peroxide emulsions, and the nitrate levels zeroed out completely. So when it comes to nitrate and ammonia emissions, I can guarantee you that will be eliminated with this. We don't mitigate, we eliminate. And there's plenty more data, but I like this chart. It's very representative to the process. The next thing we talked about was gases, and I think gases could be one of the most applicable savings to this market, especially when it comes to re-entry. We have proven that we are almost at continuous mining in the Nordics. Re-entry times can be reduced dramatically. We are speculating that we can also save on ventilation, but that remains to be seen because every mine is different. This data comes from another tunneling project in Norway, also fairly big phases. The phases were about 1.1 to 1.2 tons of emulsion per blast, where we compared on the same phase the gas and dust profile between A&E to HBE. This data stems from about 20 blasts each. And it's, I should say, it's airborne dust. It's dust in the air. And you can see very clearly that we have very dramatic reductions in nitrates. We have very dramatic reductions in carbon monoxide, also in carbon dioxide, which address your Scope 1 emissions. But dust suppression is tremendous. Up to 70% dust suppression in the working environment. Re-entry on this phase was about 20 minutes. And then we're talking big blast, over 1 ton per development phase. So I think this data is something that we should be able to replicate in this market, and I think we should be able to look at things like maybe not continuous mining from the get-go, but at least independent phase work, on-shift blasting. Me personally, that's something I really like to see in this market, and that will dramatically change your cost and productivity profile. Let's see. So what about performance? When we talk about sustainability, everybody says, okay, if you have a green product, does it cost more? Does it give me the same punch? And so on and so forth. So very early, this is data from 2023, when we did a direct comparison on Advance. We are comparing an optimized ammonium nitrate solution from a well-established supplier with our first test. So this is the first time we did tunnel development on a commercial scale. And yet again, we had 2 phases. We had ammonium nitrate in one phase, and we had our technology in another phase. And by downloading the data from the drill rigs, we could determine the delta of every advance. So this stems from more than 200 blasts on each technology. And on average, the ammonium nitrate were a little better. They were 97% pull on a 6-meter blast, but we were a very close runner-up at 95%. So we're comparing a mature technology that's been around for many, many years with our first test. Today, we're better than this. Our average pull in the mining industry today is 98%. In a Scandinavian context, I should say again. So sustainability is paired with productivity, right? Remember this. Let's see. No. So I'm trying to show you a video. Okay. This is from 3 weeks ago, 3-4 weeks ago. It's a quarry blast, a traditional quarry blast. And I just wanted to give you some comparative ideas. This is again 12 tons, it's a full MEMU truck, and this is water steam breaking this. This is completely nitrate-free. This quarry in particular is very interesting because it's prohibited to operate due to nitrate emissions into its recipients. So for this quarry, changing to our technology saved the complete operation. And we don't compromise with their fragmentation, it's the same. We don't compromise on their operational procedures, it's the same. They only change the product. I like pictures and talking, obviously, but I just want to show you this is happening. This is not a garage product. We're not in the lab. We've been out in the field doing this commercially for many, many years now. There's some examples of our underground charging units in operations in tunnel projects in Sweden, mining projects in Sweden, underground mining projects in Norway, tunneling projects in Norway, and in Switzerland. Some results. Typical fragmentation. This picture to the right is from a Swiss project. We're running a fairly large-scale train tunnel project in Switzerland. The picture center down is from a board and pillar mine in Sweden. We're at about 1,300 meters. It's a zinc mine. And the picture top center is from a very large tunneling project in Norway. So you can charge it the same way, you use the same detonators, you use your same operators, you just remove the nitrates. Easy. So I'm going to be a little quick about this because we are short on time, but so Hypex Bio represent a paradigm shift. We're completely changing the technology baseline. But we are not a sustainability company. We are positioning sustainability as economic and performance sustainability. And the green stuff, that's our ticket to play. We're future-proofing. So we are offering performance enhancement technology to your re-entry times, to your general environment underground. We will, given time, outperform ammonium nitrate emulsions. Remember, we have 46% water today. Tomorrow we have 30% water. That is a clear difference in energy delivery. We're not there yet, but we will. We are on a roadmap together with BME to bring this to this market, and we're looking for pilot customers to trial this, to replicate the results we have in Scandinavia, and to work with you to see how this technology can improve your cycle. And that's a learning curve we need to do together. And finally, it aligns very, very well with the sustainability targets and the transition targets and innovation targets of the global mining industry. Moving to Hypex Bio is probably the easiest thing you can do to satisfy your sustainability goals. Short and concise. Thank you. Thank you.
My mic's not working. Thank you, Thomas. That was amazing. We've got 2 questions on the app. When can we expect to see a formula for the southern warmer hemisphere?
So right now we are trialing a well-advanced formula with excellent stability up to 75 degrees for extended periods of time. We have tried sleep times up to 20 days without any product challenges. It's being tested in pilot production at the moment, and we're going into in-rock C2 testing in 2 weeks. So the composition is probably there already. We're now just going to do the certification tests and then obviously get BME to like it. And when that happens, we'll bring it here.
Fantastic. That's awesome news. The last question is, what percentage increases can one expect to see from productivity in underground mining? And can we expect to see any working capital and overheads reductions?
This is a good question. It's important to understand that every mining operation is different, but our baseline is underground. That's where we feel we can add the most value. And if we look at share of wallet, where we have 4 to 5% cost for explosives and ventilation cost and productivity cost due to downtime is substantial, I foresee that productivity can be increased by potentially adding a new shift, having parallelizations or phase availability increase. I will not give you a number. It's up to every mine, but we have seen vast improvements in Scandinavian mining, mainly due to these reasons, but also risk mitigation due to nitrate issues.
Great. Thank you so much. Another round of applause.
Thank you.
Good.
Thank you. Thank you, Lungi.
Thank you.
Thank you, Thomas. Very insightful. Our next presenter, also an international speaker, Tom Dimony. Tom, please join me up on the stage. He's going to talk to us about from civil engineering to global tech leadership. Tom Dimony will show us how EIS, that's electronic initiating systems, if my memory serves me correctly, drives value across the mining ecosystem. Tom is the International Technology and Field Service Manager and holds more than 80 years of experience in the civil and mining industry. A qualified civil engineer, Tom has worked through the ranks and has acquired extensive experience in various blasting applications and initiating systems. Tom has been with BME for over 10 years now and is responsible for introducing new technology into BME and providing global technical service support to the rest of the BME team. Please help me welcome Tom Dermody.
Good morning, everybody. I'll be the final person to say good morning to you, and thank you, Doc, for the introduction. I'm Tom Dermody. I am a passionate person about blasting. All my life I've been invested in blasting technology, blasting innovation, and looking outside the blocks about how we can look at different ways of driving value across the ecosystem, while also feeling that fulfillment you get from firing the blast. And for anybody here who's had the pleasure of being there at the two buttons, when you push that button and you see a blast fire, it's the fulfillment you get from seeing it being delivered, and delivering a quality blast for our client is something special for me, although I think it still amazes my family. I get so much fun from a piece of rock, but hey, that's the way it is. So today I'd like to take you through some consideration around how we drive value across the mining ecosystem, and take you through some case studies where we've actually applied our out-of-the-box thinking to help solve some complexities or challenges that are faced in the blasting industry. So for us, normally when we see a blast, we'll see a blast video. We won't actually, we don't normally see maybe the complexities, what is perceived, what's behind a blast video. Hold them on. So what looks like a complex blast or a simple blast carries a lot of complexities in behind it. It's going backwards on me. Hold them on. When we think about complexity, it's normally a challenge that's been put down to us by the mine, that they've been driven predominantly by a safety challenge, or sometimes we see it from a productivity challenge. Maybe we have to change the orientation of a mine, or they want to enhance the fragmentation, or sometimes it's driven by our environmental constraints, such as vibration, dust suppression, communities near us. But I think Ralph alluded to it earlier there this morning when he said that BME is commitment to driving value. So when we put all these together, sometimes it's a combination of safety, it's in productivity, it can be a combination of environmental and productivity, or all together, where we're actually looking is how are we creating value for the client. To drive that value, you need to have a differentiated value proposition. So when we look at it, we look at our technical expertise. You need to have people with advanced blasting technical expertise who supports the customers and come with different knowledge and thinking to the systems. Digital systems like our blasting lines and what Nishen spoke about earlier about Streos, how we bring data-driven decision-making into the mining industry so we can predict what's going to happen. We can understand, we can see what this is. When you get to that point where you get to push those buttons for fulfillment, we actually have understood what was going to happen. To deliver that, I think as Scott spoke about earlier as well, was about where we see digital initiation today, about precision and accuracy. And I think someone asked a question there about what was perceived as the older 8-millisecond rule. Now we have the availability with safe systems to deliver that accurate outcome on the bench. So we can really understand how we can influence rock and how we want to move it, how we want to fragment it, or how we want to customize it for the solution that we're looking for, be it an excavation solution or be it elimination of a process in the mine. And most importantly then as well is having an explosive product that can actually manage the rock. So Raki spoke about our products earlier there, particularly thinking about product performance and also then the flexibility to match the energy. So sometimes we'll have different situations where we need to consider an increase in powder factor or a reduction in powder factor, how we influence it, and using the software to design the simulation of how we can push the material in a different direction, or we can create different fragmentation. So to really look at these in reality and how we do it, I'm going to take you through some case studies where we've actually applied these in the field. So to give you a look at what we do, our first case study looks at a dragline operation. So the overall review or scope of it was this dragline operation for a typical dragline shot of about half a million cubic meters of rock per production blast. The mine itself, I think I have a little light here. This is our production blast here. But because of the actual dip of the floor beneath the coal seam, the dragline shot needs to fire auxiliary these little auxiliary shots across the floor as a lock and key to stop soil creep down along the floor while they're excavating a production blast. The mine in this position here, they utilize this to protect the coal seam. So in this typical operation before we addressed it, they were actually bulldozing then this auxiliary fired key. They would bulldoze that rock up against this face here to create a protective layer against the actual edge of the coal seam, so to prevent coal loss with the coal seam. And that's particularly a risk when we're blasting, that we can damage this initial area of the coal seam while we fire and we fire the front rows. So what the mine had been doing was firing this auxiliary blast here that we see, and then also pushing that up a bulldozer. So what they really wanted to look at was, what they wanted to consider from the safety aspect was, how could we eliminate the dozers having to work beneath the high wall, because obviously we know it's a high risk and permit to work system that we have to work there. And also, how could we utilize this auxiliary blasting in some format that we may actually be able to come up with a solution. So the challenge that the mine set down to us was, well, we want to improve production, like I said, to take away that dozer push. The protection of the coal seam was paramount. That was the reason, one of the main reasons for firing the auxiliary blast. But also then, we had to consider a redesign of this auxiliary blasting and how we could influence the rock that come out of that trench and actually propel it again in the face. So what that actually looks like, and you see the simulation, this is actually a blast. You get to see a simulation. So what we did is we created a blast design that we could actually, the blasting material could be projected towards the production face. You will see as it initiated there's a 4-row blast. You can actually see there's 2 leading rows, actually center lift and leading row, and then the 2 rows that are furthest from the face are used to project the rock with the timing up against the wall. So what that allows us to do to create a kind of throw style of the rock for the mine to eliminate the dozer push, which would in turn protect the coal seam, like I showed in the diagram, but also would reduce people from working under that high wall, which was the main key here. Was the main driver was the safety of production. We wanted a production gain, but being able to utilize this lock and key system that they needed to fire for the soil or for the dragline, and utilize this rock, it was key to how they wanted to move forward. So for us, this was the result. So you can see here in this image, this is actually that blast, and the final result surpassed what we expected, to be honest. We actually achieved, that was a 4-row blast, and you can see here, this is the back trench at the back where the lock and key will be, and we eliminated dozer push from them. They did not need now to put people beneath the dozer push anymore, beneath the high wall anymore. So from our complex diagram where I said we're faced with a challenge of normal safety or productivity or environmental, in this instance, the safety for us was reducing those people beneath the high wall. It was eliminating the cutoffs that could be created also from misfires by changing our blasting technique for the mine by using electronic detonators. From a productivity side, it was actually substantial for them because now the doses that were absorbed in the floor of the dragline shots now could actually be utilized elsewhere for stripping overburden. And also then we were able to maintain what they asked us in production was to ensure that we protected the coal seam, that the projected rock that had to go in there, that we can actually cover the seam that actually resides actually kind of here at the bottom of that blast there. So as you can see, we projected the material quite high up against the face. The value creation for the mine was increasing mine safety. They were quite pleased with the fact that we could actually take the people away. The risk to people had been reduced significantly. The operational hours from a productivity side meant that approximately 40 hours of dozer push for that floor now could be utilized somewhere else. So it meant a utilization of machinery from a production side, and also we still maintained that reducing that coal loss for them in the projection of the rock against the face. A second design where we would have used the same complex solutions model to think about was in an open pit design. This is an open pit shot, open cut coal shot as a pit and shovel, truck and shovel operation. The mine was a number of 2, 3 years, maybe 4 years actually into operation when they realized that they probably weren't getting the most out of their shovel and actually wanted to get a lot more out of it. They found that there was a lot of downtime from bench prep, from creating bench prep for each blast. So they wanted to integrate their blast benches. That's what they really want to do, and drive productivity. So they want to understand that could we change the pit design. And as anybody's familiar here, our pit models are created a long time ahead, long-term planning. So to consider how now, 4 years into a lovely expansion of a pit design, to go and change the methodology of mining based around the excavation unit actually became a cost-saving initiative for the mine and a kind of value and use of driver for us. So what they really want to do there was consider how we would change that excavation method for them, but also increase productivity by doing so, by reducing the downtime for blasting. The challenge, and it was a challenge, was combining these two benches. So here's a cross-section of those two benches. Each bench was about 24 meter benches. We had to change it then into a 48 meter bench by combining the two. Now, it actually posed quite a challenge for us because one of the problems we had is because with this new bench here, and we've been benching perfectly and lovely clean benches and high wall protection, meant that now when we actually drilled the holes, we could not reach them from the crest. We could not get out far enough to drill this area. So we had to consider how we were going to blast that later, which we were able to establish. But when to combine the first initial bench to start this double flitching, if we want to call it, we had to drill the full depth down to 48 meters plus a bit of subgrade. The challenge in there was because of this, if you want to call it like a ring beam of rock that sat in front of the blast furnace, we had to consider how we were going to lift the rock vertically to manage the extreme confinement that we were going to experience there. So we've been down to 48 meters, you will have extreme confinement. And really what we were worried about was the fragmentation. Because when they were going to excavate it now, they're excavating flitches that have less downtime for blasting. But the challenge here was that when they get down to dig in this area, we could remedially work that piece of area that couldn't be initially drilled. But the challenge was, how would we manage this white box area here, as you can see on screen, to manage the confinement that's in the rock there, particularly around the fines and particularly around the diggability. They were extremely concerned how it could impact their tons per hour for the machine, because we could actually lose the value of changing the mine if we found that the lower two flitches of excavation were actually quite tight to excavate. So the solution, this is the blast, this is actually the first one we fired, was to introduce 2 initiation points into the blast. We used our software to design an elliptical initiation sequence. And this became very important. When we created the center lift, we created 2 for a reason. There's one here, as you can see, and one here. And this is the contouring on the top, showing us how we actually looked at it from a simulation side, predicting ahead to give us the decisions about how we could blast. While we had to put consideration into the initiation, we also had to understand what energy we needed to create the initial uplift. So we created relief in the blast. It's quite a large blast, as you can see. So to pull that 48 meters out of the floor with some relief in around it there, and by creating relief in the blast, so we could still maintain fragmentation. So a lot of work was done around understanding rock movement, burden response, mapping the blast, understanding how the rock is predictable, and we did a lot of work with the geotechnical team to understand fractures and faults, because this mine actually also struggled with some extreme faulting, and loss of energy could become a major problem for us at the deeper depth. So if we had a couple of faults intersecting here, the firing through the faults incorrectly could actually dissipate a lot of our energy. Also, part of, while we did the design here that you can see in the simulation, we put consideration into how, as the blast progressed out, how it interacted here, but also as it moved to the edges, how we actually slowed the blast down to allow it to move. Because if we fired it all to one speed, the blast would end up choking itself and tightening up against each other. So when you get out to these end walls, you actually wouldn't get actually really good fragmentation or movement. What that looks like is the image on the top. So we managed to pull, this was measured 20 meters up out of the floor. That's, the mine actually said, that, I think there was about 40,000 cube of rock come up out of the floor when we did the blast. Now, I don't have the video for it. I would love to show you the video. There was no ejection. It was absolutely full heave because of how we designed. We looked at the scale depth of burial around those IP points, and we looked at the energy and how we distributed the energy and what energy we used in the initial holes that created the lift in the blast versus what energy we used. So we changed different type of explosives as we moved away from those IPs because we wanted an initial hoof to lift it out of the ground as well. What you can see here in the images post when we did the other remedial blast to move the other ring, this was the material excavated at the 45 RL. So we actually surpassed the fragmentation we were even expecting ourselves. We predicted that the fragmentation would still remain some way consistent, but this was the material that they actually excavated out of the 45 RL at about here, about this side of the blast here, when we started initially digging back down into it. But from our complex solutions diagram that I spoke about from a productivity side, what we actually achieved was we revised the mining method for the mine. They now could actually look at improving the production efficiency, what was seen as a challenge for them of combining these two benches and having to actually change their pit design. They now could realize through this trial blast design that we put there, that they could actually implement this across their mine and actually change the methodology for the load and haul. What that actually meant for them was to minimize downtime. And when we think of downtime, we always think of just downtime from blasting for shovels, but also with the remedial work of bench prep and bunding and drilling and all the work that needs to go into place just to create a platform for the blast to be drilled. We'd half that immediately. So that absolutely led to efficiencies all across both their load and haul fleet, but also their drill fleet and also their remedial work fleet as well. What was important also, that maybe I didn't mention as I was going through it there, was part of that control was of the high wall as well. So I think I spoke about the faults when we had faulting there. One of the things we had to be careful of was the energy that we put in there did not actually break back into the wall and actually open up faults or create another problem for the preceding blast thereafter. So consideration had to be given in around high wall protection, the timing side, the energy, what we had to do. So that was just something from the environmental side that was also delivered as part of this blasting. The creation, like I say, from the value creation side was reducing the overall cost of mining. Production volumes went up, reduced the overall cost of mining from, and truly we optimized the load and haul. Productivity went up on their excavator because of the depth of which they could take now. So they actually found that over the period after we rolled this out over a period of 6 months, they actually found that they were getting better swing rates with their excavators and better loadout rates based on the fragmentation, the methodology, and the introduction of multiple point initiations on large blasts, creating that relief within the blast. The case study I'm just going to take you through, and there's quite a bit to this one, is managing vibration to maximize resource recovery. So to give you a little bit of overview, there's a lot more than I could say in the scope. This was an open cast operation where they had actually been doing some blasting here. What the challenge was is, as you can see here, that's the boundary line across the blast. Next door, a neighboring company had an underground mine on the same coal seam. that remained active while we were blasting. So the guys would not evacuate underground. They would stop the longwall miners, go to the refuge, fire the blast, go back operation. So they wouldn't actually come up from the surface for the mine. That was a challenge, to say the least. But the bigger challenge for us was actually the ventilation shaft. There's a ventilation shaft that they had for pulling in fresh air into the mine. And that ventilation shaft had quite a couple of large fans. And on those fans were vibration sensors or oscillation sensors that if the the bearing started to go, these would trip out the fans. But a blast could, if you shook it hard enough, could simulate that the sensors thought that the bearings had gone in the shaft. So what they had to do was understand how could we manage vibration through here. we took over the work to help them there. They had one HPI, and they had asked us to come and have a look at what was happening. They had a HPI incident, a high potential incident, where they actually triggered this fan, which actually resulted in emergency evacuation of the underground mine, which is ultimately what you have to do. So that was quite a large event, both from an inspectorate and management, and actually threatened the whole viability of this area to be mined. And while they were mining here, they did go back to being able to control vibration. So a focus was brought back in. They could control vibration, but they couldn't achieve fragmentation. So although they brought the limits of the blasting down around for that area, the actual rock was coming out very, very tight. And they actually couldn't dig it. The diggability was kind of gone in the rock. So it was nearly not viable to actually excavate that area because of the nature of blasting, so constricted to vibration. So, excuse me, to understand that challenge, because of that, using our depth to scale burial and using our scale distance and understanding vibration, we actually had an MIC that we couldn't exceed because of the distance to the vibration point, particularly the ventilation shaft. So we needed to keep the vibration below 10 millimeters per second for all blasts. So that's not 95% roll, that was all blasts. Any exceedance was seen as a non-compliance against the other mine, would raise a non-compliance against us to the inspectorate, so it became an issue. And the ultimate one was we had to have no impact on the neighboring operation. So we had to understand how, while we were blasting, we could not have any impact in any of their operations on what they were doing. So I share a little bit here in these diagrams to think about how we had to approach it. As you see, when we initiate and think about vibration, we need to think about the MIC. Each one of these little rings represents an MIC charge initiating. And as you can see, the direction of travel is left to right in this position. As each hole fires, depending on the location and the properties of rock and how the wave passes through, the velocity of the wave through the rock, you actually at a point get what we call wave interference or actually reinforcement. This becomes a big problem for us if anywhere around here that ventilation shaft seems to be, because while we're controlling vibration singly per hole, while these waves traveled out, they actually could accumulate and actually create a more concentrated expectation of what was going to happen than what we were predicting. So when we did our designs, we had to consider how we could influence if to stop these crossing at any vibrational point. And I shared a video to show what that looks like from, particularly the lake is the quite easy one to see 3 rocks coming in. You can see here how they cross over and where each one of them crosses, there are actually zones of influence here and here from each rock being dropped in. Although they're dropped in separately or together, the points of influence where they all meet can sometimes be way beyond where the hole was and how we think. That also came important when we talk about the wave. We also have to think about the direction of fire, and also what we know is the word I'm looking for, the dominant energy or potential is towards the direction of fire. So we had to understand if we could actually change the direction of fire of the blast as well to move it away from how we fired the blasts for the mine. So, excuse me, the solution, as you can see here, is actually reverse echelon firing. So we actually fired the blast in reverse. So we fired it from back to front. And you might think that's crazy in some ways, but what we had to, and you can see here, we're missing a deck here so we can create the same face profile when we go back the next time. But I've only showed you here for a reason why we alternate the deck sequence for a reason. What we had to consider was if it was just simply top to bottom, the restriction and the confinement around here meant we were not still achieving the fragmentation at this lower level on the bench. The decking was driven by the MIC that we could use on the blast, so we had no choice, but that was the maximum charge at any distance. So this hole here actually became, the nearest hole to the blast became the critical hole that would dictate. As we went away from the location, you could modify the explosives a little, but it was minimal the amount of changes that you would make. So we remained consistent across the blasts because that became very important when we did some measurements thereafter. So actually then what you see is when we sequentially fired, you get to see that we fired it 1, 2, 3, 4, 5, and then top bottom. So we used a staggered pattern in the decks to create fragmentation across the blast as well. So we understood what the burden relief meant to us, but also understood that the direction of travel was very important and how we influenced where that wave was going. What that looks like here is actually that blast. And in here you get to see is what you're paying attention to here is each wave actually was designed to pass through the underground ventilation shaft. So the timing, you can see here obviously there's a bit of dominance there, but that's going away from the blast and direction of travel. We were really concerned about this area here, which was the drift down into the underground mine where we had monitors all along, and the ventilation shaft where we monitored on the surface. So you can actually see how we influenced the waves to stay uniform as they passed through particularly the ventilation shaft. We had to consider how we could, the resonance of the frequency of that wave as well, and how we could consistently, so basically the ventilation shaft did experience vibration. It wasn't like it was zero, because 10 would exceed it, but we would also have to think about how the shaft could harmonize with it and actually oscillate over and back. So we had to consider also the frequency of that wave in our timing design. So we didn't create timing that was too long. We also had to create a timing envelope that was short enough to allow that it didn't actually begin wobbling over and back for a long duration. It actually just resonated with the blast. So thinking about the frequency of the waves as well. So what that looks like. So what you see here, and I'll just keep playing, is that's actually the final phase thereafter, the phase of the blast where we actually shunt the blast forward in shears. So you get some overspill, like a wave, but it shears through the blast and leaves an angled repose of the rock that we can actually manage it thereafter. The noise you hear over me here is actually the phase burst coming through of each echelon as it pops the last row. So I'll leave it play again so you'll hear that. It sounds like a dozer tracking, really. So what that meant for the mine was, going back to our complexity solutions and how we look at it, from a safety side, we protected the employees next door. That was the ultimate number one thing. They had a HPI and there was a lot of nervousness for the customer, the next door or the client or the neighbouring mine, if we could actually manage blasting. So we had to show a methodology of blasting to the inspectorate and present it also to the mining the client next door, so they were confident in how we were going to approach it. We were actually still achieving. The client itself wanted to understand how they wanted to see the confidence in that blasting, but they also, their priority was productivity. We were controlling vibration, like I said before, but we weren't controlling fragmentation. So they still wanted to get the fragmentation in the blast. From our side was, from the blasting side was, we had now introduced with the mining team, we had introduced a new blasting methodology into the mine. So this increased the life of mine. This was going to be an area that was going to remain stagnant if a methodology hadn't been created. So, and still achieve that fragmentation that I spoke about from a productivity side. From the environmental side then, as I said, the big driver was controlling that vibration. Thinking about how we influence the blast, maybe a little bit outside the box to fire a blast backwards and in a funny zigzag across the blast, but understanding through measurement how we can influence the outcome at the position we're looking at. And sometimes it's not always the blast we're looking at, it can be the area that's farther away environmentally, in this instance, a ventilation shaft. And understanding how we can use our software from a digital side to predict what's going to happen, but then realize it with our electronics, where we can actually have a selected time windows, which can actually deliver the outcome that we wanted there. The creation for the customer was they could now extract what they couldn't extract before, and went on to operate there for another 18 months in that location. It obviously increased the economic viability of the mine in that pit. And most of all, as we all do in what we do, we have to maintain a relationship with our neighbouring people around us, neighbouring business and companies, and to present that to the mine and consistently go on and number blast thereafter this, and to be meeting with that mine, they grew in confidence that the approach that we had and what we were doing would allow them to continue for the time that they did thereafter. So, a little bit in summary. Today, just as a little bit of takeaway, just sharing that's kind of the knowledge that we work with here and we think about. And I always say about the out-of-the-box thinking and what we could look at and how we could drive it. And I'd like to hopefully kind of show how we explored some different innovative blasting techniques and to how we were challenged through the, as I call it, the complex solution diagram here to create the value that we spoke of and always focusing on that value creation for the customer. Thinking about how we can the case studies here that presented that maybe you can take away into your own operations or think about some of the challenges you face, either be it productivity or be it a safety challenge or environmental, and maybe consider how looking at it a little bit differently, a little bit outside the box, or the tools that are there to help us design that and think about it a little bit differently and deliver that outcome for us. And finally then, hopefully you see how we disseminate just our technical expertise. It's data-driven intelligence and decision-making. That's key to us. We need to understand, predict beforehand. That was very key to our relationships with our clients there, that they understood that we were managing it, that we had confidence in how we were doing it, but also ensuring that having the tailored solution that delivered the outcome from them was really, really important for them. So they understood that we came there with our expertise, with our products, and having the suite, the portfolio of products to be able to handle the challenging conditions was key for us to drive them forward there. Super. So thank you so much for your time. I'll hand back for questions to Dirk. Oh, there.
Thank you. Wow, that was incredible. We've got 3 questions for case study 1. What was the intent behind the timing sequence used to initiate the first floor blast?
Okay, good question. I think I spoke about a little bit there, but when we looked at the initiation, what we really want to do was actually lift the blast out of the floor and then actually use the momentum of the rows behind it to actually propel it like you saw on the diagram. So we put a bit of thought about how, if you think of typical civil engineering trench blasting, how we would zip the blast, we'd zip a trench and then use the energy of like a production to push it away. So the thought process and methodology we used around that from a design purpose was we looked at it from like a civil engineering perspective of firing a trench as a zipper, and then as you might have seen there in the diagram, it zips, but then we use like an armed production thereafter where we delayed the 2 rows behind them. So while that zipper technique lifted the rock with energy, we then, while it's in the air, then we use the other energy then to propel it forward. So consideration was given around the 4 rows on the blast, but the 2 closest to the blast being the ones to the production phase being the ones we lifted, and the 2 of them further away then being the ones that are actually the pushers that actually acted like the bulldozer to push it up against the face.
Great. In the case study 2, after the initial blast, how was the area that couldn't be drilled before then be blasted?
Oh, okay, yeah. So again, you'd see it there, and maybe I didn't explain so well. The red area that we couldn't drill initially from the bench, what we actually did was we actually flitched down the first 3 flitches with the digger, and we then went back out and fired just a remedial trench blast all along the front. So that area that we left there, we ensured that was 4 to 5 rows deep. So we actually had its mass that it wasn't displaced. So if you had a smaller mass of 2 rows, the energy being created from the uplift would actually create swell and actually damage all the rock. So consideration was given to the size of that area we couldn't drill also, because we want to understand the mass that it wouldn't be displaced. So when we go back and drill it later, when we flitch down, we went and just fired a remedial back down to the lower 48, and that allowed us then to move the whole high wall back to a 48-meter high wall. So although there was a step process there was consideration given around that area that we couldn't blast, particularly around if we shunted it forward while we were creating the uplift.
Great. And then on your last case study, what initial measurements were necessary to understand wave propagation? Oh,
yeah, good, very good question. So as part of the work we did with this mine, we actually brought in some experts in P-wave analysis and signature shot holes analysis, and we did multiple signature holes around the blast to understand the speed of the waves from initiation and what they were reaching and the frequency of how they were reaching. That was kind of critical in a sense that you can do 1 signature hole behind the blast was not sufficient, because what we found was at one end of the mine and one end of the bench, we actually had a fault dissecting the bench that actually influenced how the wave was changing there and dissipated a lot quicker than we understood. So doing multiple point P-wave analysis using signature shot hole analysis was key to how we measured the velocities for the wave. That then, once we had those calibrated, we could bring that into our softwares then, and actually, when you see those rings going out, they move at the speed of that wave, so we understood that where they could cross or if they didn't cross each other.
Fantastic.
Thank
Thank
you.
you so much. That's all the questions.
Thank you, everyone.
Great round of applause.
We also decided to keep the heavyweights, so to speak, of the industry for this session. So we have two very well-known speakers. First of them being Robert, or Bob as we know him, McClure. With over 30 years in explosives, Bob is here to talk smart drills, smart loaders, and smart blasting. A little bit about Bob while he's just busy miking up over there. He's a globally recognized expert in blast engineering and explosives technology, serving as the president of R.A. McClure Incorporated, and internationally consulting firm specializing in blast optimization, explosives training, explosives disposal, and technical services. Bob is also a certified instructor for MSHA and ATFE, and an active member of several professional bodies, including the International Society of Explosives Engineers, otherwise known as the ISEE, the Institute of the Makers of Explosives, IME, and Society of Mining, Metallurgical, and Exploration. Please help me welcome after lunch, Bob McClure.
Thank you. Yep, thank you very much. Is this on? Oh, there we go. Very good. Well, it's a pleasure to be back. And gosh, these conferences for over the years, and I've attended quite a few of them. You know, it's just great to see this thing back and alive again. So, you know, it's great to see this, and got to hand it to the team. You guys have put together another great program again. So, special thanks to the AMIA and BME group. So, with that, I'll get underway. We're going to talk a little bit about, let's see here. Well, there we go. The smart drill and loader technology and using this technology, whoops, I'm not sure why this thing's jumping ahead here, but using this technology for optimization of blasts. And what we find, and this is a problem pretty much worldwide, is you know, when you have very difficult faces, you know, being able to get the accuracy in the drilling out to the field. You can have the best plan ever, and it's how do you get that out there with the level of accuracy we need to handle very specific issues in the face where we could have some potential concerns. And so when we look at this, it improves the optimization process by getting that I'm not sure why things jumping ahead. By getting that blast design out to the bench. And along with that is with the loader, you know, being able to also get that grade control by going out there and being able to maintain that. Because what I find, and particularly it seems like in the quarries and the construction side, they don't have engineering there all the time. They don't have the survey groups there all the time. So having a little problem with the PowerPoint wants to kind of go on its own here for some reason. You know, we need to be able to maintain that. So that way we know the specific bench heights, we can maintain the grade control in there. And it may be for a whole host of reasons. Compliance, it could be for vibration and air overpressure issues, things along those lines. It could be the blast performance. We might have fragmentation issues. We might have wall control issues or floor control issues and things like that. The other area is the data reporting and KPIs and being able to track that. And what we're seeing now is finally a lot of quarries in particular are recognizing the need to move forward with this, because these KPIs are things that they need to be able to do a better job out there and get the performance that they need. And they need to bring these controls in to be able to manage that. So we're seeing now that the price point on a lot of this technology is getting down where it became more realistic, And it's been interesting because as we've introduced the technology into a lot of these operations, the comment we hear is, wow, we should have done this a long time ago. And of course, you know, you're there pounding away on these guys for a long time to get them to go forward, and finally they're starting to move forward with it. So I'm going to walk you through smart drill and loader technology first, you know, some of the benefits and what it brings to us in the field, and go through some of that. And then I've also got a case study. We'll try to get to the case study as well and step through that. And that was with one of the operations that we deal with in North America, Vulcan Materials. It's a very, very large aggregate producer. So let's first start off with the key component to the whole program. And that's the hub of all this, the software that's behind the scenes on it that we use to be able to communicate and seamlessly move the data around. And what we're looking at here, as you can see, you know, we've got the blast design analysis software. So this allows us then to take our drone images and be able to bring those in and generate the model. We can import the GPS coordinates, bring that in as well, and we can then geo-reference those blasts. And then it also allows us to send the blast design out to the drill, and then following the completion of the pattern, they can re-import that back into it. Along with that, we can go in and then look at the profiles, which this is what we need out in the field. This is the critical part for the blasting side of it, that we have these profiles there that we can go out there and accurately load these holes. And I'm going to get into a little bit more detail on that, because this is what differentiates this technology and helps tie all these things together. And then post-blast, we can go in, look at cross-sections and fragmentation and all these different things that we need as a follow-up to determine, you know, what kind of performance are we getting, and being able to track that and see the benefits that we're achieving with this. So, you know, there's a lot going on, but today with you know, the technology and like with the software that we have here, that being the hub, a lot of this is pretty seamless all the way through. So I'm going to step you through the workflow on this. And like I say, it may seem a little bit complex, but one of the first things that we start off with is our GPS out here. And this base station, it could be a portable base station, it can be a permanent base station. A lot of operations, what we do is we install the base stations right at the quarry. So you got coverage all throughout the whole entire pit. And the processing can be PPK or RTK, which what we're talking about is centimeter accuracy with the GPS. And then the next step is the flight. We take our drone out there, we do the flights, take all those images and introduce that into the software. And whoops, this thing seems to want to progress on its own. Sorry about that, but I don't know what's going on there. So what we're doing here is we're generating the model here so we can achieve a very high accurate model from those images, and then by incorporating the GPS coordinates in it, everything is completely geo-referenced at that point. So we go in and we do our blast design. We can also take and do the characterization of the rock mass and incorporate that into it. So as we do our blast design, those are some of the things that we can take into consideration into the blast design like we see here. Once that's completed, then that information, there we go. Once we've got this completed, we reference this as the as-designed blast pattern. So, you know, we've modeled it, we've input our pattern into it, we've looked at all the burdens on here, and this is our proposed as-designed blast pattern. So the very next step is then we send that to the drill. Once this goes to the drill, it can be loaded up in the drill several different ways. And then once the drill gets out there onto the pattern, we can use the navigation of this, and I'll talk a little bit more about that, which is going to get us to the holes while we're drilling. And Scott mentioned this a little bit earlier. We have the measure while drilling technology, where this is generating a blast log for us here. And then following, if you go in with a borehole survey system, you can go in there and track the borehole, and then from that, incorporate that into the as-drilled pattern, and this information, we pull it off the drill, it goes right back into this same model, and we get a what we call a geo-referenced as-drilled file, like we see here. So this is what we need to take out to the field, because from this, we're going to generate this minimum burden profile, and I'm going to talk in more detail about this and why the minimum burden profile is so very important to us on the blast performance, because like you saw in Tom's presentation, you know, when you start doing these kind of blast design, it is absolutely critical that we're maintaining the proper energy factors in there. Then once that's completed, then we can come over here and we can do the full blast analysis with fragmentation and cross sections and the swell, things like that that are going to allow us to capture those KPIs and get a clear understanding on what kind of performance advantages we're going to get, so we can constantly make those adjustments in the pattern, like we can see from the results with that. So looks like a lot going on, but you know, with the process today, we've got this to where this is quite seamless all the way through. And we've got companies today that they are profiling every single blast. In one particular area, these guys do well over 300 per year on with the quarries that they've got in around their given area. And I'll talk about that because it's one of the locations that we did one of the primary case studies and stuff. So let's first talk about the smart drill systems. If you're not familiar with it, what we can do is we can, you know, order a drill. So if we get a new drill, we can just have all this installed, which would be the GPS systems and all the equipment like you would see here, come right on the drill like that. And this would have everything for the monitoring, multiple GPS units on here. This gives us the orientation of the drill. And now with these articulated rigs like we see here, where the mast can move around, whoops. I'm not sure why this thing has a kind of a mind of its own here. We can move this mast around, and it will track exactly where it's at, the angle and the azimuth of it. So one way is you order the drill in like this. The other way we can do it is if you have, in a case like this, an older drill, or maybe your drill's a dumb drill, and we can make it smart. So that's the advantage with it. These kits can be put on there, and through an aftermarket system, the hardware can be installed onto it, and it can actually be taken off and put on, you know, moved over to other drills as you retire that one out of the fleet and things like this. So the advantage is whether you bring a new system in or, there we go. I don't know, is there a way they can stop that from? No, it's whoops. For some reason, it's got a mind of its own. Is he fixing it? I hope. But, you know, with the drill kits, there we go. There we go. So with the older units like this, we can put an aftermarket system on it, and you can bolt all the system on there. So a great advantage that way, and some of the aftermarket systems actually carry an additional benefit, which we'll talk about a little bit later on, because with the tracking, because some of the systems, if you purchase it with the machine, you're going to be tied into that particular manufacturer's, you know, reporting systems and data collection and things along those lines. So there's quite a bit that goes on to it. Typically, you're looking at maybe a day or two to get everything installed. And as I mentioned, when that drill's taken out of service, all that equipment can come back off and then reinstalled on another drill. Obviously, you'd have some time involved with it. But the advantage is that we can take an older system, whether it's a tracked rig, or we've even done rubber tired units, because a lot of the quarries around our area, they actually have these rubber tired drills that they use for most of the quarry operations, because they travel to a lot of the different sites, and they can put those systems on there. So let's talk a little bit about the smart drill capabilities and what are the benefits that this technology, putting this technology on there and using it, really bring. One is, and one of the foremost one, is drill navigation. With that, one, you're getting borehole setup. So as you can see here, you can actually see the drill. This is off the tablet in the cab. They can identify each of the boreholes that you put into your design, and they're geo-referenced on the screen here, and you'll be able to see as you track up to that particular hole where to set the mast and be able to boom up on it. So it gives us that collar placement, and now we're talking centimeter accuracy on that placement. Along with that is it gives us angle and azimuth, and I'll show why this is really important, because when we get into very complex blasts, being able to get that position properly is key. In the past, we had to do this manually, and we'd have to put arrows out, things like that, set those angles and azimuths on there, and just kind of hope for the best on it. And of course, that's why we'd profile it and bore track it to check. But now today, with this kind of capability, we can put it in our design in the model and then execute it out in the field with that. Along with that is also the depth, and I'm going to talk a little bit more in detail about that as well. So we're getting a lot of information that comes from the design, goes to the drill, so they know exactly what they need to do out in the field. The other part of it is the major well drilling, and Scott mentioned a little bit about that and some of the advantage. What this is doing is giving us the borehole condition, essentially. We're getting kind of a subsurface view of that geology that we're dealing with. And along with that, we're picking up, do we have hard, soft, fractured, overburdened rock mass? Now, as they're drilling, that drill is sensing that material and generating a report for us so we can capture that. And again, this is critical information for us to be able to take and put it into our blast design, because in some cases we may have to deck through it, we may have to do some custom loading, we may have to address some things like that. The other thing is cavities, like we see here, and in this particular case, you know, this was almost a meter where it was the cavity was there. And that's really key, because obviously this could create a significant bomb if we loaded that up. So we need to know these kind of details in there. The other one is seams, especially if we see a very significant seam. This particular one is kind of a clay shale seam in there. Again, those are things that we need to know to incorporate into the blast design, because unfortunately, Mother Nature just didn't give us good rock. We always have these kinds of conditions that we've got to deal with out there. The next part of this is the drill performance. And when we look at the drill performance there, this is information that we can pull in off of the site. We can determine where the location of the drill is, you know, in the quarry. We can look at operational uptime and downtime with it. We can look at drill footage, and along with that, penetration rates, which are extremely important to us, and also re-drills. So now we can capture a whole host of information off that very specific drill on that site. And again, this helps us build that history of that site, so we have a very clear understanding of, you know, what we're dealing with out there. Because you may have a particular quarry or operation where we've got some areas that have a lot of seams and voids and issues there, and maybe the other sides might be quite a bit more competent. So now we have a way that we can pull that information up and track this information, and also operationally as well, you know, for on the admin side. So you can see where the Smart Drill brings in a lot of capabilities. So what we'll do now is we'll break down the benefits of each one of those and talk a little bit about both and what that brings as far as the value. The first one is the drill navigation, and this one is really what I see as a significant benefit, because one is the borehole pattern layout. So we flew it, we designed it, we sent it to the drill. If there's any changes in the pattern or whatever, that's all going to get captured. But on the initial drilling, when we've sent that pattern to that drill and they track out there, you don't need any marks on the ground. They're looking at that tablet in there and they can see the collars of every borehole. And as they track up to it, we can pull up there, and we're sending this information all to them, you know, with the flash drive or even by email. So when they get this pattern, this is that as designed pattern, we can see all of that on there in a tablet in there. So one of the key things here with that is we don't have any layout required with it. So you can see in a case like this, you're not putting anybody out in harm's way. We don't have to put any marks on the ground. There's no reason to pull tapes across the shots. A whole host of things that were really quite problematic, especially if we had issues where the terrain was a bit of a problem. And when we look at that, whoops, there we go. That way we can be sure that we're getting the collar placement even in very extremely difficult terrains. And I'll give you an example. This just happened to come right here from South Africa. And you can see here, the bench was supposed to be up in here. And look at this. You know, it takes a significant amount of engineering to be able to fix a problem like that. And with the variation, because if we're trying to maintain a very specific grade down here, you know, look at the difference. Here you can see some of the guys standing on the bench. And again, you know, to be able to get that, how do you pull a tape across here or get a proper layout? So this is where one of the really great benefits comes in, because on that drill, they're looking at that tablet. They know exactly where that borehole is because of the GPS units on the mast. As that mast is put out there on these articulated rigs, they can get the alignment correct and proper, even in very rough conditions like this. And again, and what was interesting about this, we questioned the operator, and they told us that he was the lowest cost price. What's that tell you? Sometimes maybe you better not go with the lowest cost guy, you know, because the cost to come in and clean that up is quite significant, and you can see what a mess it is. And you know, that was just simply over drilling. You know, they just over drilled and overshot that particular area in there. So here's an example. We animated this. Here's our train here. So the topography, you know, it's up and down, kind of like we saw in that last picture. And obviously, that's a real problem, because if we're trying to maintain a floor grade across here like this, and we want to maintain this level grade, or maybe we've got a slope in it, whatever the case is, we need to be able to adjust all these boreholes accordingly to make sure that we get the proper depth. And along with that, also is to add in the required sub-drill that we need to be able to pull that floor. So when we go in and load and shoot this, we can capture this grade all the way across here. But obviously, for, you know, as you can see, we need to be able to make sure that we've got enough sub-drill in there as well. So when we put this into the original model, because we've flown the top of it, we have the topography in there, we capture that, we now know exactly how deep we need to go. And then if we put in there, we need, let's say, for example, 1 meter sub-drill on it, then it's going to add that in. But along with that, if I'm trying to hold a very specific burden and spacing on that, we can be assured that we're going to get that in between all these holes all throughout that pattern, because we know exactly where that collar is going to be and what the sub-drill is in here. So this is huge, because in a lot of cases, it is so difficult to manually lay out a type of blast like this. And we find in a lot of the quarry operations are out there, like in our area, it's snowing, the wind's blowing, you're trying to pull a tape that's 100 meters long, and it's, you know, up and down. You are not getting that kind of accuracy. And this is where the system really shines, because now we can do this without any marks on the ground and be able to get the proper depths all the way across that pattern. The other area is when we start talking about larger scale shots, and when we look at, you know, like a cast operation, you know, out in Wyoming that we have, kind of like what you have up here in Middleburg, places like that, you're just not going to manually go out and lay out a shot like that. You know, this is where, and most of the bigger mines have some degree of this, but in some cases they might not be doing the more complex shots with the angle holes and things along those lines. So as you can see here, it would be nearly impossible to lay that out. So now, again, without any mark on the ground, the driller has this, they know the depth, they know the angle, they know the azimuth, and they've got that on it. Even if it's like a platform drill, kind of like a pit viper or something along those lines, like you see here. So we can take care of that very rough terrain, but we can take care of the larger scale shots as well for something like this. The other key component, though, is the fact that we can get the drill angle, azimuth, and depth. And the important thing with that is as you kick the angle of that hole out, it has to be longer to accommodate the depth. And in the event we're adding a sub-drill onto it, we've got to add that on there as well. So one of the great things in the design side of this is as you get that design started, it's making the calculations and then telling us what that depth has to be. As we do the design, we can use a heat map to determine that we've got the appropriate burdens on it. So a big advantage that way. So that way when the drill sets up, they're looking, once they're on top of that target here, and you can see the alignment here, once they're on that collar, then they're just moving that articulated boom around to get that alignment so it's lined up all the way through. So here's a good example. This was a blast that the previous company was in, did a shot over here and it failed to pull this corner. And essentially what you have is almost a three-sided shot just in this particular area on this bench. And so it turned out to be quite complex. It was unsafe to put any equipment down here to try to drill it out. They had to take an angle hole and try to get that down through here. But you notice there was a lot of preconditioning in that area from that previous failed blast. So it was real problematic to be able to try to get a hole strategically placed so we could carry out and pull this tow and this heavy burden down here in this particular area. So when we look at the alignment, and you can see here is the proposed drill, this would be a 2D view of it. And if we look at the 2D view, this is essentially what you can see. And in this particular case, they were trying to hold, I think it was right around 4 meters on it. This dashed line that you see right here represents right around that 4 meters on it. And keep in mind, this is a 2-dimensional view. But one of the things that we would do in the software is we would then also use the heat map and apply that. And when we do this, what we can see here, whoops, there we go, 2D view. This particular area, if you notice right in here, notice the red. So we're right around a scale of about 2/3 of a meter. So what this is reflecting is the blue represents, in this case, kind of an overburden on those boreholes. The green is right at scale where they wanted about that 4 meters. So where you see the green in through here like that, and then of course the red is less. And of course, once we got the design here, we couldn't really move the hole any other way. We had to get the hole somewhere in there to help carry it. But right away, that raises some flags right off. We know there's a potential for a problem there because when this shot went in this area here, it tore a good portion of that corner out and then preconditioned all this area up in here. So we're going to come back and revisit this, but that's the 2-dimensional view. In a lot of cases, companies are going out, and that's all they're using is a 2-dimensional view. And you'll soon learn that it doesn't tell you the whole tale. It's only telling you part of the problem that you've got here. So on the angle drilling, we track up there, and like we talked about, once the drill pulls in, lines up on the collar up here, and we get that angle and azimuth. And as I mentioned, one of the key things is if we put in, let's say, for example, 3 meters of sub-drill on it, you can see here's our design floor grade, that red line across there. And, oh, there we go. It will add that in, so we now know that as that angle is increased, the depth of that hole has to be greater. We have to make sure that compensation is included in there, so that way we can make sure that we're pulling this thing down here through this grade right in here like that. And then again, as we put the additional holes in, we run into this in a lot of quarries where they have very problematic faces. And in a lot of cases, it could take 2 or 3 rows to get that back to vertical like you see up in here in cases like that. But the important thing about this is when we're looking at our blast design, if we have a specific burden and spacing that we're trying to cover, well, we need to make sure that we obtain that right in here so we can capture that. So once that design is done, we can further look at that in a little bit more detail as well. To check the angle of the hole, our recommendation is any angle holes should always be bore tracked. So you'd run the bore track probe down the hole, that would capture the deviation. We would see it on both the profile view and also the bullseye view. Then this survey would be incorporated into the as drilled, what we refer to as that as drilled model, and it would update it and show exactly where the deviation of that borehole is. So if it wandered off or it wandered together, any kind of combination like that, it's going to reflect that because any deviation off that could be quite critical for the potential for fly rock and air blasts, and of course performance-wise. But in the software, we can also look at it. If you're looking at our pattern here, here you can see the boreholes represented here. These are the measurements in between. And then we can look at that as kind of a heat map, and any of them that are closer are going to get reflected like we see here in red. And it's like a wafer view. You can take that plane and you look at it down at floor grade. You can look at it all the way up to the collar, each third of the meter all the way up through there. So what that's going to do is represent exactly where that borehole is in relation to the other boreholes around. So again, we've got the opportunity to custom load those boreholes so we don't have a situation where we've overloaded it or underloaded it. And where the performance comes in is if I'm trying to maintain a specific powder factor, in other words, a certain energy throughout that rock mass, that allows us to make those critical adjustments in there, and we can see this all before we go out there and hit the button. And that's one of the great things about this is we've got these tools in here that you can take a look at it and you can see what's going on with it. As we talked about with the borehole survey, once we've imported that in, now we've generated what we refer to as a true minimum burden. And the true minimum burden is exactly how it's drilled and its relationship to that quarry face, including the borehole deviation and the wander that we might be getting with that drill. Now, in some cases, the wander could be just changes in geology. It could be how the drill's operated. There's a whole host of things, but we've now captured it, and this becomes quite critical, both on the safety side and also on the performance side. So the way the software looks at what we refer to as a true minimum burden survey is every third of a meter down this hole, it looks spherically 360 degrees all around that whole entire borehole at that point. And what it does is it plots the lightest burden. It could be above, it could be off to the side, it could be below, it could be in any direction, and it plots that. It's important because we need to know and understand what is the lightest burden on that hole, because that's going to direct how we're going to go in there and load the explosives into that to ensure that we're going to have the safety and performance that we're looking for. So once we've run that, and it runs the plot, you're going to get a completely different looking profile than like the 2D. So here you can see, here's our 2D profile here, and here's the exact same hole, but this is reflected as a minimum burden profile. Now, this hole is still angled, like we talked about. It's still an angled hole, but keep in mind, this is generated by going up and down that borehole every third of a meter roughly, spherically looking around it and plotting that face all the way down through. Now, the lines that you see here, in this particular case, the burden was somewhere right around 4 meters. You can see here, the blue line here represents where it's overburdened, and the red line here is where it's underburdened. And as we were looking at this before, that area obviously really an area prone for a problem. So we want to pay close attention to what's going on with this, and this plot clearly shows it. So if we go out to do the blast, and I said, hey Scott, here's the 2D profile, and we need you to go in there and load this blast, but we've got this one hole, oops, right there, that we stood here with our 2D profiler, or we looked at a 2D CAD drawing of it, and it reflected that borehole right here. This is the profile, and I said, hey Scott, make sure you don't load anything less than 4 meters of burden on it. Well, if you look at that 2D view, you'd be inclined to load that hole all the way up to about 8 meters, about 8.3 meters from the collar. But if we take our minimum burden view here, where this is all plotted down here, looking at the lightest burden, 360 degrees around that hole, in fact, you wouldn't load that particular area, because we know we've got an extremely light burden in there, and you can see that right here, down and through there. On this particular borehole, you wouldn't load that column probably any higher than about roughly 17, 18 meters from the collar. Make sense? Oh, 2 minutes, geez, okay. So you can see why the minimum burden profile is so critical there. The major well drilling side, the drill output, the key thing with this is that it's the penetration rate, and a lot of the drill companies display it different ways, but the tool pressure, the air pressure, torque pressure, but what's really key in this is when we're looking at this, one, we're getting automated reporting. The operator in the cab tracks this, can make notes on that, so we got a report that can go to the blaster. So it still requires driller interaction on it, but we're getting very specific, detailed information. And the great thing about this is we now know how to load that hole, that if we've got the voids and the cavities and problems like that. So this is where we kind of have that subsurface view, what Scott had mentioned there before. We've got your hard, soft, fractured, overburden, and rock mass. So we would pick that up. So example, the drill's coming down through, the penetration rate is slow. If all of a sudden the penetration rate increases and our air drops off, what's that reflect? We've gone into a situation like this. We either have a cavity or maybe a seam. And of course, that's an area where more than likely we need to stem through that to make sure that we don't have any kind of problem there. The other one is on stemming and stemming adjustment here. In this particular case, in this area, the rock's solid, but you can clearly see in this zone here, they over-drilled and shot that whole area. So if you were to go in there and load that borehole and stem it the same, this area here is definitely going to be prone for fly rock and having problems there. And of course, it's really clear here. Look at the dirt. So, if you're holding the same amount of stemming as you've come along through there and you didn't account for this, this is where the major well drilling is really going to come in and help you out on the blasting safety side. So, tremendous amount of tools with this. The other one is the variable density in a case like this, that as you drill a hole, here you can see we got a significant difference in the geology in these areas. And capturing that through the major well drilling, that can go to the bulk truck so they know exactly how to go in and load each of these areas like we see here and make adjustments accordingly on it. So that way, we can custom tailor the load, where in some areas where maybe in this case we've got heavy bands of limestone, we need to hit that pretty hard. We've got some shale, we don't need to hit that all that hard. We got some sandstone in there, you're somewhere in between, things like that. We can custom load with that up there. Quality control, same thing. We can capture those zones where it might be material that could be a problem for us. On the loader side, same thing here. We can take the technology, put it on the loader, so in the cab, they can track it. Same thing, they put the hardware on it. We've got the GPS on top of the unit. It knows where it's at, it tracks it, and The great thing about that is the benefits we get is, one, the operator can maintain those elevations that we put in there. They're looking at a cut fill on that tablet in there, and especially where in a lot of cases you've got a pretty good turnover of operators. You can put somebody in that cab and they can see right there, am I high, am I low? What adjustments do I need to make? And in case you can even dial in, say for example, like a slope, if you're trying to, for water down to a sump and things along those lines. But it provides a significant amount of information to the operator, but it's also mapping your quarry the whole time it's running. And all that's uploaded, goes into your maps, and updates all that. Here you can see, the screen on grade. Right here's your gauge, and you can set your variance on that. Here's your top view so they can see exactly where they're at in the world. And the other thing that's kind of unique about it is, say you have a hazard, maybe it was a potential misfired area. You can actually load that in there, and as the operator gets by, it comes up and notifies them they're in an area that there's a potential safety problem with that. So I guess it's probably good. Time-wise, 2 minutes? Oh, okay, very good. All right. So one of the things with the tracking of all this, with like an aftermarket type setup like this, we've got centralized tracking of all the equipment. We can capture all these KPIs, but we can look at the drills, we can look at loaders, we can also look at the haul trucks. And one of the advantages that we've seen with that is you might have different manufacturers of all this different equipment. They all have their unique and proprietary systems. This overrides all of it. We can centralize it and have all that equipment report back into one centralized site where we can track all these pieces of equipment, and we can generate an ortho map, and we can have that all reflected there.
Are there any questions for Bob on this fascinating presentation on accuracy? Whilst you're thinking, we've got one question on the app, Bob, and maybe, one of the things, notes here, I'll just walk you through it. The question really is concerning, it's fantastic outcomes that we have here, and the question has got to do with, so when, a quarry or a mine migrates over to an advanced system like this, are there any lessons learned or considerations with regards to, change management and, more particularly involving the operators, on the bench moving to a system like this?
Yeah, first of all, it's the finance guy, the one who writes the check. He's like, well, what's the value? And like we talked about earlier, it's the downstream value. You've got to keep that in mind. You can't just nickel and dime that, this booster costs this, that booster costs. You're never going to get there. So it's the downstream value with that and making sure that mindset is there. On the operators, there were a few drillers that weren't real happy. They thought it was something that was watching them, But they soon learned that there was a significant value to it. And the same with the loader operators. It was quite interesting because, when you get up in a 992 cat loader in the middle of the night and you're trying to maintain a level floor, that's a challenge. And those guys, after they got them in there and they saw that on the tablets, they're like, wow, this thing's helpful. And you could see the improvements in the areas of the quarry where they didn't do any of this and they had moved over to a different section. And clearly there's a visual, as soon as you pull in there, you can see it. And the main thing is maintaining that proper grade and getting those cuts right, even though the terrain varied quite a bit. And some of these quarries look like it's pretty flat, but it's not. You still have changes in it. And once everybody understood the value it brought and then saw it, these guys have bought into it big time. Management really liked it because they saw a return right away with it, with that kind of benefit. And then just being able to increase shot sizes and things like that was huge.
Fantastic.
But, it's like anything new. Who wants to try something new if I have something I'm doing every day and it's working,
Yes,
but most of them adopted to it. But, there's always a few that...
But it sounds like socializing the results. And making sure everybody understands the benefit.
It helps.
Helps you build momentum in such endeavors.
They see it, and I can tell you, we put some over on the East Coast, and the thing that those guys recognize is they weren't getting beat to death running loaders. Before, the floor was like this, and just to drive over it was a nightmare, and you know, now they got this thing just as flat as can be.
Excellent.
So they see the benefits, and then they're like, hey, this makes sense. Yeah, okay, let's,
Fantastic.
we're on board with it, so.
Fantastic.
But
No further questions for Bob? Thank you.
Thank you very
Thank you
much.
very much, and well done.
Thanks.
Thanks, Lungi.
Great. Is my mic on? No? Thank you. Next, we have a systems thinker and tech leader who believes collaboration is key. Alan Toder is the Director of Mining Tech and Portfolio Integration at Mining 3 and describes himself as an enthusiastic and energetic mining engineer with extensive experience in operations, R&D, and leadership across a wide range of commodities. As a systems thinker, he champions interdisciplinary collaboration to unlock innovation and deliver sustainable value. Please welcome on stage Alan, talking to us about transforming mining through technology and collaboration. Please welcome. Thank you.
Sani Bonani, Dumaleng, Goeiedag, how's it? It's great to be back in South Africa. It's been 3 years. It's wonderful to be surrounded by many, many known faces and many new faces as well. I'd like to extend my gratitude, my sincere gratitude to BME for the invitation to be here with you today. I think it's a true pleasure, and I really look forward to the collaboration and the conversations that we will have, but also, you know, the discussions that we've had so far. They've been fascinating. Apparently this is a bit of a challenge, so just bear with me. Thank you. It's clearly the other way. Right, there we go. So many of you might know me. Or you might know me from my previous role. I was the head of Drill and Blast, global head of Drill and Blast for Anglo American for 8 years. I've finished with Anglo in 2023, so that's, I guess, my past life. Subsequently to that, I've moved to Mining 3, which is an organization based out of Australia. It's a non-profit, but basically what we try and do is accelerate technologies into the mining industry. We do this through technology development with our partners. We do this with advisory services back into industry. And also, quite importantly, is when we do find the right partners and we do identify those opportunities, we build consortia through that. So we look to matchmake, and sort of internally, there's been a bit of a joke that we're the Tinder for mining industry. We try and bring the right people into the room to have a conversation and ultimately deliver solutions that are beneficial for the value drivers. Thomas, in his conversation earlier, or in his talk earlier, mentioned that mining is not going away, and it is the foundation for modern society. So the harsh reality is that we are going through a pivotal change, I guess, in our history as human beings, and that's being driven mainly by the energy transition. So we're going to need many more metals. We're going to need much more mining at significant scales. Military defense, so we've seen that with Ukraine and the wars around the world. Armies are restocking their supplies. Supply chain resilience and global political risk. So we're seeing a shift in that, which is now driving sovereignty in many of the countries, and that demand for the metal trading. Environmental and social pressures are put onto the industry. Infrastructure and urbanization, and of course digital infrastructure and AI is all going to require a significant amount more metals in the years to come. So we've got a bit of a burning platform, and the global demand out of these critical minerals is expected to completely outstrip supply. Right? If we look at the graphs on the bottom, the critical minerals down here, so copper, lithium, nickel, cobalt, graphite, and rare earths, to name a few, you can see that it's anywhere between 2 to 4%, times more what we're currently producing today over the coming years. So that's significant. That's going to put significant pressure on everyone in this room and basically our industry. If we look at the precious metals, so again, recognizing that South Africa, we've got the PGEs, we've got gold. Again, if we look at that trajectory of where it's going, there's going to be significant demand as well. So that's good news. It's, keeps us in a job. But equally, we also have to deliver not only just the tons, but we now have those social responsibility targets that we have to meet, the environmental targets that we have to meet, corporate telling you that you have to adopt new technologies because that's what's going to drive this change. And all of these pressures are now going to basically give us a burning platform. To put it in another perspective, if that didn't hit home, if we just look at copper specifically, and to meet the 2050 emissions targets, right, that have been set from a global climate change perspective, we as an industry have to produce, in the next 22 years, the equivalent of what mankind has ever produced in its entire history. Okay? So that same volume, that same tonnage has to be produced in the next 22 years. Okay, so I'll let you guys do the math as to whether that's actually possible or not, but that's a separate conversation. So that just kind of gives, hits home the urgency. This graph should talk to, many of you. You'll know this, you live and breathe this on a day-to-day basis, but it's basically the rock to metal ratio, right? And that's how much rock, how much waste we have to move to actually generate a ton of metal. So if we look at copper as an example, for 1 ton, if you look at 1 ton's about a small car, just to put it in perspective, right, if you had to lift it up, we get about 5 kilos of pure copper from 1 ton of rock, 1 ton of ore, okay? 5 kilos bowling ball, sort of a fire extinguisher. If we look at cobalt, it gets a little bit worse. You get, for 1 ton, you get 1 to 2 kilos of copper, which is basically a laptop or a pineapple. And if we look at PGEs, we then have 3 to 6 grams, right, which is significantly different, which is basically a sheet of A4 paper or a raisin, right, for 1 ton. So again, we're actually in the industry of not producing metals, we're actually in the industry of digging waste and moving waste, right? And that comes at cost. And as we get bigger and as we're required to deliver more, we see that our grades of our pits and our ore bodies are going down. So that means there's more waste that we have to move for less metal. And again, if we look at the demand curves for the various different things, that's going up. So fundamentally, the way we do business today has to change, okay? To couple that, right, just to add another paper cut to the mix, if we look at the amount of discoveries, this is copper specifically, there's a lot of data on copper, unfortunately there's less on other metals, but over the last, sort of 20 to 30 years, we have seen a significant drop in terms of the discoveries, the brownfield discoveries of major copper deposits around the world. So the Bingham Canyons, the Escondidas, Los Bronces, they've gone, or we're not finding them, right? So again, the pressure on the existing assets that are here today have to be able to produce those metals from a raw perspective. Companies are now also doing less greenfields exploration. So if we go back to 1979, it was about 50% of greenfields exploration. They were sending those rigs out and they were looking for ore bodies. Today, they've basically reduced that down to less than 20, and they're basically exploring more around the existing assets in today. So we're not finding these big ore bodies, okay? Excuse me. We're seeing this coming through with the capital expenditure that companies are spending. So, that's investment in technology and investment in infrastructure. So that's significantly going up, and that's for all major mining companies around the world. And I guess this to me is an important message, because what it's telling us is that the companies are investing in technologies because they believe that it can leverage that opportunity to unlock, I guess, the value that's in the ground. So the scale of mining as we know it today is going to dwarf, the scale of mining tomorrow is going to dwarf what we know today. It's going to change. It is changing. We're seeing that. And to meet that demand, we're going to have to adopt technologies, right? And we've had some very good presentations today around technologies that exist in the field today. We know some stuff that's coming in the pipeline, and there will be some more breakthrough technologies that will come about in the next few years. But we need to be better at actually adopting technologies. We can't wait. There was a great question, I think, to Tom earlier, which is, how long does it take for technology to actually be implemented and become sustainable on a mine site? And I've got a graph that talks to that. But we need to be better at actually unlocking these technologies. And that has to happen through better insights into the enablers. And that only happens through collaboration with, I guess, our peers up and downstream of the value chain. So just to talk a few, and specifically I think from a drill and blast perspective, we've heard today around initiating systems, significant breakthrough with the onset of wireless. That is really going to unlock some key potential and some great opportunities. We've had some really good conversations in terms of understanding how improved accuracy can actually deliver better results. But now take that a step further, where you can now start drilling a hole well in advance, charging it, and then leaving it for a while, and then when the time is right, you then fire it. So these technologies exist today. There's more technologies coming in that space, and I think that this is going to be an absolute game changer. Digital AI, we heard Strauss and Bob just now talk about, I guess, amassing that information and being able to proactively make decisions. That's huge. So again, I think there was a slide that said garbage in, garbage out, 100%. So we need to make sure that the way we manage our digital information is an equal asset as, I guess, your drill rig, right? Automation, that's coming, and it's not, I generally don't believe that it's to remove people, but I think it will reduce the variability, and people still drive that. So I think that's again, another game changer and enabler. Integrated operating systems, so how do we now have take all of this information that we have, and how do we do stuff proactively? How do we link in, upstream, downstream, and that whole value chain to essentially optimize the operation, not the process? And we've heard about, the various different bulk explosives that are being produced to market and how they can enable and be fit for purpose for the conditions. So all of this technology is coming along. What we need to do is be able to stack it, right, and leverage each component and the value add that it can deliver to actually give us step change, which is what I think. The next few slides are really to talk about, I guess, the pathway to adoption of technology. And I guess this is what I really want to impress on you. And if there's anything that I leave you here today, it's the next few slides. I'm not going to talk technical, I'm not going to talk drill and blast, but I'm going to try and instill or ask you to go away today and think about, in your roles, how is it that you enable or constrain the adoption of certain technologies? Okay, and technology is not just a detonator. It could be a process. It's not just a data collection point, a sensor. It's also how we collaborate in that system. As an example, mine to mill. So there's this thing called the technology hype cycle. It goes through a series of phases. The first bit is the innovation trigger. So that's when someone has this aha moment and they go, have I got the silver bullet that will solve all problems? And they go away and they invent it, and it builds a bit of traction. And that's great. Then you get the peak of inflated expectations. And for those of you in the crowd that are in the marketing business, I'm kind of looking at you and kind of, if we can dumb that down a little bit, because there's often this big expectation that, this technology will solve the world's problems. And everyone then buys into it and they believe it, and, hey ho, we go off on that journey, and then all of a sudden we implement it and it goes to, well, the proverbial, right? And we get into the trough of disillusionment, where we kind of go, this doesn't work, or it's, increased my safety risk, or, whatever, we don't like it. And then slowly over time, we get into the slope of enlightenment, where we start creeping out of it and we kind of see, okay, this starts working, and eventually that technology lands and it becomes, the plateau of productivity, and it becomes embedded. So it goes through this life cycle, and it's a stark reminder, and I specifically put this up there because I want you to understand that when you go through any adoption, whether it's a process change or a technology adoption, you will go through this drop by default, right? So it's just a matter of how well you manage it and to get out to the other side. This slide is the hype cycle, but it was a Senko drew it. I really like it because it's 2018, so it's old. So a lot of the technologies at the time were on there and they plotted it. Now, if we just look at 3 specific examples, right? We're going to look at drones, we're going to look at connected mine, and we're going to look at autonomous haulage or autonomous vehicles, right? And just have a bit of a case study. So drones, at the time, was sitting in the trough of disillusionment, right? And people were basically saying, these things don't fly, they don't work, and it's great, it's wonderful, but it's pie in the sky stuff. I would argue that today, sort of they've come through, and we're actually, we've had a lot of presentations today that actually talk about drones and talk about how, and we know how to use them, we know how to integrate them into our processes. If we look at autonomous vehicles, again, we're kind of coming out of that. I would argue that, some operations, yes, they're in the plateau of productivity, but as an industry, I don't think we're quite there yet, but we recognize that there is that potential, and it's just a matter of, sort of transitioning into it. And then you've got the connected mine, right, which is, all the data, it's all integrated. We heard Strios today. But I think we're kind of further down that curve. We're not there yet. We recognize that there's that potential, but we're kind of disillusioned by the fact that, this system doesn't plug into there and it doesn't give me the answer and I still need to train it and I still need to do all of this. But I would argue that there's, patience, and we collectively need to enable that to actually bring it out of that trough. So now you couple the hype life cycle with something called the technology adoption life cycle, okay? And that's basically a distribution, and again, you've got your innovators, right? And they're a small percentage over time. Then you get the chasm, which is that big drop, and everyone throws up their hands and walks away, and there's a few people that persevere, and you get the early adopters, right? And at some point in time, you then get the early majority, right? And this is really where, I guess, OEMs, SMEs really start seeing that their products sort of gain weight, and they actually start, delivering and they get the sales. You then get the late majority, which is sort of a tail end, and then the laggards who are just, so slow that they've almost missed the boat. So you got this beautiful distribution. So I thought I would go and I'd do a few drill and blast specific case studies, and I've used conferences dating back to 1975. Drill and blast conferences specifically, but I've also looked at a few others outside of drill and blast. I've done a little bit more than just a word search, but basically my hypothesis was, can I look at the adoption hype cycle and the distribution by using as a proxy the number of papers that are written around these different technologies, right? Because essentially what is a conference? I get up here, I present my case study because aren't I great? I adopted Thomas's new product, and, it works, and ta-da, aren't I wonderful? And I basically sell it to you guys as I'm the first person to do it. Well, the reality is I'm not, and, I think the more papers you see ultimately gives us that indication of how much pull there is from industry. So the first one is non-ELs. Great, it's on that screen it's cut off halfway. Look, there's a bit of flex here, but non-ELs basically 1973, and I'm prepared to be challenged on that one, but 1973 is when they really became commercially available. South African products. May I remind you that it was actually South Africa that didn't necessarily invent it, but took it into industry. And if we look at, sorry, giving the game away there. If you look at basically the life cycle, you had a few papers that were talking about it. This is in the one and twos. You then see sort of around there, you start seeing a trend that starts coming up a bit. 1990, we then start seeing this peak, and then we kind of see it tapering off. Now, for some reason, back in the 2025s, the 20s, we're now seeing a reemergence, but I think a lot of those papers are now the comparison of non-ELs with EDDs, okay? But, I think this beautifully demonstrates it. So, if we were to say that we want to get to as the majority, the early majority is really where we want to get to from an industry perspective. In this case here, it took 18 years from commercialization for the early majority to actually start and ramping up. If we have 22 years to deliver as many tons as we've ever produced in copper, this can't work, right? If we want to curb our emissions, this can't work. If we want to improve our safety, this can't work. So we have to get better at that. Let's look at EDDs. Similar story. So it was in the early 90s that they became commercially viable, or commercially available. And we saw sort of a trend. This one is a little bit more, I guess you kind of have to close one eye and tilt your head. But if we look at, unfortunately, I do have a bit of a gap in terms of the proceedings in that space to be able to do analysis, but I would project that we would see significantly more papers in that time. but it took 13 years to get to the early majority. It's not just limited to, I guess, technologies or hardwired stuff. It's mine-to-mill as a concept. Mine-to-mill in the 90s, the modern mine-to-mill terminology came out, which was, using chemical energy, explosives, to fragment the rock better so that we could get improvements through the mill. And again, you kind of see that trend happening, that in 2010 to 2015, we start seeing that emergence, okay? And that was, again, 12 years, okay? So it's taking anywhere between 10 and 20 years, 10 and 15 years to start adopting and seeing that pull from industry. So my question is, all right, the technologies that were presented today, right, and the technologies that are on the table today that can unlock serious value, like how long is it going to take, for wireless as an example, to actually become a reality and add that value that it can add to your operations? Is it 12 years? 10 years? 5 years? What do we want? And I think that really sort of then talks to, and how we drive the change is really through what's called the solo paradox, or the J curve. So bear with me as I walk you through this, but you've got your current state, right? Your operations today, right? And some bright person, corporate, innovator, marketer comes along and tells you and sells you this idea, and they say, look, we can get you from here to your desired state, right? And there's a sustainable, tangible benefit. And this is true. This is quantifiable, and this is measured, and this is reality. There's a value add. But what a lot of people make the mistake of is and then you do this over a transition period, okay? What a lot of people misestimate is that you go from here to here in that trajectory. We think that we will realize it, that Monday week, when we start implementing this technology, we'll see that benefit. The harsh reality is that this is what happens. And you get this decrease in productivity, or you get this adverse performance impact. And that's not just productivity, it could be a safety incident. It could be an increase in cost. There's a whole heap of things that basically your value drivers, your KPIs, all of a sudden get hammered because you're having to change the process. And I think it's the lack of recognition around this that is what puts us in the trough of disillusionment, and people go, no, I'm out. My KPI says I need to produce a ton. I've always done it this way, so therefore I know how to do it. I'm going to go back to doing that. And we don't actually enable the process and allow ourselves the opportunity to work through that technology. So yourselves in the room, basically, number one, recognize this. Know that it's coming, right? When you're changing a process or changing a technology, know that this is coming and design into it, right? Because if you design into it, you can then start managing it. It will be there. You will get a decrease in productivity. But I think understanding that will enable you to actually manage it and reduce that significantly, and I guess ultimately manage up, down, and sideways as you need to. So where to from here? I guess the key considerations, and these are some of them, that there's multiple of them, but again, this is where I talk about the collaboration. This is where I talk about, having to integrate and understand the guys in your adjacent swim lanes, right? So as drill and blast practitioners, what we do is we show up very early in the morning, we go and we see that the driller hasn't drilled a hole. We pump some snot down it, we then stand on the midday sun, get sunburnt, have a horrible time, fire the button and go home. But if we start understanding the actual, implications of the downstream, the milling operations, or we understand the geology, as Bob talked about, that then becomes a serious enabler to our operations as drill and blast, and actually delivers our value that we can do. So from a technical perspective, and that's what we're technical people, we need to keep it technically simple. But as Bob pointed out, there's complexity in that, right? It's not simple for the simple sake. It's keeping it a complex problem as simple as possible, okay? And it's understanding that. From a risk perspective, understanding the characteristics that around that risk. And risk is not just health and safety. Risk is to production. Risk is to your financial, your cost sheets. Risk is to, annoying the neighbors with your vibrations. Risk is everything. Risk to business. So understanding that in context really will help you make sure that you are implementing that technology effectively. Regulatory. So I'm really, really glad to hear that we've got, our regulators in the house today. So they play a key part, and they're not the enemy. If anything, they're our friends, right? We need to work with them. We need them to understand what this technology can do, And ultimately, regulatory is not just the government or, sort of them. It's also the standards that the organization sets, your procedures, right? It's making sure that we work within certain bounds to deliver certain outcomes. Organizational structure, it's just the HR guys. No, we need to be upskilling them. We need to be enabling HR to understand what are the training packages that we need, what are the new skill sets that we need to actually adopt these technologies and these processes. Operating model, right? So every organization has an operating model. In some cases, it's a buzzword, but it's how do you align your operating objectives with the appropriate KPIs and the effective means of monitoring those to actually drive that change and sustain that change. And then ultimately, your stakeholders, whether it's the CEO, whether it's someone external, whether it's internal, whether it's your shareholders, identifying and enabling them to support the process is key. So when you go through that, sort of curve of decrease in productivity, they're informed and they understand that, and they almost give the grace. You need to get out of it as quickly as possible, but equally they've got to understand that and they've got to work with you. So I think this is, probably talks to, at least this was one of my biggest frustrations, is that we would get there and we'd be so close yet so far. The bridge just did not get together. So what is really needed, right? And I guess to achieve these goals, I believe that we need shared language and a shared understanding, right? And that's collectively, whether it's, your OEMs, your suppliers, and yourself as a mine site, or whether it's your manager and the guy on the ground. We need a shared language. We need to understand. One of the biggest lessons I learned as a drill and blast guy was fragmentation and coarse fragmentation. Now, to us, coarse fragmentation is, a rock the size of this stage. Coarse fragmentation to someone in the grinding or downstream, is microns or is centimeters. So if I just say coarse fragmentation to them, they're straight away hearing centimeter or, sort of fist size, which does not equate. Fist size to us is great, right? So it's, again, understanding and having that shared language. Cross-functional translators, so people that can actually have these conversations and translate through those systems so that we actually unlock and understand how we enable each other or enable these technologies. Commercial models for collaboration, right? At the end of the day, if we look at mine to mill, why is mine to mill? It's an operating philosophy. It's not a technology. It's not something that you do. And in many cases, they're case studies. Ta-da! We've improved fragmentation. Yay! And then we go away. The issue there is your mine manager is driven by his budget, and he's told to minimize his drill budget, as opposed to maximize his drill budget. Right? Buy more explosives so that you fragment it, because the cost of grinding it is significantly higher. So the operation benefits by increasing your powder factors or your energy distributions, rather than sort of trying to manage each one of those in silos. Pilot infrastructure and funding, I think, is really relevant where these case studies. I don't know how many of you guys have a new technology and then you have to trial it, right? You have to see it for yourselves on your mine site. Yes, there's an element of that, but you don't have to reinvent the wheel. Like we know, as an example, Hypex Bio works. You can go to Europe, you can fly there today, and you can see blasts, right? They've commercially deployed it. Whilst it needs to be seen here in Africa, it doesn't need to be repeated every single time for every single person, right? That's a delay. So how do we get case studies into the hands of those people so they can very quickly adopt it, understand it, and move on? Regulatory clarity, right? So we hear that there's clashes between, the understanding and sort of understanding, working with our regulators to actually make sure that we deliver it. And that's, again, having the collective conversations. And strategic alignment, right? What is it that ultimately is driving the value? The risks of not doing this: your designs continue to not meet real-world conditions. We've heard that today. Innovation stagnation, so companies just put up their hands and say, we're not going to innovate anymore. And you get duplication of effort. So I think I'll conclude with the next two slides, but technology does offer us a pathway to address real change. It's there. It's on the shelf today. We don't have to wait for tomorrow's widget to be invented. There's so much technology and so much process change that can happen today that will unlock significant value. We've heard it. We just need to enable it. And I guess that impact will only come through intentional design and collaborative implementation. It won't happen otherwise. So on that note, I just, ask you, challenge you guys, are you guys the supporters? Do you want to leave here today as the supporters of transformation? Or do you want to be the bystanders of delay and missed opportunity? Because I think that's really what it comes down to. And I think all of you in this room, in your roles, whatever they may be, have that power to drive that change and have that opportunity to collaborate and speak to, I guess, your value chain neighbors. I'll end on that. Thank you. And, take some questions.
Thank you so much, Dr. Allen. You've given us a lot of food for thought. Definitely things that we need to go back and think about. How are we adopting the technology? How are we using it? What do we need to be ready to use that technology in our work? We've only received one question so far, so I think we will still open it up to the floor. But the first question is, with grades reducing and demand increasing, how strongly is the world's recycling and circular economies keeping up to compensate for production?
That's a great question. That is not my area of expertise, but it is something that I guess in Mining 3 we're talking about, and we're working with various different organizations. I was in a workshop a few weeks ago around biomining, of all things, and there was a slide, there was a conversation that fundamental mining will still need to be produced. Like, we will still need to add to the existing. Recycling and recirculation will only give us so much, but the demand for what we need today is increasing, right? So again, if we just go back to that copper graph, right, the same amount of copper that we have ever produced is going to be needed. We need to double that production because of the requirements of whether it's the energy transition, whether it's the military and defense rearmament, whether it's digital and AI, so that's all going to require these metals. So yeah, there's an element of it. It could reduce it slightly. I don't have a number for you, but we will still need to fundamentally produce from, I guess, natural resources.
Perfect. Thank you. Is there any other question?
There's one just up here.
Oh, there you
Hi.
go. You just press the green. There you go.
Good day, everyone. My name is Oscar. My surname is Mola. My company is Sufficient Grace Trading. My question is that is it your technology, this technology cost effective, where junior miners, SMMEs can be affording? Because lots of technology that are coming abroad are afforded by those big companies that I want the space. You get small companies, they want to absorb this technology, but the problem is that the cost is too much to get it, to put in place.
I think that's a great question and a great challenge back to, I guess, the suppliers and the people that ultimately develop these technologies. I'm going to try and answer this in a few ways, and I'm not going to say that this is particularly the right answer, but any technology needs capital, and obviously, majority of business is not a charity, right? So they need to recap that capital. So whilst I think that the big organizations, and that's where the selling point is, and that the hype cycle, right, the peak of sort of expectations is really to drive that pull. But I agree. I think smaller companies have to or do run much tighter budgets. And if the pathway to getting the return is through volume, the quicker you can get case studies out there, the quicker you can get people to buy into it and understand that this actually works and get you through those life cycles, I believe the quicker you are to actually get greater scale adoption. So whilst I don't sit in a company that makes these decisions, I would encourage the idea of looking at working with smaller companies, trying to find ways to, I guess, if you will, subsidize that and get those case studies, those proof of concepts delivered quickly, but then also out into the market. So there might be a conversation, I don't know, and I'm thinking off the top of my head here, but there might be a conversation that might be, okay, we can subsidize that for you, but in return we get publication and we get the opportunity to actually market this at scale, and we might need to change a few processes within your organization to actually make sure that it works. Right, so it becomes this win-win, it becomes a collaborative partnership to actually do that, because then it's a win-win. right? Because then the company's getting that pull. I mean, I'm looking at two CEOs over here. I don't know, they might be sitting there going, Alan, no, it doesn't work that way. Don't know, that's why I'm not a CEO. But, to me, I think there's opportunities. I think we can think creatively around finding this. But at the end of the day, it's about finding the value drivers that drive the various different businesses.
Great.
Sorry, I've got a question. Hi.
Sure.
It's Gerard from Glencore. That J-curve really interests me a lot. And I've seen it with so many products, particularly in mining, because suppliers believe that the mines have got endless pockets and very deep pockets that they can just pay. And they bring a wonderful product to the market. And I'll just use this wireless debts as an example. A wireless debt, I was quoted, I could buy a smartphone for less money.
Mm-hmm.
Okay, than blowing up, it's like blowing up a smartphone every hole.
Yep.
It's insane. I mean, I know it's technology, I've tried it, we've run a blast, it's great, but it's not going to work, not at that price. There's a should price for everything, and I think it's the first time I've seen it explained like it, but now I can understand. It's when the actual price reaches the should price of the product, that's when we'll buy it, and it will flourish. And some products I've seen where the inventors just will not budge on the price. I mean, the actual input costs of some products are pennies, and 20 years later it comes back to the market, and there's a product that's just happened. It comes back to the market at literally a few bucks, and we adopt it and it works.
Yep. No, look, I think there's a few elements to that, and thank you for raising that, Jared. I think it's a very valuable point, and I think it talks to our colleague over here as well. You have to recap your capital and your development costs, right? And obviously there's a timeline to do that. So whilst you're bringing new technology and you're accelerating that technology through the technology readiness level, so the TRLs, it costs money, right? And you need those early adopters to allow you to fail so that you can go back to your lab to tinker away and pay someone to actually fix it a little bit. And it fails again, right? And I guess this is where the paradigm and the paradox is. You're on site to deliver tons. You're not there to be a test ground or a lab, right? So you want it to work from day one, right? Which is the expectation that you jump straight from, up in the red line. But understanding that and getting that grace to be able to find ways then increases the volume, increases the confidence in using that, increasing the volume, then decreases the price, right? So we kind of get into this kind of circular spin. And I think that's what I believe is why we have those dips and why we have those chasms of, it's kind of, don't come here, come, in 20 years' time. But I think by having these conversations, being transparent with each other, and sort of finding creative ways to actually have true partnerships. And it's not, and I know drill and blast industry is very, sort of cloak and daggers, but we all know each other's secrets, right? So if there was, and maybe I'm being a little bit too philosophical now, but if there was better collaboration and better understanding for the value drivers that all companies are now signed up for, it's not just the bottom line. The bottom line is what drives the business at the end of the day, 100%. But we also have to bring in, the ESG targets. We also have to bring in the safety targets. We also have to adopt technologies. We also have to, social license to operate, and on and on and on and on. All of these value drivers, you can't measure in dollars. So therefore, they become kind of deprioritized when it is, and I would argue, 100% right, it's dropping a cell phone down a hole. But if, and I'm not saying that it does, but if that could unlock other value drivers that are not dollar or rand specific, but we could quantify in a similar way, you potentially could have justification to drop a cell phone down every hole, right? So it's about reframing that and understanding, I guess, the greater context, and that's the conversations that we're not having, in my opinion. Anyway.
Thank you.
Anyone else? Can I go?
No, you may not.
Oh, no,
please
I gotta
stay
go.
on stage.
Right.
A huge round of applause for Dr. Allen, please. All right. Now we're going to be switching things up a little bit. I'll hand over to Dirk to introduce our next section.
Thanks, Lungi. Appreciate it. And Alan, I don't know if you want to just grab a glass of water. You're okay, but please stay on the stage or don't go too far. I'm also going to ask Nishan, Thomas, and Bob if you won't please join us. You've all given us very insightful presentations around technology. And as Lungi has said, we want to mix things up a little bit. So for our next session, we're going to have a panel discussion. And I'll share the topic with you just now, but again, I'd like you to just turn to your, what's that thing we've dropped down the hole?
Cell phone.
The cell phone there, the smartphone. On our app, there is also a poll. So asking a couple of questions around the session that we're going to have just now. And we'd love to have your feedback on that. So Nishan is going to guide our panel through a discussion here. And the topic that we will be exploring is looking at disruptive technology in mining, and there was quite an interesting discussion developing here. Innovation versus resistance. So Nishan, with that, over to you and our panel. Looking forward to the discussion.
Thank you, Dirk. Thank you, team. Thank you, guys.
Thank you.
Wow, we've had some fantastic conversations, fantastic presentations, stimulating questions, almost driving us off stage. But yeah, I think it's important questions that needs to be had, and I think in keeping with the theme of today, we're talking disruptive technology in mining, we're talking innovation, we're seeing resistance. So the question is, are we breaking barriers or are we building walls? And I think to unpack that, we'll go through two sections in terms of the question set. So Thomas, I'm going to ask you first. So this panel sits squarely in the area that Hypex Bio operates, or you currently find yourself in. Your topic, moving mountains with innovation, hinges on Hypex Bio's ability to deliver an alternative technology that still needs to be improved in some markets, but proven in others, right? But you also need to prove that it achieves equal and or better outcomes than what the conventional products are. Can you take us through maybe the company's drive to apply this HPE technology, this disruptive technology, in the industry? What were some of the challenges you faced, and how did you overcome them?
So first of all, I've been doing explosives development and research for about 20 years, mainly for explosive companies, and historically, I ended up in various projects, normally by chance. A friend of a friend contacted me with an issue and something like that. So historically, it's always been issue-driven. There was an issue that needed to be resolved, and you're trying to fix it, even if it's operational specific, if it's strategic or something else. So my work historically has always been to resolve a problem that has arisen, right? And when there is a problem, the value is very clear. There's a problem. There's a stop somewhere, or there's too big of blocks in a block cave or something like this. So the value is very clear. And when you end up in those situations, you don't really discuss money, you discuss value. Value and money, two very different things. We're going to go back to that. So, and I also need to say in this context that we talk about mining like it's one type of entity. That's not the case. Every mining company is different. Every person in that company is different. So I would say it's unfair to push all the mining companies over, one edge. There are people, out there willing to discuss and willing to engage. It's absolutely true. And it's different in some regions and it's more easier in others. But throughout that journey, the type of questions we got was very often around things like re-entry or on-shift blasting or nitrate mitigation. It's very, very clear that, the value chain of mining it starts with the drilling and then the blasting. And a lot of issues arose with the blasting, and you, Bob, talked a lot about the drilling, but from a blasting perspective, the use of the products we have, they lead to a lot of issues. And I've always been I'm a very curious person. So I took it as a challenge, like out of curiosity, can we solve this? But as the curiosity transformed and we we realized, holy heck, we can actually do something about this. And we developed something that, okay, this actually can solve this problem. It became more of a moral driver. Now we have a concept where we're morally, let's say, entrusted to see if we can take this all the way. Because it's a really good thing for the mines, it's a really good thing for the planet, and hopefully it's a good thing for us as well as a business. It can be a win-win. So I think it's started by curiosity, spawned by a very clear value position, driven from these questions from the mines, and then throughout step-by-step research, we managed to see that we can do something about it. And to your question regarding challenges, I think the challenge is obviously to find the first entry, convincing somebody, hey, I need to do some off-the-bat testing in your mind. That's not normally how I present it, but that's really what it is. Like we have this really novel explosive, we want to do some test blasts in your mind, and we just want to prove it's safe. And the first question you say is, okay, so it's not safe now, right? So explaining the explosives development process step by step, very small scale, a lot of testing before we do the blasting, being able to connect with the right people, developing in-house testing protocols and showcasing every step of the way, and explaining and convincing people of the process. So that's really how we managed to get into the mines, and then, as I said, scale it up from. I remember the first blast I ever did with hydrogen peroxide emulsion, we blasted a 2 cubic meter boulder. That's it. We spent a week to achieve a boulder blast. That's it. We put a container lab at the mine to produce that emulsion, and we did all the safety tests to get it underground, and we blasted a boulder. It took 20 minutes to blast the boulder. But after that, we blasted some cuts. We pulled the cuts. After that, we blasted half a face, and then a full face. And so step by step, proving by data, by results that this works. And then obviously optimization comes after.
No, thanks, Thomas. I mean, that's a great segue into Alan. I'm going to ask you a question next. And the point on cost versus value, I think it also talks to the two questions we had in the audience today, understanding what the cost really is and what the value you're trying to achieve. Because unit by unit comparison, you're going to lose if you look at the higher technology aspect. Yeah. So Alan, on that point, the transformation of mining processes through technology and collaboration has been proven to deliver substantial benefits in efficiency, productivity, cost reduction, and we've seen that technology plays a fantastic aspect in achieving that. Yet the industry continues to experience slow progression, or rather pockets of adoption. I mean, the slide you had on non-ELs, 18 years, electronic initiating systems, 13 years, mine to mill, 12 years. Once you frame it on that roadmap, it hits hard. Right? So in your view, why does this resistance or slow progression persist?
Anyone? Help me out here. Yeah, look, Nishan, I think it's a combination of a whole heap of stuff, right? So a technology evolves, right? You have a prototype, it's what Thomas just talked to. It's, you can come to my site, but you'll start small, and you start small and something doesn't work, or, you tinker and you can optimize, you need to go back, and you go through this iterative process, and that takes time. And I think through that, people's confidence increases if you deliver it, but people's confidence decreases if you don't, right? But that doesn't mean that the fundamentals or the concept isn't valid. So I think it's really, so on a one-on-one conversation, I think you can develop that relationship with your stakeholder. Unfortunately, that individual stakeholder then has multiple, stakeholders themselves, or, stakeholders, shareholders. If we look at an organization, right, value is dollars. Value is, at the end of the day, the bottom line. How much money are we making? But there's pressures, social license to operate. How do you put a dollar value, unless you shut the mine down, it's very difficult to put a dollar value on vibrations. It's very difficult to put a dollar value on emissions. It's very hard to put a dollar value on, nitrate loading on, yes, there's regulatory fines, but it's that disconnect between what we know how to measure and what we measure on a regular basis, and everyone in this room is measured on productivity in some shape or form, which is a dollar value. We kind of default to that. And I think it takes time for people to then come around and see the new value that a technology can add. You know, that is not necessarily just dollar. I mean, Gerrit gave a good point. It's going to cost me a mobile phone. True. But if that mobile phone then eliminates, and I'm just going to throw it out here just as a crazy idea, right? But, you know, eliminates all potential for annoying Mrs. Jones's house from vibrations and allows you to fire one blast a year because you can drill out and charge out. The value around that is huge, but we can't quantify it. So I think there's that disjoint, and it takes time for people to realize what that is. And as they realize, then they kind of start going, oh, okay, you know, sort of come on in. So it's that transition through the innovators. I think they're the brave people. They're like, okay, they take risk, and they're happy to kind of go through that curve, and they understand that curve. But the majority, the early majority, don't want to take that risk or don't understand that and have different expectations. So there's that disjoint.
Fantastic, fantastic. I mean, Bob, you operate in that space, right? So, I mean, as a renowned service provider in the blasting and explosive space, I mean, you've had the luxury of and the opportunity of playing around with multiple systems, various systems. Some of those systems I don't specifically like, you know. but so you've also had customers' expectations change. You've also been involved with evolving expectations and challenges. Right? So to what extent has RAM leveraged various technologies, you know, technologies and innovation to address these customer challenges? How much of reliance do you place on technology to help achieve the end game that you're trying to set out to?
You know, with the technology, you know, we do our best to stay on top of everything that's coming out, and I mean, some technology you just know you've got customers out there that have a specific problem and you know it's going to address it, and then there's others that you explore it, and just like both of you guys said, you know, the testing and the quantification gets very costly. So you got to find the right partner in it, and that's really what it takes, and that's what quickly evolves a lot of these products out there, and a lot of times when we're there, you know, because we're in the field all the time, and we see a lot of needs right there. But the other area where we get a lot of good ideas from is all the companies we work with, because they come back and they say, hey, what about this or that, you know, and we're like, yeah, that's something we need to go back and revisit and take a look at that, and that's what's really evolved a lot of the softwares and things like that, and like with the machine control and things, because they have very specific needs on it. And, you know, if there's one thing that I think all of us have brought up, it's the value. What's the value? And, you know, you just got to get people away from it. Costs how much? It was interesting because I was having a bit of a flashback of listening about throwing the cell phone down the hole. And, you know, a long time ago when I was selling electronic detonators, it was pretty lonely out there because there wasn't a whole lot of guys out knocking on doors with electronic detonators. And at the time, you know, we were trying to sell these things for $50 or whatever each, you know, and I mean, we were losing money on every one of them, but we were trying to get the thing going. And we knew that there had to be the right companies out there that had, whether it was a vibration problem or fragmentation problem. I just kept thinking, you know, I just got to get that order from one of these guys, and you know, you'd go in and you'd meet with the manager and you'd tell them about all the great things electronic detonators can do, the testability and all these great things, and we'd get to that price. They'd bring it up, of course, and so we'd talk about price. I got two orders. One was get out, the other one was stay out. And, you know, but it was interesting because, you know, it was that same customer that down the road had some issues, and he said, hey, you know, you came in here back a year or two, whatever it was ago, and you brought this, you tried to bring this technology to us, okay? There's more activity because just like you showed in the timeline, I mean, there was a flood of papers at ISEs and things like that, and just even at EFE when you saw with hydrogen peroxide, the buzz is out there. And then they're more willing to adapt. And of course, with the electronics, where we could easily show the benefit was when we got into the casting operations, because just 1%, the savings was a no-brainer. But you got to have good partners out there, and you know, all the mine operators, you know, we need that help to progress this. And that helps everybody because it elevates it. And, you know, and what we've seen is as we've been there, we've learned from it, we've improved the products, and it just continues on. And that feedback is so critical. But the partnership of it, that's really what it takes to move it forward.
Yeah, partnership with your customers, yeah.
Can I just build on what Bob has just said? I think sort of recognizing that technology has to be fit for purpose as well, right? So why take a wireless detonator that costs you a phone when you're trying to just break waste, right? And dig and excavate waste to take it to the waste dumps. If all your value driver, or all you're trying to do is fragment the rock. If you then add another level or another value driver to that, which is now mine productivity, so we've moved away from blasting waste into blasting ore, and we now want to optimize the mill, well, now you need good timing. So your non-L timings that you scatter might not, or your timing configurations might not work. So that kind of gives you a justification to move to a more costly EDD, right? If vibrations is another one, then that kind of really eliminates the potential of having non-Ls because you have to protect, that shaft or whatever. So you have to move towards it. So you incur the cost. If now we look at wireless, and all of a sudden, back to your quarry example, is if they can reduce from, I think what you said, 2 to 3 times per week blasting to 2 to 3 times per month.
Yeah.
What if they can blast 1 time every 6 months? Which becomes another value driver, but would EDDs be able to do that? No. So that might be the value driver in which to adopt a wireless technology. Yeah. Right, so again, it has to be fit for purpose, and that fit for purpose is defined, I guess, through the value drivers.
I also have a comment.
Please.
A lot of innovators invent problems that doesn't exist. I think that's a normal thing. But I also think we need to discuss, are we solving a problem that the customer understands, or are we just trying to improve something? In my experience, if we're trying to improve something, it takes a lot of convincing, right? A lot of convincing. But if there's an existing problem that a customer desperately needs help with, they understand the problem, and then the solution is significantly simpler. What I see is that there's a lot of suppliers. Some suppliers are doing this very well because they understand the customer base, they understand the situations, and they're trying to address real problems. And in this case, it's simply a matter of educating the customer. But in most cases, the customers understand their operation much better than we do. So if we try to go in there and sell them something which requires tremendous change, and it's a pain in the ass and change things. We all know this, right? So we can make things easier for us as innovators, and we can make it harder, and that is by being better at defining the problem we're trying to solve. Obviously, then comes all of these things. We're trying to define the value in dollars and pounds and all of these things. But there are substantial problems out there which we can address, but nobody's interested in solving those problems because they don't know how to do it, right? So we talk a lot about improvement. Okay, so that's one part that's the hard thing to sell improvements in my mind. The easy thing to sell is trying to address problems where they arise. So if we try to roll something out through the entire mining ecosystem, that's going to take us forever. So try to pinpoint the customers who understand the problem you're trying to solve, and then you grow from there.
Yeah, but Thomas, it's solving for a problem that exists is easier to talk to and upsell a new innovative technology. But solving for a sale of this new technology obviously comes at a premium price. Right? So what then are the trade-offs to consider? I mean, how do you manage that?
So I think, let's start from the beginning. Developing new technology in a complex industry costs a lot of money, time, effort. Time is just one major component in that cost. Obviously, things will be expensive. But yet again, you need to understand why you're doing it, and is there a clear defined problem you're trying to solve? So can you communicate to your customer, yes, this is a direct solution to your problem. It's rare to do that, it's hard, I understand that, but if you can do that, the communication becomes much clearer. And it's really about mitigating risk. So if you can mitigate your implementation, your rollout risk through that customer partnership by solving a well-defined problem that they already own, you can mitigate your own risk. And the way we have done is that we have redefined the terminology. We're not talking about customers, we're talking about partners. And another thing that we did very, very early is that we had an open book policy. We showed them everything we wanted to do. We broke down the cost. We told them this is our cost. This is our cost. This is what's it going to cost. And then we require the same from the mine. We said, what are your costs? And then they outlaid the cost, and it turned out that their cost was significantly higher than us. So in that way, we could quantify the problem, and it made sense. And I think the second thing we did is that we gave them very clear insight on our process, and also a risk mitigation process, which allowed them to kick us off the mine if they weren't satisfied. We said, okay, we're going to take the first step. We're going to give you in the report. You're going to be included in the process. If you see that our way of doing things is not to your satisfaction, you can throw us off. But if you accept it, we take the next step. And by doing that, we didn't not only deliver a very, let's say, collaborative process, which really aligned our businesses. At the end, the discussion of price weren't even there, because we solved the problem, they understood our cost, they understood what the margins we needed, and they accepted it because the cost of their problem was much bigger.
Yep.
Thanks for that, Thomas. That's really great. Ellen, if I can ask you, we've seen what happens when technology and engineering fails. Right? And could this be one of the reasons why the industry's resistance to attract new technologies and new innovations exist? Or what are your thoughts on that?
Absolutely, and I think it talks to that confidence, right? So whether the technology was invented to solve a problem that didn't exist, let's remove out of that world there, because I think that's But when a technology is developed and it fails, I guess you kind of have to do a bit of an analysis on why it fails, right? And I think there's multiple mechanisms in which it can. I think 9 out of 10 times it's probably not the technology in itself that has failed. I mean, the technology might not be optimized, it might not be the greatest product in the world ever, but I think 9 out of 10 times it's those enablers that haven't actually enabled. You know, Bob talked to FlyRock, and I guess, my previous life in Anglo-American, we had incidents where we had FlyRock, and we know how to fix FlyRock. I mean, Bob talked us through it today, right? If, it's part of the design. You can design FlyRock in, you can drill FlyRock in, you can charge FlyRock in, the conditions can change. If you don't recognize that full system and work within that full system and the partners that enable that, so working with the surveyors to give you the drones and the scans, working with the drillers to make sure that they drill it properly, working with the OEMs to make sure that, the technology actually delivers the information that you need, working with maintenance to make sure that the sensors are calibrated. All of those things have to be in place so that you can actually have the information that Bob was talking about today to mitigate FlyRock. And I think we, as individuals, focus and we swim in a swim lane. We go, I'm drill and blast, I just do this. Day in, day out, and I swim back and forth. What we really need to do is become a water polo team or a football team where we understand, our areas and we can move between it. So defense plays defense, but he covers a lot of the pitch. But his main objective is to stay in this certain area, but he or she transitions through it. And I think that's what we don't do very well. We don't understand how to enable these technologies and then work with the people who, help enable it.
Yeah, thanks for that. Bob, if I could ask you, I think we've spoken about it a little bit, but sometimes we only know what we know, right? Sometimes there isn't a challenge or a problem that needs to be solved unless you made aware of that problem, right? And we do know that mines are getting deeper, more complex, geologies are more complex to mine out. How do you see this playing out from a technology perspective? And from a service provider to the industry, where are you putting your money in?
I would say, what we look at, the expertise has got to be improved out there, and the tools that they have available. Because when you look at like the deep mine operations where, say for example, wall control becomes a bigger and bigger issue, the practices that they have today probably won't be acceptable as they get deeper in there. And in cases like that, I think, that's where we need to see, one, the level of personnel that are going to be in there handling that, the equipment, software, and things like that. They need to have the right tools with it. And along with that, the other key thing is training. You know, because it kind of falls back to the earlier question. You know, there's been really great products that went out there that were either misused or used in the wrong application or whatever. And one thing I learned about anything new coming in the field, bad news travels way faster than the good news. And that's one of the challenges that we have with that. And you know, that's one of the key things I see there is we've got to get that level of expertise up because the demand is really going to be pushing hard on that to be able to manage that, to be able to get the job done and done it safely and with, you know, with the accuracy that we need.
Yeah. No, thank you. So, I mean, I would like to say, I mean, there you have it. I mean, I think we're going to experience resistance. We're going to experience barriers that we need to overcome. Technology definitely has a place, definitely a significant cog in the wheel to take us forward. And I think before we close, I mean, any final thoughts on the topic from either of you?
One thing I would say is just to have the openness to try and the partnership that, hey, we've got this little part of the mine, you can go over here, and if there's a problem, okay, it's not that big a deal. But that's really critical and imperative when you're trying to launch different products, whether it's the explosives or whatever the case might be. And I know that the work that I've been involved with, if it wasn't for that, a lot of those products would have been way more than the 13 years or whatever, you know, like you had on the chart. It just pushes it out further. And, you know, I look back today, I mean, people early on thought you were crazy with electronic detonations. Now today, nearly every quarry I go to, they're shooting them. So it's great to see that people realize and understand the value it brought, and man, they're off and running with it. And you know, it's continuing to get better, and just like with the explosives as well. That's the key thing. We need that help to help, you know, evolve that.
Yeah, fantastic. Thomas?
I just like to say I love this industry. Well, I hate it and I love it at the same time. But when you're talking about technology and where I am from, I can't pinpoint any other industry where you have such a complex ecosystem of technologies. So we work with Boliden Mines, you know, we spend some time with LKAB and all these, and you have automation, you have AI, you have, you know, these extremely complex environments where you have to have life support systems, right? Who works like that, right? Office workers wouldn't accept a day in a mine. Huh? We have advanced water treatment and chemical processes. We have heavy-duty equipment that crushes enormous amounts of rock every day. So when we're talking about technology, we are talking about an industry that is heavily technology dependent on all of the aspects, and the opportunity for development is everywhere. So it's a process. It will take time, and as the globe is changing quicker and quicker by the day, I think we will get there. And I think these cycles that you're talking about, Alan, is going to get shorter. Never going to be short enough for an innovator, sure, but there will be improvements.
Alan?
I think just to build on that, you know, I think the cycle will remain the same. They will get shorter, but you will still have an innovator. You will still have an early adopter, an early majority, and so on and so forth. But if there's one thing that I can impress, or hope to impress on, I guess, our colleagues today is just think about that J-curve, right? You will go through that adverse effect, and I think it's working with, whether it's up to your manager, your CEO, or down to the guys on the ground, or, you know, your stakeholders sideways. It's really working with them and giving them that visibility, and, you know, affording yourself a bit of grace to allow that to happen. And then the quicker you can allow that to happen and design around it, the quicker you get out of it, and you actually start seeing the value that it promises. And I think, you know, all too often we just very quick to dismiss that and go, nah, it's, you know, it's too costly, or it's too dangerous, or it's too this, or it's too that. That is, you know, that's part of the gig, I think, at least in the paradigm that I live in.
Fantastic, fantastic. We can talk about this for days, but we can't, so I'm not sure if the audience wants to ask us a few questions.
Microphone back to Dirk, please.
please. There we go. Thank you very much. Technician panel, thank you very much. A fantastic discussion. There is one question on our app which I would like to put to you, but talking about barriers that needs to be crossed, the one barrier that remains for us to go to T is just to get through the poll that we've done. So whilst the folks are still thinking about it, the one barrier here is that we have 16 respondents, and if I look at the group, my maths is way off, but I think we're still missing a few opinions. The other assistance that I need is that according to this poll, it is either, and maybe it's just the composition of the audience, it's either the accountants or the HR people. That's the biggest barrier that when it comes to technology adoption. So for those of you who may disagree, if I could ask you to quickly go to your app and help us change that opinion. But in the meantime, while you're thinking about that, the question is that, and I don't know, Nishan, maybe we'll see who's the best suited expert to answer this, but the question is there perhaps a difference in the trend of technology acceptance and adoption when the technology is invented or, I guess, presented and brought forward by an established entity or company? In other words, perhaps does your reputation, the entity that brings the invention forward, does their reputation or the size of that organization matter?
Not sure. Open to the team. Personally, I think it depends on the technology, right? Obviously, it does add value if it is presented or offered by a well-established and competent organization. It definitely adds to the technology buy-in. But ultimately, the technology has been designed to serve a purpose. And if it serves that purpose, irrespective of who delivers that technology, it shouldn't really matter. Right? I'm not sure if there's another view.
Any other view on that?
Yeah, I'll comment quickly. Under the assumption that the technology will deliver value, I think it's also how, so big, small, it goes back to values and how those companies breathe and demonstrate, is it visible, felt, adoption of those values, right? Are they transparent? Can you trust them? And I think it does, in the early stages, it comes down to trust. And, if you can't trust someone, big or small, you're more likely to kind of be a bit adverse to it. If you can trust them, and they're a small startup and they've never existed before, then I think you're more likely to give them a go. So I think it's not just the technology.
If I were to just put on my Ravi cap on, probably the reason why he's collaborating with BME, right?
Maybe. Nishan and our panel, Alan, Thomas, Bob, thank you very much. So we have given it a bit more time. Some of the results have changed a little bit. It's quite interesting. I don't know, you should be able to see the outcome of the app. So at this point, it seems like the accountants are winning the black flag for holding up technology by a small margin over our HR people. So basically what we're saying is cost and investment constraints, which is a financial or economic incentive, is just short of 40% of you feel that's the biggest barrier, followed by resistance to change. So I'm sorry, our HR colleagues, if I put that bucket in your space. And then followed by the engineers. And I think something that is actually very encouraging and worth mentioning is that only 7% felt that it is our regulators that's holding up technology. So I think that is a very good outcome, and I think a very good compliment for the way that our regulators amongst this crowd, or impacting on us here today at least, is going about their business of regulating the industry. And I think that's fantastic, and I think that's applaudable. Let's start, and I'd like to welcome onto the stage with me here Tamara Whittaker. So our next speaker certainly has the tech and the tools and the talent, and is passionate and experienced professional in the commercial explosives industry, currently serving as technical service manager for RAM, with nearly a decade at RAM and prior experience at some other explosives manufacturers. Tamara has built a career that spans field operations, project management, technical consulting across surface mining and the underground environment. Please help me welcome Tara Whittaker, who is going to talk about something I probably know the least of all the topics today, fragmentation reduction through cap rock management. Thank you very much. You're welcome.
I'll just stand over here. Sorry, guys. Hi, I'm Tamara Whittaker. I'm going to talk to you guys a little bit about fragmentation and cap rock and a case study that we did a couple of years ago and the process that we went through to, that buzzword again, optimize and improve the fragmentation for this operation. So just a little overview about the quarry. Quarry in the eastern U.S., limestone operation, 5 million ton a year, right on the south end of a major metropolitan area. So regulations were pretty strict. They had a lot of air overpressure that was being closely monitored by the regulators. And if they got even slightly close to the limit, they were getting calls from the regulators saying, hey, watch your numbers there. Patterns were, 3.3 and by 4 meters to start with on the front row. And then they had an internal pattern that was a little bit different initially. You guys can see that there is a 2.7 by 4 meter internal pattern. So burden spacing. 114 millimeter diameter borehole that they were starting with, and we were running about 20 meters on the bench height. So pretty good size high wall. And the patterns, well, in my opinion, they could have been bigger, even at a 4.5 inch or rather a 114 millimeter borehole diameter. So just to give you guys an idea, that obviously when you start any kind of project, you want to know what the problem is. The customer comes to you and says, hey, I've got a problem, can you help me solve it? So these guys were under the impression that their crusher was operating below what their target throughput, which it was, but they thought, let's see if the fragmentation is the reason it's operating below the crusher throughput limits. Plus they had excessive oversize. I mean, we're talking oversize to the tune of the 992 cat can't lift it, has to push it across the quarry to get it to the oversized pile. So pretty good size rocks. And then they did have a lot of fines, which obviously is indicative of shrinking in the patterns to try to make up for the oversize they were getting, to try to take care of that. Now they're pounding the rock and turning the internal part of the pattern into bug dust. But because of that, they started to lift up or reduce stemming, so now they're starting to get some air overpressures or some error. Now they're starting to bump those regulatory limits. So these are all key areas of concern for this particular operation. Obviously, you want to keep the neighbors happy. So what kind of tools did we use for this? There's a lot of tools out there, and I find that for us, if we really want to quantify a blast, one of the key things we use is GPS, and we're seeing that more and more common. You really have to know the holes or where the holes actually are, so you know where you start, so that any changes that you make, you know if the changes are because when you made adjustments to the pattern, that the pattern is drilled out the way you designed it. Additionally, we use drones, that's the new, right? Once drone came on the market and it got easier and easier to get those licenses, at least in the States in 2017 when they released their drone license and the requirements for that, overnight everybody was using them. And they make great for making 3D models, but also getting good quality video. We use the 3GSM software. It's another one of those blast design, blast audit software that's out there that uses photogrammetry, generate proactive blast design or blast audit options. And for both the blast metrics for the blast design audit side, but also for the fragmentation side. And then high-speed video cameras. Still, even with all the technology out there today, high-speed and regular, good digital quality videos is one of your best blast audit tools. So how did we do this? We wanted to look at the oversize. We wanted to look also at the backbreak issues. You guys can see that here, because of the nature of the cap rock, which I'll show you here in a second, it would break off in these just huge chunks, and they would just push them right over the top, and then they'd have issues with drilling and getting their holes right where they wanted them in that front row. Back shatters, so hitting the high wall so hard that they were damaging and preconditioning that next shot break or even the next high wall. If you don't have enough relief, all that energy is going backwards and damaging and preconditioning that next high wall, which then affects how your explosives distribution or explosives perform on the next blast. And there's that cap rock, that was the big one, right? So this cap rock was, what, 2 to 4 meters-ish in that range, depending on where you were at. So it's right in that, what, stemming zone? Right where you stem. You can't get any explosives energy up in there. Yeah, there you go, 2 to 3 meters. And the really interesting about it was you had one section of it that was pretty solid all the way across, and then you'd hit one section where it started to split. So now we had to look at how deep was that section that started to split where we started getting a prominent seam. The interesting thing about this is if you look down here, 100 meters to the right of this, no cap rock. Thinly laminated all the way to the surface. But this particular section of the pit was causing him a lot of heartburn. They also had issues with, so on the oversize, floor control issues. So their drilling depth, maintaining drill depths. If you guys can see this here, that's a high bottom, or we call that kind of high. That's about a 6 foot, 2 meter difference in elevation between this here and just this section right here. And then you go down here. Of course, this over here was intentional. These guys had a lot of water. They had a river, a creek that just come right into the pit. So they were pumping. So they purposely made the low spots over here around the outside of their pit and high wall to divert the water over to the pump areas. So some cases it's good, some cases it's not. Their crusher throughput. So they were targeting 1,800 tons an hour. That's what they wanted. They were told, the crusher manufacturer came in and said, we guarantee you're going to make this. Well, they weren't. They weren't even coming close to what they thought they were going to be getting. So that's what they wanted. One of the issues that we saw, and one of the reasons they said was the crusher, the oversize, was plugging up the crusher. So we wanted to look at what was oversize, and how it was affecting the crusher, and how much time. Were they getting black belt time, or was it just they had too much hammer time at the crusher? All of those questions you look at. They had 3 rock breakers running in the pit. So your secondary breakage costs are going up, and that's a very expensive. I mean, consider it this way. You paid to break it with the blast. Now you're paying to break it with a secondary rock breaker, and then you're paying to break it again when it goes to the crusher. So now you've done 3 different ways of breaking it. So why does that, your cost per tons are going through the roof. If you can get it to just break from the blast, you're in a lot better situation. So yeah, the one crusher was at one with the breaker was at the crusher, and the other 2 were in the pit. And occasionally they had to do a secondary loader because there was so much oversize they had to sort it out. They couldn't keep up with the truck, so they'd have to bring a second loader down to make up for the time. One's sorting and one's loading. So it just really depends on how your operation works and how much money it's going to cost you. So what do you do when you do a good project, or at least our highly recommended optimization, is you got to collect a good baseline. You have to collect enough data so you can get some results and you know where you're going to start, so you know how to measure against that. And then, so you do the analysis. We do pre and post blast flights in this case, so we're doing a pre-flight to verify the blast design, and then we're doing a post-flight for fragmentation analysis. And then we'll look at both the 3D and 2D fragmentation and the blast pattern to make sure it sticks in. We did 5 test blasts for the baseline. We did 4 implementation blasts once we started making changes. just to get to the point and to prove the proof of concept. So let's talk about those baseline blasts. Once again, I mentioned to you guys we got almost 3.5 by 4 meter pattern on the face row. And then internally, they had a little less burden internally, same spacing. So this is what we're watching right here. Gets a little exciting. So if you pay attention right here, this is what we're looking at, and you can see the oversize go right down there. We'll slow it down a little bit so you can see it a little bit better. So you see where the energy's going. The whole blast is shooting out from underneath that cap rock, and the cap rock is just dropping down into the pit. Not really fragmenting very much. You know, the nice thing about the fragmentation analysis, when you do the post-blast analysis, is that you see the big oversize, but you don't really know where, you kind of see where it's coming from. How do you quantify it? You can see very clearly exactly what's happening when you start to look at the fragmentation. So there's your muck pile. We got a picture of the muck pile here. And then this is a 3D model generation. So what did that look like? What did we see from just the blast video? First, you see a lot of block movement. The surface is there, as I mentioned. Blast moves out, things drop down. You get the venting through the seams, and not just, and you guys might not have seen it, and you'll see it on some later videos. They didn't just get venting, you kind of see here. These guys also had some pretty significant vertical seams that caused some issues, and I'll show you some examples of that here in a minute. But so you would get venting this direction up, but you get venting right out on those seams where the energy goes out in the cap rock, and you lose that energy, and it doesn't transmit up into the stemming zone. And then if you looked, one of the things I mentioned about the back shatter, where we run into, is if you look at this section right here, the opening of that blast, and then fragmentation over here, there's a significant difference in the fragment size. And actually what I noticed, and I'll show you from the fragmentation analysis, you can tell where that blast was initiated from by the muck pile shape and the fragment size in the muck pile. So kind of show you that right there. Everything in red is 0.6 meters or bigger. Everything in red there. And so on the first blast, the distribution ranged from small particle size to about 0.02 meters, with the largest being 3.6. That's a big rock. So that's not going through the crusher. They're lucky to get one that's even close to a meter that's going to comfortably go through the crusher. 34, or rather 0.7 or whatever, is their largest rock to go through. Just to kind of break it up more specifically, we wanted to know, okay, we've got our 0.6 meter size that they wanted to start at that and call it oversize, even though technically for them it wasn't quite. But that's where they started to see problems. We wanted to break it down into, well, US foot by foot, so every 12 inches our foot, so 0.8, 0.9, and then 1.2 meters for you guys. Everything, you can see that here, everything. The separation of 21% of the blast, and this is all on the surface, was over 24 inches, 0.6 meters. And that's a pretty good size number, especially with their pattern size that they were running. So we blasts 1 through 5 really were all basically the same. So we had this same setup, same pattern, roughly the same number of boreholes and the same bench. It's just where they initiated from. So there's your blast 2 fragmentation. See that? Like we said before, when you look at the analysis, that is the cap rock that just floats in the air while the blast shoots out from underneath it and drops down and hangs out right here. Barely even moves. You can almost see the shape of the bench on some of these. So fragment for blast 2 was 0.1, almost 0.02 meters to 2 meters, just over 2 meters in. Once again, there's your size. Now notice what you see when you highlight and block out all the noise from the smaller fragments. Here's your cap rock. here's your face. Those big chunks from the back shatter, you start to see the bigger rocks that come from either the open end or just the face in general that's been preconditioned, so you start to see some of those bigger chunks. We did do, on phase one, we did just an initial internal examination of the muck pile, just to demonstrate how much fines that you guys were getting. When we did phase two of the project, we actually did a 6 blasts, 3 to 4 times each internal muck pile analysis as they did digging and did progressive digging. So we did a pretty in-depth analysis of both surface and internal muck pile for fragmentation to just look at what kind of differences we can see. So the average results for blasts 1 through 5 was about 19% oversize over that 0.6 meters and over. Of that, 9% of it was between 0.6 and 0.9, and then 4% of it was 0.9 to 1.2, and then 6% of the overall numbers were over 1.2 meters. That's a pretty good size number, considering you've got to sort all that out. So it required the secondary breakage for every single shot. The thing that really concerned them about secondary breakage, sometimes they were like, well, because of the kind of company they were, sometimes it didn't bother them to run secondary breakers because they'd use it as an opportunity to train operators for more difficult stuff on the construction side of the business. However, their biggest complaint of secondary breakage was, for some reason, that breaker rock just liked to cross-link when it hit the crusher. So it was like, it would just bind up and clog the crusher so much more. It must, for the angular or however, because of how it broke, but they would have to rake and rake and rake forever to get that secondary breaker rock to not clog the crusher. So they ran into more issues with that than they did regular rock. So they didn't like having to do secondary breakage. So as I mentioned, 0.86 meters was where they considered oversize for the loader, and then the loader would handle it out, and then it would go for breaker rock. So 2 things they said that their crusher time based off of the study was the downtime was due to the crusher being plugged up, they weren't truck limited. In other words, they didn't have a lot of time waiting on trucks. The trucks were waiting there, and they were waiting on each other to dump and to get the rock through the crusher. So, summary and basics, oversize over 0.6 ranged from 17 to 21%. Press the correct button. Majority of the oversize is generated from the top surface, from the cap rock. So we said, and on the shot breaks, as I mentioned. So what we wanted to look at was how we can resolve that issue to help these guys get their oversize down so they can get crusher throughput increase. So there's that vertical jointing, right? Geology, how that affects. It can make it really difficult to get energy up into the cap rock area when you've got horizontal bedding planes with pretty loose seams and contacts, so you get venting out horizontally. And then you've got these blocky sections of the geology, so you have to figure out how also get that energy, because it stops right there and just vents right out. So we come up with the solution, not a new solution, people have done it before. We did a little bit different way about it, but we decided we were going to go into each one of these in between the holes on second row, third row, and in between the burdens, and put some satellite holes, drill them in there. Small diameter, so we could get explosives distribution better, small powder factors. We also use these items, you guys may have seen them out there, they're called rock locks. They're essentially not a plug, but what they do is they give, it's just a slight bit more time of confinement to hold down the stemming and the explosives energy for those smaller diameter satellite holes. They decided, because they wanted to get energy up and we weren't doing any satellite holes in between the back row, we wanted to put some air deck in there to give them a little more energy to get it up closer to that powder column. And then the other thing that we did to try to help alleviate the back shatter and back break was put a little bit of extra timing at the end of each row, just to allow a little bit more time for that pattern and for that explosives energy to distribute the material before ending it, so there's a little more relief and hopefully a little less damage to the high wall. So let's look at the test blasts. Test blast 6, and 7, we did half the pattern with the satellite holes and the other half the pattern the standard way. Direct comparison, right next to each other, fired in the same blast, so we had an opportunity to compare apples to oranges, but do it a couple of times, and it just gave us an opportunity to look at the differences. On blast 8, the entire blast was drilled with satellite holes to show the end results, our expectation, full implementation. Our satellite holes were 63 mils and about not quite 2 meters deep initially on the first round on blast 6. And then very, very little difference. We put about a meter, sorry guys. We put a meter, 1.2 meters of stemming on that. So not a lot of powder. I mean, we were really running 0.2 kgs per cubic meter, not a lot. And we did 2 holes per row. I'll show you a picture of that here in just a second. In between the mid pattern, and then 1 hole. Oh, I've got it right here. That bad, huh? Jeez. Sorry, guys. Anyway, 1 hole between the spacings of every row. So as the row goes down, we're also putting a mid spacing. So mid burden, mid spacing. So same basic concept, except for the pattern. We didn't change the pattern much, but we did get our satellite holes pattern. I'll show you what that kind of looks like here coming up. So we're I'll watch that again. So can you guess which side's got satellite holes and which one doesn't? You can see right there how it just breaks this area up. So broken right there. So there's your high speed again. So this opening section, and again you can see, I guess you can't really see that because of the lights. That's right. Sorry, it's probably kind of harder to see there. So we had this section on the left side of the blast was where we had the satellite holes, and on the right side is where we didn't have the satellite holes. So if you look at it, you can kind of see it in the blast video once again. Let's look at the blast video and just look at it little by little. This looks just like it did before from the original blast, where all the energy is just going out from underneath. And then you look at this section. This has already moved out farther, even though it was shot later than this, but you're not seeing that same layers of material. So we did see some marked improvement, though, when we fired this shot and stood on the bench. We just looked at it, all of us just went, because it didn't look like it. From the ground, it just didn't look like there was an improvement. We just were like, oh my gosh, look at all that oversize. It still looks really, really chunky. Maybe this wasn't such a good idea. And then we looked at the actual results. No satellite holes, satellite holes. So it's that, remember that old rule? This one, everyone says the thumb rule, right? It's about this size, it looks pretty good. This one, yeah. So dug better today, depending on if you or hung over or got enough sleep last night, got in a fight with a spouse, whatever. So the nice thing about this technology that we've got now, especially with drones, is the ability to actually physically measure what we're getting out there. and see it. So we don't just get that, we tried that before and it didn't work, or why it didn't work, or it seemed to dig better today than it dug yesterday. So, as I mentioned, so everything in that white is over 1.2 meters. And that's a lot. So the overall shot, just to look at it, was 19% still in the oversize range. Remember before, from the baseline, we were 17 to 21% with an average of 19. So it doesn't look like there's any kind of marked improvement here. So I keep pressing the laser button. So if we looked at the standard pattern size where we didn't do any satellite holes, it was 22%. So it was higher than even our highest in the initial baseline blasts. And, some of that's probably part of where it's coming out of. They're in the corner, they're opening up a little bit in, so you don't have an open face to work with. So we can see that. And then you look at 22% over 6.6 meters, 7%. Again, even higher than our initial blast. And then we look at the side where we did satellite holes. 14%. So significantly lower than what our test blasts were. 6% was over that 0.9, and only 3%. So we're half of the 1.2 meter size, half of what we were before. So we did 2 blasts like that, 6 and 7, and then we did blast 8, as I mentioned, full implementation to see what it looked like. So there was one change. They decided to, when we do optimization, our goal is to make one change at a time. One. Problem is, you get out to the field and the blaster's like, I decided to do this pattern this time. You're like, but no, we're measuring. So we did have one of those where he got a little anxious, wanted to help out a little bit, and he shrunk the spacing in a little bit, which only increased the fines. But so we had a little bit smaller spacing on this. Instead of the 4 meter, we were actually in about 3.5 meter on the spacing. But the same pattern on the satellite holes. This is still the same pattern size. And we did start to drill a little bit deeper. The thing that we noticed, the 2 meters wasn't quite enough. We wanted to go just a little bit more because we just weren't quite catching as far down as we wanted. So, see that? I mean, every time, it doesn't matter where you start from on that opening hole, you're going to get that kind of bulge out because of that preconditioning. Exciting right there. Traditional video cameras are so much better because you get the sound with it. Drones, you don't get the sound. It's just not the same. So, I mean, we slowed these down. We only slow them down so much, but there's that opening. Again, you guys, there's too bright. You can't see that very well, can you? Anyway, it's just a slower version of what you guys just saw. Yeah, I mean, a lot of the things we saw really was the same thing, but now we can actually, through the video analysis, we can actually see that there is a difference. Instead of seeing that material on the bench surface just lift up and the rest of the material shoot out from underneath it, we're actually seeing it break up, and that's what we were aiming for. So let's look at some of the results that we got from that. This was the current blast. If you look at the surface in this area up here, look at the clear layers here that you see from the initial blasts and what we got. When we first fired from blast 1 through 5, we saw that very consistently. You don't see that layering a little bit, but you see it's much more broken up in the test blast. So what did that look like in final results after we came out and did the fragmentation analysis? This is what we come up with. It's about 0.07, almost 0.02 meters on the slow side and 2.7 on the large side. So remember, we were as much as over 3.5 meters on some of our initial blasts. So we saw some reduction, but just look at the difference. Remember everything here that was white? Now you got a few chunks. Those are your 1.2 meter bigger rocks. So there's a pretty big difference. So let's look at the final numbers. When we did the entire shot in with the satellite holes, we only had that 14% oversize, so consistent with the test blasts. We had 4% of that was over 0.9 meters, and only 1%. So from 6% down to 1% of the 1.2 meter fragment size. So we did some pattern changes. This was the initial pattern. Remember, I did your 3.3 by almost 4 meters and on the front, and then 2.7 by 4 on the internal, where we added in some satellite holes. So that's how our satellite holes look. Just to give you an idea, these were the satellite holes. Then you had your regular rows, the straight ones, right? And then we would have a double hole. These are satellite holes right here. So we would have double in between each spacing and burden, almost on the diagonal. And then you'd have, again, one in between, and then you have here. So the idea was that energy in those satellite holes in between the burdens, because remember, it wasn't just the problem that we couldn't get the explosives energy up into the stemming column because of the horizontal bedding planes. The other thing we ran into was those vertical bedding planes that had those blocky sections, so you couldn't transfer the energy this direction very easily either. You'd get that venting up. So by adding the additional satellite holes in strategic locations, it allows us to get a better explosives distribution rather than just drilling. You know, some people say, well, just put a little charge in the stemming column, which has been something that people have used. But if we can't get the explosives energy up this way, we can't get it this way. A charge in the stemming column is not going to resolve that. And that's why we did the satellite holes drilled in those locations. So that's kind of hard to see the design there. You guys might recognize this a little bit. So this is what Blast 8 and the timing that went with it. The way we timed it was those satellite holes fired at the same time as the production hole that it was next to or that they were just in front of. So the intent was to keep it on the same timing, which made it a little more difficult to tie in the shot. I think you can imagine it can get a little crazy when you go from 70 holes to 112 holes and making sure that you get all the detonators tied in and logged in the appropriate order so that they don't get out of sequence, because that could cause some real issues. So just kind of summary on that. We did see some changes in the back brake, just from where we had the standard design here and then the satellite holes. So we did see, and it wasn't just the satellite holes. Again, we also had the hole plugs, the stemming plugs in the back. I think that probably helped a little bit. We did see some improvement on the way that it broke the back row. So we didn't see as much rock that was just getting shoved over and broken up like we did in the section like this here. Additionally, there you go. This is the average, right? You got Blast 3, which when we did the analysis fit right in the average of the baseline. And then Blast 8, the full implementation blast. So what do those two numbers look like in comparison? So the average was 19% over 0.6 meters, our 24-inch range. 10% of that was over, of which 4 was between 0.6 and 1.2, excuse me, 0.9 and 1.2, and 6% in the oversize over 1.2 meters. Versus Blast 8 after implementation, 14% over 0.6 meters. That's 10% of that was 0.9 to, or 0.6 to 0.9. 4% of that, or 3%, the next level up was 0.9 to 1.2, and we only had 1% over the 1.2 meters. So what does that result to? If you have a 5% reduction of so we went from average 19 down to 14, it's a 26%. It's a quarter reduction of the oversize there. And if we went down by 6%, It was a 40% reduction in the 36, or rather the 0.9 to 1.2, and then we had a 83% reduction in the over 1.2 meters. So I can say they were pretty happy with the results there. So anyways, we made some suggestions for phase 2, which looks like we're running tight on time. So, but mostly it was just monitor crusher throughput so we can do some analysis to see if and some improvement there. Monitor the rock breaker hours a little bit better. They weren't very great at that. And then we did do the internal muck pile fragmentation analysis. Talked about different studies there. They're still doing it, so they're pretty happy with the results. So I'll go through that. Just some long-term recommendations. Obviously, we want to be proactive blast design. Implement the GPS base station full-time, drill navigation, all grade control, all of this stuff to help them maintain their optimization results and improve on step 1, which is what we did here. So you guys have probably seen this a couple times today. So yeah, any questions, I guess, is where we're at. Sorry.
Maura, thank you very much. Very insightful and some very good results coming out there. We've got two, if there's no questions in the audience, one question, Alan, over there. Just you can lift up the mic and just press that little button.
Thank you. That's a brilliant presentation, and I think a good case study for what everyone in this room probably has faced at least once in their lifetime, if not on a daily basis. So thank you for that. Could you talk to, I guess it's probably a little bit of reluctance. You know, when I first saw that, I thought, you know, bringing a drill rig in to drill, you know, satellite holes, and oh God, here we go again. It's an absolute pain. So I'm sure there was a reluctance at the start. The end obviously talks to itself. It's a sustainable practice now. They see the value. But is there any learnings that you can talk to in terms of taking the various different stakeholders on that journey to actually buy into it and kind of grasp, you know, that additional discipline is needed, additional steps, to, you know, the process around that?
Yeah, I think the biggest part about the implementation there, our biggest reluctance or pushback was the drilling and the loading company, because it's a lot more work to load 112 holes and tie that in than it is to load 76. Because it was such a term that we used to use all the time, burning platform for the client, they didn't care. They were going to get what we suggested, and they were going to try it because they had tried so much. They wanted to get their 2,000 ton an hour, 1,800 ton an hour, and they didn't really care what the blasters or the drillers said. That in point, the blasters were, it was a little extra work. They had to bring a few more crew on board, but they kind of fell into it, and we were pretty on board with it. And the drilling company was lucky enough to have a smaller drill available, but yeah, they did change steels or had to bring in a smaller drill to drill the smaller diameter boreholes.
Thanks, Tamara. Any other questions in the audience? Think not, Tamara. Maybe just one. There are a few questions in the app, but we won't get to all of them. I think this is an interesting one, and I'll just add on to it a little bit, and it's as a reference to the oversize. Any views on the impact of that quantity, I guess, of oversize on either the health or the increased safety risk of the operators that they needs to manage all of this oversize after the blast?
You know, one of the things that we noticed, I mean, especially if you can reduce the damage to the high wall, it makes a big difference, because then you're not getting all of that back break, all that back shatter. It makes it a little less safe to load the blast. Because the ruling there in the States is if you've got those big cracks, you're supposed to be so many feet or within good distance. There's no official set rule, but mostly people have taken up about 2 meters back from the biggest crack. Well, when you're getting chunks of rock that are breaking back 6 or 3 meters, and then you're supposed to be 2 meters back from that, it makes it really difficult to drill and load a shot. You have to start tying off. So there is a huge increased safety value there just by getting a more solid, more stable high wall, especially closer to their crest. It allows you more flexibility there as far as that goes. As far as the oversize goes in the pit, I mean, time and effort in the pit, and really the energy and wear on the equipment is a big cost.
Yeah, certainly. Certainly something it seems like you want to avoid in mining. Tamara, thank you very much, and let's give Tamara that round of applause. So just before we introduce our next speaker, we will get back to you, and we'll ask our presenters to get back to you on all the questions on the app. So thinking back on the presentations that we had today, if there's any other questions that come to mind, please go back into the app and just post those questions, and we will endeavor to get back to you. Thank you very much. Ngili. Can we have Ngili's mic switched on?
Hello? No? I'll just stand here. And to close off our speaker sessions, we welcome a renowned economist and storyteller, Dr. Roelof Porter. Dr. Roelof is an award-winning economist and widely recognized as a commentator on SA economics and the political landscape. He has over 40 years' experience serving in multiple influential roles, including economic policy advisor at National Treasury and chief economist of SA Federated Chamber of Industries. He has published thousands of articles and research reports and is the previous winner of the FinMedia Economist of the Year Award. Please join me in welcoming Dr. Roelof on stage to talk to us about mining economics. Please welcome.
Okay, I got the sequence right. The first time I spoke at this conference was in 2006, I believe. So I must have done something right. There are only two things more difficult to do than talk about economics. Half an hour before happy hour. And those two things are trying to climb a cliff that is leaning towards you, or trying to kiss a lady that is leaning away from you. Makes it so difficult, but anyway. An interesting observation I saw on one slide, one of the latter slides, muck pile fragmentation. It does remind me a little bit of the politics of this country. I couldn't resist that one. But you've listened to the must know, and now it's hopefully the nice to know, but not everything is nice to know. Let's start out with a quick macro mining sector snapshot. Your production volumes for coal and iron ore, iron ore is much better than it was in 2005, but coal not doing so well, and there are many reasons for that. It's about the only mining activity, new mining activity is in that area. It's frightening to realize that I think there are about 10 junior miners on our stock exchange, 700 in Australia. And in Canada, it runs into the thousands. A High Court judge of the Gauteng division a couple of years ago found, and this is recorded, he concluded that the Department of Minerals was an irrational and incompetent organization that was obstructing the very investment in mining that this country needs. And it has made a case for its own substitution. That's a High Court judge, not me. I do agree with him, of course, but... And now that we have a government of national unity, the sky's the limit as far as I'm concerned, in terms of what could happen in the next couple of years with regard to this cooperation. So if that judge was correct, and there is a case to be made out for their substitution, is there a substitute available? I think you are aware of the Minerals Council. Just imagine that the Minerals Council takes over the functional tasks of the Department of Minerals. I can guarantee you we'll have 50 junior miners within 12 months. If they can just get the system working again. It hasn't been working for quite a while. On a lighter note, the DGs of the government departments prior to the GNU went on a Lekgotla just before last year's elections, and the theme was, you know, guys, we really need to muster some support from the public. What can we do? And this one chap He said, he raised his hand, he said, Mr. Chairman, why can't we get all civil servants to work 2 hours a week extra without extra pay? Well, that sounds like a good idea. This will win us some brownie points. And they started debating the practical issues. And then one concerned delegate raised his hand and he said, Mr. Chairman, is it okay if we do that in working hours? And unfortunately in South Africa, working hours in the public sector at large and in the private sector, the difference is like day and night sometimes. Unless, of course, you compare the Western Cape municipalities to the rest of the country. They have actually mastered the art of fixing a pothole. I'm not quite sure, but it does require some postgraduate study. In Cape Town, if you report a pothole before 10 o'clock in the morning, it's fixed within 24 hours. And that's a fact. In Northwest, if there's a pothole, after 6 years, a sign goes up, which says, danger, potholes. Okay, well, let's move on with more serious stuff. Your average monthly sales for coal and iron ore, also plodding along. Coal not doing too badly. There will continue to be a demand for that product. This is a 4-quarter average because of the volatility. I had to get rid of that. Manganese not doing too badly. Chromium not doing too badly as far as sales values are concerned. If you look at the value added, the average annual growth, real growth, in value added by sector over the last more or less 13 years, mining is one of the 4 negative sectors, unfortunately. I think you know all about that. The prices haven't been in our favor. And of course, there's been a hiatus in certain areas because of the fallout from a decade of state capture. Let's not forget how much damage was inflicted on this economy as a result of state capture. I was privileged to be part of one of 3 research projects aimed at trying to quantify what this damage was. And all 3 of them arrived at more or less the same figure. 2.5 trillion rand in lost GDP. And between 8 and 10 million jobs that could have been created. This was no joke. But fortunately, that's behind us now. Your gross operating surplus, value added ratio for mining, slightly higher than the total for the economy as a whole. So you can obviously still make a bit of money in that sector, especially now that the gold price and the platinum price are doing what they're doing. I'll get to those slides in a minute. Mining sector contribution to gross value added, we've already seen in the second quarter a slight fillip. In that, it's right up to where to a higher level than it was before COVID, which is good news. And then, of course, one of the main reasons why government needs to take mining and the public administration of mining exploration, mining licenses, permits, etc., and the record keeping more seriously than they have done up to now is that without mining, we are going to have one hell of a balance of payments problem in this country. It's one of the, not the only one of the main reasons why we are looking at the 9th successive significant trade surplus in 2025. So thank you for that. I think that deserves something in this glass a little bit later. But for now, it's only water. There's the gold price. I mean, just what a beautiful slide. It's just a pity that our gold is so deep. But who knows? If it stays there for a while, I'm convinced that there's new life in this industry, and this is even better. I was forced to send my slides to the organizers, who have done a very good job, by the way, about 10 days ago. The only irritation is that since then, of course, the platinum price has changed. But it's still at above 1,600. I'm not complaining at all. The trend is fantastic. This is more important than gold by a very long shot. Over the last decade and a half, if the platinum price increases significantly and it stays there for a while, Mr. Godongwana laughs all the way to the bank. He's the Minister of Finance, if you don't know. He's actually also the acting state president of South Africa, if you haven't picked that up. Mr. Ramaphosa has just departed on a 5 or a 6 day overseas visit, and Mr. Mashatile is on holiday as usual, and so Mr. Godongwana was sworn in, I think this morning, as acting state president. Well done to him. By the way, those blasts, these videos are really pretty impressive. It's just a pity that you cannot invite, or perhaps you can consider that, inviting the Monetary Policy Committee of the Reserve Bank to maybe attend one of those blasts, but get them to sit very close. I'll get to that a little bit later. Thanks to gold and platinum, and to a lesser extent, also chrome and manganese, but mainly because of gold and platinum, our average monthly sales value of metallic minerals, four-quarter average, has just shot up, which is great news. And I expect that to continue. Okay, so let's move over to some more, not negative stuff, but this is a huge concern to us. If you look at South Africa's capital formation GDP ratios, it is below 15%. I would say the average of our major trading partners is between 25 and 30%. This is ridiculous. This is pathetic. It's one of the lowest in the world. And it's not supposed to be like that. If you look at the Afrimat Construction Index, the four-quarter average, that's the red line, it's still lower than it was before COVID. I'm not sure what data the MPC, that's the Monetary Policy Committee, looks at. Your real value of building plans passed by the major metros is just going one way. We're not building in South Africa. And construction is the most labor-intensive sector of this economy. We need to get capital formation going as quickly as possible. If you look at the value of construction works, I'm convinced that there are organizations here present that derive value from this type of activity by the public and private sectors. The private sector, at least, is up from where it was in 2008, but not the public sector. And I don't have to tell you that one of the main reasons for that is certainly state capture, which has led to a large amount of incompetence or corruption within many of our public sector agencies. Hopefully that will improve. Are there any visible signs that the Government of National Unity can eventually start fixing some of these problems? Yes. Within about 6-7 months after the elections last year, the new Minister of Home Affairs, he inherited a backlog of ID applications of 247,000. And I don't have to tell you how important an ID is for a poor South African. So what did Dr. Schreiber do, the new minister? He put a team together, some of these people from the Western Cape, some of the people that he identified at the department that knew what they were doing, and they put a plan together and they executed that plan. And within 30 days, the backlog was annihilated. That's what can happen if you put your mind to it. And if you have a plan that can work, and you actually implement that plan, and you don't go from one meeting to the next and then a pre-meeting for the next meeting. It's so frustrating. You know why they changed the streets in Pretoria into one-way streets many years ago? It was to prevent the civil servants that arrive late from obstructing those that want to go home early. I'm going to just have to dwell on this slide for a minute or two, because this sort of encapsulates one of our biggest single problems, and that's a lack of new fixed investment in productive capacity in whatever sector, mining, agriculture, retail, and obviously certainly manufacturing. So we go back 2007, it's a nice snapshot of our economic history, and just a quick word on capital. What are we talking about when an economist talks about capital? We are not accountants. We are talking about the stuff you need without which you cannot produce goods and services. So for a farmer, it's a tractor. For a small builder, it's a bakkie and a cement mixer. You are intimately aware of the physical capital that you require to do your business, to add value to this economy. For a consultant like myself, it's a laptop and a fast car. And apparently a very pretty car. Because there's a crowd there when I travel to the airport near Ekurhuleni that keep on taking pictures of my car. I mean, it's a nice car. It's silver and quite fast, but anyway, very pretty as well. So we're on our way to the Soccer World Cup. Who remembers that? I remember it vividly because for two reasons. Number one, I'm a soccer fanatic. Hierdie lyfie, nee, is nie vir rugby gemaak nie. I was a soccer player, league soccer player for 35 years. I actually coached one of the Bafana players, Mark Anderson. And the other reason is that's the first time I won the Economist of the Year award, because we were growing at 5%. And I'm the most optimistic economist in this country by a long shot, because I do my homework. And there we go. We're growing at 5% for 4 years in a row. We create literally millions of employment of jobs in this country thanks to building 3 million RDP houses. And then we have the World Cup, and then we have the global financial crisis. Who remembers that? That was a bit of a bummer. A friend of mine at the time told me, you know, Doc, a recession is worse than a divorce because you also lose half your fortune, but you're still married. Which is actually quite cynical. And then we recovered quite quickly. And we were not growing at 5% anymore. It's hard. It was a hard act to follow, but we were growing at close to 3% per annum for 5 years in a row. And one of the main reasons for that, was the governor of the Reserve Bank at the time. Who can remember who it was? I'm listening. Nope. Thank you, Jill Marcus, the only woman to ever hold that job and the best governor we ever had. Because she went to the trouble, apart from the fact that she understood economics, she went to the trouble of involving private sector economists in her decisions and in the MPC decisions. And we seem to have convinced her at that time, we had convinced her that a developing economy should not have a real prime rate of much more than 3%, otherwise you are not going to grow this economy fast enough to create jobs. So what is the real prime rate? I mean, this is not rocket science. It's the prime rate minus the CPI. Let's do the quick calculation. What's the prime rate today in South Africa? Who has a mortgage bond? You're close? 10.5, thank you very much. 10.5, that's a prime rate. That's a prime overdraft rate. So if you're very lucky, you work for BME, you're probably paying prime minus 2. If you're a lecturer like me, you're paying prime plus 2. And the inflation rate, the latest one was published a couple of hours ago. I can tell you what it was 3.4. So we have a real prime rate of 7.1%. During Jill Marcus's term of office, the average real prime rate was 3.1. We're talking about an increase of more than 100%, and that's after some interest rate reductions. The new MPC that was appointed after Jill Marcus's retirement in 2015 by Mr. Zuma, he also appointed the Guptas, by the way. He's on record for saying that this country's problem started when Jan van Riebeeck got off the ship. Anyway, so they asked him what year was that, and I think he replied 1611. I don't know. But Trevor Manuel, whom I actually know quite well, I know his wife better, for one reason only, she's an economist, and a pretty good one at that. Some socialist leanings, but I'll forgive her for that one. Trevor Manuel is on record for saying that the biggest disaster in the entire history of this country was Jacob Zuma. But you need to add to that all these cohorts of his, the Guptas and a couple of people who are now in parliament. Those are the people that should also remind me of the Makpal situation. But anyway, so three terrible things happened to us. Jill Marcus retired. The new MPC immediately started raising rates. Then came state capture, and then came COVID. So from this point onwards, maybe you can just have a quick look at how many important key indicators of this country's macroeconomy are moving in the right direction. I'm not naive. We are not where we should be, our economy. But are we moving in the right direction? That at least is a good starting point. And if there's a critical mass of key indicators moving in the right direction, then next year will look better than this year, and the year after that even better. So what did these MPC members cost us? There you have interesting inverse correlation. You've got the red line is the prime rate, the nominal one. There you can see 10.5%. And the blue line is the index of home loan applications of Better Bond, one of the largest bond originators in the country. This slide was, as the prime rate goes up, fewer people can afford the repayments on the mortgage loans. The fewer building plans get passed. The fewer people find jobs in construction. And who's crying all the way to the bank, or not going to the bank so often? Mr. Kieswetter, who will shortly, unfortunately, retire. That's now SARS Commissioner. Just be wary of SARS. It has the same acronym as Serious Acute Respiratory Syndrome. And they're both pretty dangerous. Household debt costs as percentage of disposable income just skyrocketed as a result of the MPC's weird, incomprehensible decision to absolutely copycat the US Federal Reserve. Every time the Fed raised their rate, we did the same thing. Perhaps it's because the only member of the MPC that actually understands economics is an American. But I don't like him. I've played soccer against him and he swears on the field that gaan hom nog eendag bliksem. Somebody can translate that to the other people. This is what they did. They decimated households' ability to spend money. Because if that percentage of what you earn, of what you can spend, if you have to take a larger portion of that to service your mortgage bond and your credit card and your overdraft, then it's not very difficult to calculate that you are going to spend less money. And if you spend less money in the economy, then you're not going to have a lot of growth, by the way. This slide was published by Business Day as well in an article that they requested to explain to their readers why the MPC have lost their plot. I just want to make one point clear. The South African Reserve Bank is regarded as the outstanding central bank of the emerging market and development economies in the world. As far as its administrative and oversight functions are concerned, their adherence to the Basel II requirements, etc., is absolutely impeccable. It's only on the monetary policy side where they have a serious, serious problem. Because I cannot understand how you can go from one monetary policy committee to the next, and you have an increase in the real prime rate, the real cost of capital of more than 100%. It does not make any sense. And I'd like to quote Joseph Stiglitz, Prof. Joseph Stiglitz, Nobel Prize winner in economics, who said a while ago that there was also this debate about lowering the inflation target. And he said what South Africa needs is a higher inflation target. And he went on to say there is no proof whatsoever that inflation under 10% is bad for a developing country. But for some reason, the MPC thinks that we are the United States. They're not very bright. And that's putting it very mildly. I'm saying bloody stupid, man, in elk geval. What is the unemployment rate in the United States as we speak? And they're concerned about this. Thank you. It's 4%. What's the unemployment rate in South Africa? The broad definition? The broad definition. It's 50% on the nose. 50, if you include disillusioned work seekers that don't go to the trouble anymore of trying to find a job. Does the MPC not understand this? This is serious stuff. They should all be fired. And by the way, I'm in the process of trying to arrange that. I've put a team of renowned economists together who all agree with me. And it's taken me the better part of the last 5 months, and possibly also my marriage, to come up with a report which is almost finished. It just needs to go for peer review next week. And the report's title is Quantifying the Damage Inflicted on This Economy by the Monetary Policy Committee of the South African Reserve Bank. And that's going to make riveting reading. I've got really bad news for them. Household credit extension, the total value of household credit in South Africa today, in real terms, is less than it was 14 years ago. This is unbelievable. An economy cannot grow unless household credit is growing in real terms. It is really just such a pity that government hasn't thought about one of our recommendations, which we'll be making in our report, long time ago, and that is to change the composition of the MPC. 3 people from the Reserve Bank, 2 from National Treasury, because they want growth. They don't like high interest rates. And then 5 private sector economists with at least 25 years experience and a master's or a doctorate in economics. And if you had a 10-member MPC today in South Africa, I can almost guarantee you that the prime rate would be closer to 9% than 10.5. Who would like that? I can tell you the whole economy would like that, except the filthy rich, who have all their money parked in a money market account. We don't need that so much. We need physical capital formation. And there you can see the inverse correlation. As the prime rate goes up, GDP growth goes down. So what caused this high inflation? What is the MPC's rationale? Why did they raise interest rates as the US raised interest rates? So they made a couple of grave mistakes. In the first place, what they apparently didn't realize is that global container freight charges increased over a 2-year period. You are seated, right? 700%. How would you like a 700% increase in one of your major cost items? Would you still be in business? It would be difficult, am I right? On top of that, you had a 400% increase in the oil price, inter alia thanks to that mass murderer who calls himself Mr. Putin, a military dictator de facto. Combine these two, nothing in the past century has ever happened to the world economy as phenomenal as this. It was no surprise that inflation in Germany peaked at a higher level than in South Africa for the first time ever. It was also predictable that both of these key cost items, by the way, 80% of all tradable goods get shipped by the ocean, not by aeroplanes. This was a huge, huge blow. But it was so predictable that after COVID, because remember, harbors were closing left, right, and center, reopening, then closing again. It was chaos out there. But it was so predictable that at some point in time, all the harbors would open again, and the oil price would drop again, and that inflation would come down. Not because of high interest rates. It would have come down anyway. It would have been a natural, and that's exactly what happened, a natural sort of occurrence. There you can see median global inflation. So why did South Africa's inflation rate peak at just about 7% and not double digit like some European countries? It's because of the fact that we are the 32nd largest food exporter in the world. We are self-sufficient in food. But I don't have to tell you that apart from mining products and oil, agriculture and food are the most traded commodities in the world. And I'm going to whisper in my friend Johnny, that's now Mr. Steenhuisen's ear, when I see him again, that while he's Minister of Agriculture, he should build a monument for this country's farmers that put food on our table. Okay, now we're going to go over to counting exercise, the key indicators moving in the right direction. Retail trade sales, we're talking about a figure of, I think, about 122 billion rand a month. This is a major, major indicator, moving in the right direction. Last year, an all-time record high. Has this momentum been kept up? Absolutely. This is first and second quarter this year is just going in the right direction, which is good news. And wholesale trade has also picked up nicely now. It's running at just under 300 billion rand a month, and it's also picked up a little bit of steam. The US trade tariffs, yes, absolutely, it's going to hurt us. I'm assuming that a majority of the people in front of me are embarrassed from time to time by this country's foreign policy. Why the hell could we not just have gone the Switzerland route and remained neutral? Why do you have to choose sides? Why do you have to choose the side of a country like Russia whose head of state has a warrant of arrest hanging above his head? It feels like Texas in the old days. Billy the Kid, wanted, dead or alive. I would prefer the previous But anyway, why could we not have remained absolutely neutral in this East-West communist free enterprise and democracy debacle that is going on from time to time? Why did we have to choose sides? My advice to government is resign from BRICS. I personally do not want to be part of any organization that has Iran as a member. A country that is not shy of the fact that it supports and finances terrorism wherever they can, and is guilty of gross human rights violations on a daily basis. Our constitution and what happens in Iran are so, as far removed from each other as east from west. And rather plow our efforts into SADC, the Southern African Development Community. This is our home. 5 of our 10 major trading partners in high value-added products are SADC member states. If we can collectively start acting like OPEC and make 100% sure that we are just more careful and more systematic and smarter in the way we market and brand and sell our minerals, because the rest of the world cannot function in the long run without SADC's minerals and metals. But for that you need a lot more intelligence, I suppose, within government. I just want to tell you that the other good news is that for the first 8 months of this year, Belgium, which was number 8 on this list, is now number 3. And the US has slowed down the ranking a little bit. So that's good news. They buy a hell of a lot of cars from us, and actually also components. There you have the year-to-date figure. The US has dropped down to position number 6. And Belgium has shot up the ranks, but the top 10 for high value-added products, the top 10 are still intact. By the way, China is not even on this list. They buy coal and iron ore from us, and that's it. And we buy everything from them, including cars that are not so reliable, but anyway. But I'm biased. Our cumulative trade balance, I mean, this is not only moving in the right direction, but it's moving in the right direction at a hell of a rate of knots. I must tell you that I bumped into a trade union leader a couple of years ago at the ETV studios. I'm not going to mention his name. So I had a chat with him and I asked him whether he knew the definition of a communist, which he didn't. I realized subsequently he's not much clued up about anything, but anyway. So I told him, you know what? A communist is somebody who's got nothing, but he wants to share it with you. And he didn't find it funny. An economist, on the other hand, is somebody who will marry Charlize Theron for her money. Which is not a bad idea, depending on the mood she's in. This is quite spectacular news. So this country's gross gold and foreign exchange reserves has hit an all-time record high, and the rand is ridiculously strong, to the detriment, unfortunately, of our exporters. Just imagine what could happen to our mining exports if the rand goes to 1850. Bonus time at SARS, big time, bonus time. So, by the way, this is the value of $1, so you have to calculate the reciprocal to get to the value of a rand. If this goes down, the rand is strengthening. Of course, it's a fundamental recovery. Last month in September, the rand was the strongest currency in the world against the US dollar. Post-COVID recovery rate for overseas tourist arrivals, doing magnificent stuff, and the prettiest star in the universe as far as I'm concerned. That is the future, as far as I'm concerned, of energy. And this is becoming cheaper every day for some applications, and everything else is becoming more expensive. And let's give ourselves a pat on the back. Who of you have got solar? Well done. There's exponential growth in the switch to renewables, especially solar, but also some wind in South Africa. We've been forced to do that, but it's really a pretty good development. And this surprised me. In July, we handled at our 5 ports 100,000 more containers than a year ago. And to some extent, this is the work of Barbara Creasy and taking government's commitment to closer cooperation with the private sector seriously. And now that that court case is behind us, I think it was Maersk that challenged the Philippine company for the Durban Harbour upgrading. hopefully that can also gain some more traction. Imports of minerals and machinery and equipment, remember, moving in the right direction does not necessarily mean that you move up. If the inflation rate goes down, that's moving in the right direction. Interest rates go down, moving in the right direction. And if mineral imports go down, that's also moving in the right direction, because when you see mineral imports in this country, all you see is diesel and oil and petrol. And you can clearly see the impact also of a switch to renewables. South Africans have become a little bit more savvy, and the fact that we are importing more machinery and equipment, that is good news, because what you see behind that is capital formation, and obviously some of the activities that you are planning and involved with. I had to send the slide about 10 days ago. Since then, the real prime rate has come down to 7.1, but my argument remains intact, and that is that interest rates have been very slow to come down. Inflation has come down at a rapid rate of knots. So what the hell are they waiting for? I mean, I don't understand that. Other good news, the Absolute Purchasing Managers Index has finally managed, after a long absence, to go above the 50 neutral line again. And other good news is that your average monthly home buyer incomes for first-time buyers, all buyers, and for total households have increased from 21 to 22 and 23 by 8.5% for FTBs, 9.1% and 8.4%. That is in real terms. So people with skills in South Africa do not find it, the right skills, the right experience, do not find it difficult to get jobs, and their salaries are also increasing. It's the people that are battling to find jobs that I'm concerned about. And for that, we need significantly lower interest rates. What are the growth drivers going into next year? Further lowering of interest rates with a bit of luck. If government listens to our advice and they do expand the MPC, we will certainly have a faster reduction of interest rates. We have fiscal stability. Our public debt GDP ratio is just above 75%. That's in line with most of our peers. It's much lower than most emerging high-income countries, but of course their bond yields are lower. So that's a permanent caveat. Strong balance of payments, very strong. Positive influence of the DA in a government of national unity. You also see it with McPherson, the new Minister of Public Works, where he's the first minister to do something about the construction mafia. With a bit of luck, we can get rid of those bastards. Recovery of key agricultural crops in South Africa, and we've had fantastic early summer rains, which is good news. Gold and PGM, that's right up your alley. Improvements to logistics infrastructure, that's happening as we speak. Partial privatization of Transnet. It'll take some time. I'm not trying to say here today that, everything is rosy and we're going to grow at 5% next year. We'll be lucky to grow at 2% next year. But it's better than 0.5, which we've got right now. So I think that's the frame of mind that I want to put you in, is that are we going to look at a significant improvement next year? And who knows, perhaps getting to 3-4% off a low base in 2027. I hope we do that, because it's about time I win that competition again. Greater private sector participation, we know all about that. Tourism revival, increase in the Better Bond Loan Application Index, and growth of per capita household income. So, quite frankly, if you look at these growth drivers, a year ago, it would have looked a lot more sketchy. So there is certainly something to look forward to. It's been said that a pure optimist believes we live in the best of all possible worlds, and a pure pessimist fears this is true. But I'm feeling rather bullish about the economy. Something of that has to do with the government of national unity. Something of that has to do with the gold price and the platinum price, and the prospect of lower interest rates. I hope I'm correct. Thank you. Thanks.
Thank you so much. That was really, it was an emotional roller coaster. I didn't know whether to be sad, laugh, cry. But very insightful and quite enjoyable. So thank you for those insights. We do not have a question on the app, but I see there's a hand there. So please go for it.
Okay. Good afternoon, everyone. My name is Oscar. My surname is Mola. My company is the Sufficient Grace Trading and the Closet Trading Enterprise. I heard about all the information, which is some of the information, it disagree with the information that I was attending to an investment conference where there was a former statistician, because he was saying the problem about the growth in our economy is education. Our education system needs to be correct. It needs to be aligned with what the economy is going to. And then another thing is about crime, high level of crime, because with our lawlessness, it chases the investors, because no one can want to invest when there's no the climate, the environment climate is not conducive. Another thing is lack of investment in infrastructure. It declined our growth. Like now we are facing a water problem now, which this thing it was seen before, but the water seems to be escalated. This seems to be escalated. Another thing is also health infrastructure need to be improved, because we cannot grow economy when the society is sick, because who's gonna work there? Because we need a healthy society. Another thing is our policy need to be good, aligned with the economy. Thanks so much.
Thank you.
Thank you.
No comment.
Any
No comment.
any other questions from the audience? No?
Thanks.
All right. Thank you so much,
Thank you.
Dr.
Thank you,
Rulo.
guys.
Okay, we've
know.
come to the end of the day, and what a day it's been. We've explored innovation and a whole lot of mining magic. To close out, we'd like to invite our MD, Ralph, back to the stage along with all our speakers, please, to officially thank our speakers for the day.
Lungi, thank you very much, Ralph. Yes, please, if you can join us. Ladies and gentlemen, I do realize that I'm now the barrier between you and some more serious networking. So I'm going to ask Ralph and our presenters to cooperate. Ralph, if you can please move across to this side. And yeah, I think our presenters can join us on stage. Dr. Patak, yes, thank you very much.
I'm going to stand this side.
So to all our speakers, thank you very much for all your preparation and insight that you've shared today. And then in no particular order, if we can start, Dr. Patak. You can move across, and if I can ask Ralph just to give you a measure of our thanks. Tamarin, thank you for sharing. I also now know what a cap rock is. Thank you. Tom, thank you for sharing, Tom before Bob, for sharing your blast basics. Bob, whilst we're on your side, you took the step. Thank you very much for sharing the accuracy in drilling. Alan, thank you for giving us a view and inspiring us that we should behave more like teenagers and get going. Thomas, thanks again for bringing us a whole new technology. Scott, thank you for reminding us where we came from and how far we've come. And last but not least, Dr. Rudolph, not sure what to say. But surely a lot of food for thought, and thank you. That was highly entertaining and a lot of food for thought. Thank you. Thank you, Rolf. Thank you, presenters. You can
leave the stage.
You
Thank
can go
you.
back to your seats. So now, ladies and gentlemen, it really is just me. That's the obstacle between you and some serious networking. I do have a very long list of people that I do need to thank. Firstly, our regulators. Without you, you can't have a sustainable and confident industry because the playing field won't be fair. And I think Dr. Rudolph told us how good and strong a fair playground can make our economy. To our customers, thank you for joining us today as well, and the time you took in traveling and sharing the day with us. To our presenters, to those folks in the background, including our partners that assisted with the arrangements today, thank you very much for your input. And perhaps lastly, Lungi, I hope you had a good first conference, and thank you very much for joining me on stage today. And I think a bigger thanks from the audience, because I think you made it a little bit less sufferable today.
Thank you.
Thank you, ladies and gentlemen.